In this masterclass, we will cover every single concept that a modern data engineer has to know about Kafka. Not just the theory, we will also know how Kafka behaves in real production system. And on top of this video, you will also be given a free structured study material that you can save with you and come back after weeks or even months when you need a quick revision or need a clarity on particular topic. And also, whenever a concept only makes sense when we see that concept in action, we will work on a lab together. So you can work parallel to me as we break things together, understand the behavior, and know how Kafka works the way it works. And this masterclass is designed to take you from I've heard of Kafka to I actually understand how Kafka works in real data engineering pipelines. And if that sounds useful, don't forget to share this video to your friends. Like, share, subscribe, hype, whatever you can to show your support. Now, let's stop talking, let's dive in. Alright, let's begin the masterclass by knowing how I structured this. First, I go through this whole document that I've created, which has index and all the concepts, and all these concepts are divided into phases, and there are 7 phases in total, starting from phase 0 here and ending with phase 6, and they have multiple concepts listed in those phases. Now, unlike our other master classes where I just remember the things and explain it to you, here I'm going to read out the study material that I've created. This is kind of a study material, and I go through every single topic, every single line in this material, and I will explain it verbally as well. So I won't forget any point that I want to mention. So I just listed off all of those in this one single material, and I will also provide a link of this material to you guys. So if you're in any situation where you cannot open any sort of video or like let's say this masterclass to go through or revise the same concept, but this document will be flexible or handy, so you can just open it anywhere you want and go to that concept. And it also comes with an index, so you can just navigate to whichever concept you want to revise. Let's say to go to that concept, this is the document that I'm going to provide you. You just need to, let me zoom it in. You just need to go to that particular concept, let's say partition, and hold control and left click on that concept, and it automatically navigates you to that concept so you don't waste time. And also, I will structure this video with chapters, so and those chapters are sequential and synchronized with these concepts in the material. So if you're going through this material and you want to watch this topic in a video format, you can just come to this video and then navigate to it from the description. You can find those concepts, those timestamps for each of these concepts in the description, and you just have to click on those concepts, and the video starts playing from that concept and not the whole thing. You don't need to find the concept manually. So I structured it pretty well, I think, and this document is handy for you. Now, the structure of explanation that I'm going to follow will go as follows. First, like I said, I'm going to go through every single line in every concept in this document, and then every single concept, let me extend one concept here. So let's take this concept first, the first concept, event-driven architecture. So every concept has a code definition, why the concept exists, when to use, and there will be a conceptual diagram. Right now, I left all the conceptual diagram empty on the concepts. What I'm going to do is I will draw the conceptual diagram live on camera while I explain it in this PowerPoint, and then I just cut that architecture diagram or conceptual diagram out and then paste it in this document. But the document that I'm going to give you, the link I'm going to give you, has all these conceptual diagrams added already, so you don't have to do that. But now, for the sake of explanation, I'm going to draw it uh, live. And it has key characteristics and final technical takeaway. There will also be lab for appropriate concepts. For this concept, we don't need any lab, so it doesn't have any for event-driven architecture, and I don't think there is any for this one as well. But let's say for this one, you see this? Hope you can. There you go. Let me zoom it in. So for this, a few concepts where it is appropriate, there will also be a lab for that, which means we will do that. And here I will demonstrate every single lab, so whenever you want you can do it, so you can get some hands-on experience as well. This is how I structured the whole material, and the explanation that I'm going to do right now. And I think that's it. Yeah. Yep. Let's begin with the topic, the first concept, not topic, first concept. All right. For our first concept, we have to head to our first phase, which will be phase 0. The phase is foundations before touching Kafka, which means we're not going to touch Kafka yet. We're going to first know about the ground rules, how these platforms like Kafka works. And the first concept in this phase will be event-driven architecture, EDA. And event-driven architecture is a system design approach where state changes are emitted as events and other system reacts to those events asynchronously without any direct knowledge of who produced them. By which it means, let's say there are two systems, a producer and a consumer. Whenever the state of the data changes, this producer emits the event without caring about the consumer. That is what asynchronously means. So the producer just emits the event and doesn't care about the consumer. It doesn't care if the consumer is actually active or taking or consuming the data. It just emits the event whenever any state changes. When I say state changes, it means it can be anything. Let's say, for example, any change in database like a create, update, or delete, or alter, any of those changes will be emitted as events from the producer, and these events will be produced without caring about the consumer. They just produce. If the event happened, it just produces. That's how the event-driven architecture works. Now, the key properties include an event represents a completed state change, not command. So it is not a command, it just an event. It just represents a state change. And there is producer emits events and moves on. They do not wait for consumers. We already talked about it. It doesn't care about the consumer, it just emits the event. And then consumers choose if, how, and when to react. Producers just produce the data, and this data will be saved in a log, and then consumer, without, doesn't care when the event is produced. It just decides when and how to react to that. When it says react, when and how to consume that. And then communication is asynchronous by default. Like I said, they both don't communicate to each other. They're asynchronous. They don't work synchronously. So that is the point. And the event itself becomes the contract between the system, just the event. And then EDA is the architectural foundation on which modern streaming platforms exist. Without EDA, those platforms have no real purpose. So the modern streaming platforms, which we are going to talk today, will be Apache Kafka. that is based on this architectural foundation, and that's why we have to know about EDA before we know about Kafka. Why this concept exists? Problems it solves. Problem 1, tight coupling in request response systems. Before EDA, there is also a system which is request response system, which is a traditional synchronous system where services must know each other explicitly. The services that are working in that system, like let's say the producer and consumer, must know each other. The producer must know when the consumer is ready, and the consumer must know when the producer is ready. So they both should be synchronous. Both sides must be available at the same time. A slow or failed downstream service blocks the caller. So they, like I said, they both should be available at the same time. And a slow or failed downstream service blocks the caller. If the consumer doesn't work, producer waits until the consumer get back to work and then emits the event. Until then, the producer is stuck. It won't produce the event. So that is what it means. So if the downstream fails, the upstream will get stuck, basically. That's how this traditional asynchronous system works. Whereas EDA solves this problem. EDA removes this entirely by decoupling producer and consumers. So they just decouple, which means they work separately, uh, asynchronously, in other words. So they don't care about their producer doesn't care about consumer, consumer doesn't care about producer. And then eliminating synchronous dependencies. Same point, because they work asynchronously, it eliminates synchronous dependencies, allowing systems to evolve independently. Doesn't we can scale producer by just leaving consumer as it is. So we can evolve particular system independent to the other system that is working with that system. That is what it says, allowing systems to evolve independently. And then we come to problem 2, which is poor scalability and fan out. Scalability, like I said, increasing the bandwidth or something. So increasing a factor by increasing the system's efficiency. And what is fan out? To explain fan out clearly, I have to mention a point where EDA, the EDA systems, when a producer sends the data, that data can be splitted and read by multiple consumers, not just one consumer. Multiple consumers can read the same data from the same topic or partition. You might feel hard to comprehend these terms like topic and partition, but you will know. But for now, remember this: when a producer sends the data, multiple consumers can consume the same data from same partition, basically. So that is what fan out means. The data can be fanned out. With synchronous API, which is the traditional API, every new customer increases load on the producer. Like I said, they both should be connected. The producer and the consumer should be connected to each other. So they should be synchronous. And that is why the load on the producer get increased, because they work on a mechanism where a producer sends, a consumer sends a request to producer and the producer sends the response. If the consumer sends a request and producer is not active or it is lagging, it takes time and it gets stuck, the whole system gets stuck. If there are multiple consumers and multiple requests are sent at the same time simultaneously, they both get stuck, and that is why the load increases. Whereas in EDA, they don't send request and get response from the producer. The producer just emits the events independent to the consumer, and the consumer gets this data out of the log that stores these events whenever the consumer wants. And that is why here every new consumer increases load on the producer. That is one of the downsides of synchronous, which is traditional API. And there is fan out, one to many communication. I already explained it. I already explained about fan out. One producer to many consumers, something like that. So one to many communications become complex and fragile. Fragile means there is that is viable to break. There is a chance of for that system to break. That is what fragile means. Then scaling requires coordination across teams. Like I said, they should be coordinated with each other. The consumer should send the request and the producer should respond with the response. They should be coordinated to each other. They should be synchronous. On the other hand, EDS solves this by allowing producers to emit one event once. So the producer, so EDS solves this by allowing producers to emit an event once, letting multiple consumers react independently. They don't, you know, uh, they're not dependent on the producer or any other system. They can just react whenever they want, however they want. And then making fan out a natural property of the architecture. One to many behavior, a natural property of this architecture, which is EDA. Talking about problem 3, inefficiency and latency from polling. Polling-based designs waste compute and network resources. Firstly, what is polling means? Like I said, when there are two systems, a requester and a responder, which are known as producer and consumer. Polling means we already talked about the consumer sends request to producer, right? So what polling is about is consumer sending multiple requests again and again to the producer until it gets the response. That is what polling is. So what it does is, so it checks on the producer if there is any new events produced. So if there are no events produced, it just keeps checking for a scheduled time interval or a random time. So it just keeps asking the producer if there is any new events generated or not. What this comes with is the downsides are waste compute and network resources. Because it asks the producer over and over again, it just wasting the computational power to ask the producer and also the network resources. Whereas we will talk about EDA again, but for now that is what it is. And then introduce latency based on polling intervals. Like I said, the intervals between these consumer asking producer can be varied, and the latency based polling. So the latency increases according to this polling interval. That is one of the other downside, and there is still mischanges between polls. We have that. Now EDA replaces polling with immediate notification when a state change occurs. So when the state change occurs and event get emitted, the notification will immediately be sent to the system and it will know when to get the data. Event driven reactions instead of periodic checks. So that is nothing but the same point that we already talked about, immediate notification, but this point is just to back that up. Event driven reaction instead of periodic checks. Instead of checking on the new events over and over again, like as in the traditional API, here in EDA, this is event driven. If the event is generated, the new event is generated, the consumer will automatically get notified and it consumes the data. That is how the event-driven reactions work in EDA. So this is one of the other problems. So these are the three problems that EDA solves, but the traditional API lacks with. And then we have when to use EDA and when not to. Use EDA when you need near real-time reactions. It is not real-time. I know it is a stream, but it is near real-time. It cannot, respond immediately. It will respond with a few latency, a little latency like 1 or 2 seconds, but this is for near real-time reaction. Multiple systems require the same data. If multiple systems require the same data, multiple systems which require the same data are considered as consumers, which we already talked about, the fan out, the fan out applications. So this is one of that application. If multiple systems require the same data, which is produced by a producer, and in that case, we can use EDA. There are services must remain independently deployable. So the services should not be dependent on the other system. It just need to be independent to itself. Then we have failures must be isolated and not non-cascading. So if any of those consumer, if anything fails in between these, it should be isolated. It should be to itself and should not be cascade. What cascade means, let's say if one system fails, it should not affect the other system as well. If one system fails, it should be isolated. That means it should be taken care of separately and it should not bother the other systems. That is what this point means. It should be isolated and should not be non-cascading. That is when we can use EDA, whereas in traditional APIs, if one system fails, the failure will just get stacked on top of each other because of its request response architecture. These failures will stack up on each other, and the failure will be massive. And then the system must scale without coordination. One particular subsystem should be independent to each other, which also includes a single entity can be easily scaled without coordination, which means without scaling the other system, without scaling the other subsystems, you can be able to scale one particular subsystem independently. That is what that point means. And that is when we can use EDA. Concrete examples: orders placed, user click, sensor reading, like inventory, order placed includes inventory update, payment processing, email notification, analytics, user click, personalization, logging, monitoring, sensor reading, alerting, storage, dashboards. These are the few examples. When not to use EDA, which include traffic is low and predictable. If the traffic is low, it is not worth it to have all the infrastructure set up for that low traffic. It is not worth it. So it takes a lot of infrastructure. So we have to choose wisely if we want to use EDA. That takes a lot of computational power basically. And there is only a single consumer. If there is only a single consumer, you don't necessarily have to use EDA for that. You have a lot of alternatives where you can make it simpler than EDA. The system is purely CRUD, which includes the system is just about create, read, update, delete. And there is immediate synchronous validation is required. In that case, we can use the traditional API, the request response API, instead of EDA for immediate synchronous validation. So the merit of this traditional API is with the request response, which is real-time processing. But EDA will offer near real-time processing because it doesn't the both producer and the consumer work asynchronously, so they don't offer a real-time processing, but the request response like this, the synchronous systems will offer real-time processing, but they both have their own downsides and upsides. It depends on which situation you're in, and you have to choose one of these two architectures. Concrete non-examples: admin panel CRUD operations, small internal tools, on-off automation scripts. These are the bad examples where you can use EDA, where you should not use EDA. EDA introduces operational and cognitive complexity. If decoupling and scalability are not real requirements, EDA is unnecessary overhead. So if your system doesn't need decoupling or scalability, then EDA is not worth it. Overhead means it is a lot of work to do. And then we have conceptual diagram. First one, so I'm going to draw two conceptual diagrams, one for the traditional API and the other one for the append only log, which is EDA, event style thinking. Let's head to the PPT. Now, let me insert the title first. Say traditional API. With the header. Now shape. I'm going to name this system A. Copy paste it, then call this thing system B. I'm just drawing what I just explained. System, this is how traditional API works, right? A system requests and it receives a response because they both work synchronously. What I'm going to do is I'm going to copy these two again. Paste it here and this should be the other way, like that. So this is how traditional API works. A system sends a HTTP request to, let's say system A sends HTTP request to system B, and it waits until system B responds with the HTTP response and sends that back to system A. But let's say system B is down or running late, or I mean, it is running slow, and system A sends a HTTP request. It gets stuck. The process gets stuck until it gets the response back from the system B. And now let's assume there is another system, system C as well, which sends a request to system B. Now what happens? Because system B is slow or it is failed, this failure effect gets tagged on each other. So now system A is waiting for a response from system B, and also system C will also be waiting for a response from system B. Let me just draw another block just to say. System C. So now both, because of system B, two processes got stuck because the system B is not able to respond with the HTTP response. That is how traditional API works, and that is the downside of traditional API. But I'm not sure how to represent the connection between system C and system B. Should I just you know what, I'll just copy paste this here and draw another line. Like that. That should do. So that is how traditional API works, and that is how the diagram, the conceptual diagram, looks like. Now what I'm going to do is I'm going to take a screenshot of this. All right. Now I will paste that in this document, and when you get this document, you'll have all these conceptual diagrams ready in that document itself. Now I'm going to paste it here. Pictures, screenshots. There you go. Oops. So now what it represents is system A sends a HTTP request to system B. System B waits for a response. If system B is slow or unavailable, system A is blocked. Adding system C means additional calls and more failure points. Now that is how we demonstrate that. And now we have append only log, which will be EDA. Let's draw that as well. I'm going to copy paste this. But for this, we don't need these many diagrams. Just need to just like that. And this diagram, the first block's going to be producer, and then followed by the second block, which will be event. So the producer sends the event. Now this should be, let's say, event log. So the producer sends the event to the event log, and the consumer, which is asynchronous to producer, can get that logs anytime it wants. What we do is we're gonna place these two on top, and then insert an arrow from producer to event log. And I'm going to annotate it as event, representing the producer is sending an event to event log and not the consumer directly. Now what happens is this event will get stored in the event log, and it doesn't care about the consumer. Whenever the consumer likes, the consumer can get the log from that, can get the event from that event log. So I'm going to copy paste this right under here. I'm just separating these two steps to just represent they both work asynchronously, the producer and the consumer. Copy paste the same block right next to that. This is going to be our consumer. Perfect. Now, this is how the append-only log, which is EDA, works. The producer sends the event to the event log, not the consumer directly, and the producer emits the event whenever it wants without caring about the consumer. And this event will be stored for a while. It depends on the retention time inside the event log. And what consumer does is get those events that are produced by the producer, no matter how many events. It just get those events from the event log whenever it wants. This is how the diagram works. Now let's just add it to the document. All right. Okay, now we have two conceptual diagrams. And what it says, producer do not know consumer. Do not know the consumers who, it doesn't care about the consumers. And the consumers do not know the producers as well. They doesn't care. The event is the only contract. The only relation between the producer and the consumers is the event. They just share these events, no matter who, and they don't know whom these events are getting shared to, but they just share them. No orchestration, no callbacks. When I say callbacks, like as in the traditional API, the callbacks, the HTTP response, they don't care about the callbacks at all. They just generate
or emit whenever they want. They just consume whenever they want. Okay, we don't need that line. And then we have key characteristics to internalize. Asynchronous by default. We already know that, but we have to revise these points that we learned from these concepts. So I just created this section. Loosely coupled systems. They're not coupled to each other. They are loosely coupled because they work however they want. And then there is events act as the source of truth. Producers and consumers evolve independently. We already talked about that. They evolve. Basically, they scale or do increase their load however they want, independent to the other systems. Fan out, which will be one-to-many relation. Fan out is inherent, not engineered. This is architecture, not tooling. Now, the final technical takeaway, the short abstract of whatever we learned in this concept includes event-driven architecture is a prerequisite, not an optimization, right? If a system does not benefit from EDA, introducing a streaming platform provides no architectural value. We already talked about the situations where EDA is not necessary to implement because it takes a lot of infrastructure to be initialized. That is what this point says. This point revise. That is it with the concept 1, the concept 0.1. Now let's head to the concept 0.2. Our concept 0.2 is about streaming versus batch processing. We saw the difference between EDA versus traditional APIs before in the previous concept. Now we are going to see the difference between streaming versus batch processing. We have to know about these two concepts before we know about Kafka. That is important. And before going into the actual technical part, I want to ask you something. If you watched my previous masterclass as well, and you watch this, I want you to comment the difference between these two explanational, the structure I'm using to explain in these masterclasses. I implemented something different, the structure in this masterclass by explaining through the material. In the other masterclasses, I just explained it vocally by remembering the points, and I definitely forgot a lot to explain in those masterclasses. And that's why in this masterclass, I just, want to get all the points possible to be explained, and that's why I wrote this whole document, and I'm just following this document so I don't forget any points that are important. So just let me know which explanation is much better for you in your opinion, so that I'll know which to follow for the future masterclasses. With that being said, so the code definition. Data is collected over a period of time, stored, and then processed together as a single unit. This is the definition of batch processing. This is how batch processing work. So the data is collected over a period of time. Let's say, for example, let's say we are collecting the data about orders. So we collect the order data for a period of time. Let's say from 6 a.m., 6 in the morning, and 6 p.m., 6 in the evening. So we collect all the orders data from in this time frame, and then store the data and then process it together as a single unit. We will process this whole data, batch of data, which we collected from between these two timestamps, and then we process it together at once. That is how batch processing works. On the other hand, streaming processing works as data is processed continuously, event by event, as soon as it arrives. This is how streaming processing works. Let's take the same example. Instead of collecting and storing all the data from 6 a.m. to 6 p.m. and then processing it the whole data at once, what we do is right after an event or order, the data about order gets generated or emitted, we just process it on the spot. We don't wait for the next order or something like that. We just process it continuously and we go to the next order. So we process continuously, event by event. That is what this definition says. We go event by event instead of batch by batch of events. This 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 distinction is this distinction is fundamentally about how a system treats time. Batch systems assume delay, streaming systems assume immediacy. Yeah, that is a basic concept between these two systems, right? Batch process assume delay. It causes delay because of the because we just collect the data and then process it at the end. Let's say, for example, the data that we collected from 6 a.m. to 6 p.m. will be processed at 6 p.m. and not. So the data that we collect, let's say an event that is generated at 6:30 a.m. will be processed at after 6 p.m. So that is the delay. So it assumes the delay. And then streaming systems assume immediacy. As soon as the event arrives, it will get processed. If the event arrives at, let's say, 6:30 a.m., it'll be processed in a minute or two right after it arrives. That is how these two systems work. And then we have Apache Kafka exists entirely on streaming side of this boundary. So Kafka exists entirely on streaming sides. Kafka is not for batch processing. Kafka is for streaming systems, not for batch processing systems. And if you think batch processing is not reliable, but that is not true. They both have their own upsides and downsides. We will talk about them as well. Why this distinction exists? Problems it solves. Problem 1, latency requirements. Batch systems are designed to wait. Streaming systems are designed to react. Batch systems designed to wait. They wait until all the data in this desired or defined time frame gets added, and then after the time frame is exceeded, that is when the whole batch of data will be processed, and that is why it is designed to wait, whereas streaming system is designed to react immediately right after the event gets generated. If a decision must happen now, batch processing is structurally incapable meeting that requirement. No amount of optimization fixes a design that assumes delay. First, what is this point? If a decision must happen now, let's say if you want to take a decision right now with the data, with the updated data, batch processing is structurally incapable of meeting that requirement. For example, let's assume now the time is 8 a.m. or 9 a.m. and the batch processing is defined to process all the data in the batch from 6 a.m. like we already talked, 6 a.m. to 6 p.m. So only when 6 p.m. is crossed, that is when this batch of data will be processed. But you want to take a decision with the updated data that happened today at 9 a.m. You cannot do that, right? Because batch processing waits until 6 p.m. to process this whole batch at once. So if you want to take a decision with the data that happened today, you cannot do that. That is the downside. That is the major downside of batch processing. No amount of optimization fixes a design that assumes delay. No matter how you optimize the batch processing, it still has some delay, some sort of delay. Let's say if you want to optimize it, if you want to optimize the time frame or the time bracket for that batch processing, let's say you want to have the time bracket for 4 hours from 6 a.m. to 7, 8, 9, 10 a.m. So still, if you want to take the decision at 9 a.m., you still have to wait until 10 a.m. is passed, and then this batch of data to be processed, and then you get the insights, and then you make the decision. This is how batch processing lacks. And then we have data freshness. Batch systems answer what happened. Streaming systems answer what is happening. That is the same thing. Data freshness. You can get the insights from the freshly arriving data and not wait for the time frame to be passed and then get the already happened insight of that data. There are no implementation differences. There are different system goals with different architectural consequences. So they are implemented almost the same, but the different system, they both solve, they both achieve a different system goals. They both achieve different goals. I mean, like I said already, they both, you might think the streaming is, when there is streaming, nobody have to use batch processing. No, it is not like that. Batch processing have their own applications, and streaming has its own applications. They both, achieves their own goals with different architectural consequences. And then problem 3, cost versus complexity trade-off. Batch systems have simpler architecture, cheaper to operate, easier to reason about. Because batch systems are let me also read out the streaming systems and then I explain. Okay, so the streaming systems always on infrastructure, many moving parts, higher operational responsibility. Yeah, so for the batch systems, the architecture is simpler. You don't have to build a complex architecture to get those real-time insights. Because this is a batch processing system, the architecture is quite simpler compared to the streaming system. And it is cheaper to operate. Because it is a batch system, it is cheaper to operate. The system won't be running 24/7. The processor won't be running 24/7. The processor will be running at the end of the batch. That is when the batch of the data will be processed. So the processor will be running at the end of the batch and not 24/7. Easier to reason about. And then for streaming systems, whereas on the other hand, always on infrastructure. The infra should be turned on 24/7. So the processor, the consumer, the producer, all should be turned on 24/7. They should be working to get these real-time insights, real-time data, to make the data fresh. More moving parts, higher operational responsibilities. If the system is uh, based on batch processing, the responsibility is not that much, because if anything fails in that system, we can fix it within a few minutes or hours, not hours, a few minutes. Whereas in streaming, we have to fix it immediately, or else we might lose the data, because the data gets added, uh, live. So we have to fix it as soon as possible. This trade-off must be understood before introducing a streaming platform. Streaming is not an automatic upgrade, it is a commitment. Now, when to use and when not to use. Use streaming when data arrives continuously. Actions are time sensitive, which means, like we already talked about an example where we want to take an action and it should be taken immediately with the freshly arriving data and not the old data. Then we need streaming because we want the fresh data. And then we have systems must react to events as they occur. So yeah, the system should be active and should react as soon as the event is occurred and not wait until the time frame is exceeded and then react to it. So the system should react to the events as soon as they occur. Delayed insight has real cost. In some situations where delayed insight has real cost, like as in, I'm not sure about the exact example here. Let's say a few scenarios where if the time passed, if the decision, if you don't make a decision before the time passed, it is just a waste of time, or it costs something to you. So it should not be delayed, and that is what it says. Delayed insight has real cost. The decision or insight may delay the time. That is where you cost the money. I mean, you cost something. You may lose something if you make the decision slower. That is one of the use cases when to use. And then concrete use cases. No, concrete use cases. Fraud detection during transaction. Oh, there you go. That is one of the example. Fraud detection during a transaction. This should not be delayed, right? This should not be batch processing. This should not be, you know, detected after a certain time frame is exceeded. This should be detected immediately. That is where we use streaming. Fraud detection during a transaction. If we detect it after the time frame is passed, doesn't make any sense, right? Because that is highly secured. The transaction should be highly secured. That is one of the use case. And then clickstream ingestion, and then application logs and metrics. You have to, the logs should be in real time. They should not be in batches. The log should be real time. It can be any logs, it can be any application logs. The log should be real time, so we can look at the logs and we can make sure everything's working fine in that application. If something goes wrong, we can check the logs, which are real time. We cannot wait until a certain time frame is passed. That they also should be real time, the near real time, or else real time alerts and monitoring. Let's say like bank alerts. When you send money to someone, your bank will send you a notification. Those kind of alerts too, they should be real time. That you have to get those messages or mails immediately. That is a security protocol to be taken care of in that sort of situations as well. That is one of the use case. These workloads are the natural domain of streaming systems. Do not use streaming when data changes infrequently. If the data don't change, let's say like it only changes like once a day or something like that, you don't need streaming. Latency is irrelevant. And then, so latency is irrelevant means basically latency is the delay. Latency is basically means a delay. So if the situation is not related to a delay, it doesn't matter. The delay doesn't matter. That is where you can use batch processing instead of streaming. And then there is processing is periodic by nature. Let's say situations like where you want a dashboard, a weekly dashboard. You don't when if you want to create a weekly dashboard with all the insights, you don't have to use stream for that, right? Because you only create that weekly dashboard after a week. So there will be a week delay for that dashboard to be created. So you can just create a batch processing which adds up all the data within the whole week at once and then process it at the end of the week. Then you can create a dashboard. So creating a weekly dashboard, it doesn't need a real time or streaming for that. Now, concrete non-examples, monthly or quarterly sales report. This is similar to what we just talked about, the weekly dashboard. So if you want a monthly or quarterly sales report, you don't have to process this data in real time, right? You can just batch them up and process it at the end of the month or at the end of the quarter of year. Then we have static reference datasets, which are static. Let's say your data is in a CSV file or .csv file, which is already created. In that cases, you don't need stream. You don't need to stream that data that is stored in the .csv file because that is already static. That is not dynamic. That don't change. In that cases, you can use batch processing. End of the day aggregations. Almost the same example as the weekly reports and the monthly, quarterly reports like here. So this is end of the day. You can just define a 24-hour bracket, the time frame, and then process the whole batch of data at once at the end of the day, and then do the aggregations. Batch systems are not obsolete. They are still the correct choice for those scenarios. Like I said, they're not obsolete. They still fits in some scenarios where they are supposed to be used. So you have to be careful when you use a stream and when you use a batch processing. Stream, because stream takes a lot of computational power, and if you use stream for these scenarios, you're just overwhelming the system or the pricing of your project. And then the conceptual diagram. First, we draw one for the batch timeline, the batch processing, and then one for the streaming timeline. First, let's go with the batch timeline. And I'm gonna take all this down and the arrow to rename it. Now let's draw a timeline. So we draw an arrow representing the timeline. Like that. Is it even? Okay. We have that, and let's name it, annotate it as timeline. So here, timeline. Now we represent the batches here. How should we represent that? Nope. Perfect. Now we split this into batches using this one. Rotate it. Let's split these into 3 batches maybe. Is that enough? Perfect. Now we also call this these are also called as periodic wait times in the timeline. These, let's assume this as the data, this dotted lines as data, right? Let me also annotate that as data. Here maybe. So that is the data, and these are splitted into batches as batch jobs, and we split them into 3 batch jobs. And we call this timeline, this time, to create this batch job, the time frame. We call that as periodic wait times because we define this period of, you know, to create that batch job. We call it a periodic wait time. So this is how batch processing looks like. The data might or might not be continuous, but you can get the data until the time frame is exceeded, until this periodic wait time is exceeded. Now let's draw the, no wait, first we have to take a photo of it. Perfect. What this communicates: processing happens at scheduled points, right? And then data accumulates before any computation starts. First, the data accumulates, they segregates, and then the computation starts. Then the processing starts. Latency is inherent. And then we have streaming timeline. Let's draw that. Copy paste this. And this is pretty simple to draw, not gonna lie. Name it stream processing timeline, and let's take this. It doesn't have periodic wait times. Let's place it at the center and say no schedules. Perfect. Now it doesn't have bad jobs. I'm gonna take these two out, but I'll keep this thing because I'm going to mark this whole thing and say continuous stream. I think that's it. This simple to draw. Okay, so this streaming processing timeline doesn't have any batches because it doesn't work on the batch jobs architecture. It just, the whole data will be stream. It just executes it just process the data right after one single event is emitted. That's how it works, and there are no schedules defined. That's it. This is pretty simple, but yeah. Let's take a screenshot of it. Then go here, paste that. Perfect. We have the conceptual diagram of the batch processing, and then we have streaming processing as well. What this communicates: continuous flow of data. The data won't be in batches, it flows continuously. Near zero wait time. Like I said, it's not it doesn't offer zero, but it is near zero, because it does have some sort of kind of impurities that stop it to be near zero wait time, but it is still the faster. So it is near zero wait time before we process the data, before we get the processed data, the fresh processed data. Now, time is part of the data, not an afterthought. It is part of the data. It is not an afterthought like batch processing. It won't be done after it gets that batch. Do not introduce platforms brokers tooling yet. Okay, I'm going to take this line out. This is not part of the document. Now what we have, characteristics to internalize. Batch optimizes for throughput and simplicity. It is optimized for throughput and simplicity. It is simple. Throughput is nothing but something like, if you know about waves, it is like bandwidth. Throughput is like bandwidth. It depends, it is a factor that measures how fast the data is transmitted. That is what throughput is, basically. So batch optimizes for throughput and simplicity, whereas streaming optimizes for timeliness and reactivity. It reacts right after an event is emitted, and it is timeliness because it is near real time. So there will be near zero latency. Is that what it is? Yeah, near zero wait time, latency. Neither replaces the other. They both have their own applications. Neither of them replaces the other one. The choice is architectural, not technological. It is not about technology we use, it is about architecture. How we design the architecture here depends on the system. It can be a batch or it can be stream. We just change the architecture here. Now we have the final technical takeaway. Batch and streaming solve different time problems. They both solve completely different problems, time problems. Time problems, by the way. Streaming enables immediate reaction, and the time problems. We already talked about the time problems. Each of them solve what batch solve and what streaming solve. So that is how we differentiate between these two systems. They both solve their unique problems, set of problems. Now, streaming enables immediate reaction. We already talked about it. Immediately when the event arrives, the process is done. Then batch enables efficient aggregation. Because it is in batches, it enables efficient aggregation. Aggregation is nothing but combining multiple values into one. Like adding, let's say, for example, like adding multiple numbers. Let's say we have 4 integers, adding them to make it one single integer. So when we add multiple integers, the output will be one integer, right? That is what aggregation is like. Can be anything. It can be subtraction or addition or multiplication. Yeah, anything that makes multiple values into one. That is basically called aggregation, as far as I know. And then Kafka enables streaming, but batch systems remain essential and irreplaceable. We use Kafka is one of the streaming platform that we can use, streaming engine basically we can use, but batch systems remain essential and irreplaceable. They are not replaced by streaming. streaming engine or platform. It depends on the situation or scenario you're at. So it is up to you to decide which system to use. It can be batch or it can be stream. We already talked about those scenarios. So I think you are, you got the concept. You got this concept. That's it. That is the last section of this concept. Now let's head to the next concept, which is basically our next phase as well, which is phase 1. For our next phase, which is phase 1, we're going to talk about installation using Docker, and we also use KRaft while we install Kafka. By the end of this phase, we will install Kafka in our PC. And this phase includes 3 concepts, which are why Docker for Kafka, which I'm going to explain why I'm going to use Docker to install Kafka in my PC. And the next concept, why KRaft and not ZooKeeper. I'm going to talk about that as well. Then the third concept, Kafka installation with Docker plus KRaft. That is the concept where we actually install Kafka. Talking about our first concept, why Docker for Kafka. By the way, there are a lot of ways to install Kafka in our PC. Using Docker to install Kafka is one of the most reliable thing to use, in my opinion. And it is also most used way to install Kafka, by the way. Instead of installing Kafka directly into our root PC, it is better to install Kafka in a container in Docker, and we'll know why it is better. Okay. Now, the definition. Docker is a containerization platform that packages Apache Kafka and all its dependencies into isolated, reproducible runtime units called containers. What does that line means? Firstly, Docker is a containerization platform. Everything it creates will be a container that packages Apache Kafka. We're going to package Apache Kafka into a container. All its dependencies, Apache Kafka and all its dependencies into isolated container. What does that mean? Let's say you install Kafka into your local PC directly without using Docker. And if you want to get rid of it or you want to manage it, they're all spread all over your PC. You cannot manage them. If you want to delete or uninstall, it is hard. Or even if you want to manage them, let's say for any other task, it is still harder to manage that tool or whatever you installed. But when we use Docker to install this same tool, what Docker does is Docker creates a separate container that is not actually related to our PC. So all these files, the main application, which is Kafka, and the dependencies, which are the dependency files that comes with Kafka and that Kafka is created, Kafka creates at runtime. All these files will be taken out when we want just by removing the container. So if we remove the container, all the dependencies and the application will be taken out with the container itself. You don't have to do that again. So managing these installation and the dependencies is a lot easier when we use Docker than just doing that or installing that directly onto our PC. Docker is nothing but it is like a container. It is like the dockyard, the shipyard with a lot of containers, and each container is separate from the other containers. So, and the container includes everything that represents or that belongs to one particular tool. And here we're going to create a container separately for Kafka. That is what we're going to do here. And this is the most used way of installation, even in production, real project production. And that is why we are going to use this way of installation. Next step, in Kafka setups, Docker guarantees Kafka runs the same way everywhere. This is also one of the important thing to remember. If we install Kafka in our PC and run a process, it might run in our PC, but it will fail or it may fail in a different PC because of the PC's OS or any other thing. But when we run Kafka inside Docker container, and if you want to replicate the same environment into same setup into a different environment or different PC, you can just replicate it so easily as it is, and it works the same way that it is working in your Docker container. So that is one of the aspects that we have to remember when we use Docker. So that is one of the advantage that we get. No dependency pollution on the host operating system. We already talked about it. Now dependencies will be saved in our host machine. If anything, everything is in a container, and if we remove the container or if we dismantle the container, everything goes away with the container. Nothing stays. Fast setup, tear down, and reset cycles. It is faster to set up, tear down, dismantle easily. We can dismantle it easily. Reset cycles. Docker is not a shortcut or a beginner convenience. It is the baseline for professional Kafka environments. Like we already talked, Docker is the most used platform or most used way to install Kafka, even in production grade projects. Next section, why Docker exists for Kafka. Now, the problems it solves. Problem 1, dependency hell. Kafka depends on Java, a compatible JVM, Java virtual machine version, correct networking configuration, OS level tuning, and ports. So Kafka depends on all of these aspects, all of these partitions, basically. Traditional local installs lead to Java version mismatches. That is what I said. If you install Kafka in your local PC, it might work correctly. And when it is installed in a different PC, it might not work the same way it worked in your PC. So if you want to replicate an environment or a setup into a different PC or environment, you can just use that tool in a containerized way using Docker, and then you can easily replicate it. Path and environment variable conflicts. Broken Kafka installs after OS updates. All this use cases, no, all these advantages. Docker solves this by packaging Kafka, Java, configs together in one container, like I said, fully isolating Kafka from the host operating system. So this is not connected to the host machine. This is separate. This is isolated environment, which is a container in Docker. Eliminating host level dependency conflicts. We already talked about it. It's the same thing. And then we have non-reproducible environments. Without Docker, it works on my machine, becomes the default failure mode. Like I said, it works on my machine. It might not work on another machine because of the environment mismatches. But whereas in Docker, we can replicate the exact environment, which is the Docker container, into another PC. None of these problems will exist if we do that. Works on my machine but not work on your machine. No problem like that. And each developer runs Kafka differently. Bugs cannot be reproduced across machines or teams. That is one of the things that we cannot achieve if there is no Docker exist. Bugs cannot be reproduced across machines or teams. Docker guarantees the same Kafka version. So the Docker, if you install the Kafka in one of the Docker container, you can just install the same Kafka version in a different container on a different PC, different Docker container in different PC. The same configuration, you can configure the same configuration in different Docker container in a different PC too. The same runtime behavior every time, no matter where you run it, no matter which PC you run it. If you run it in the Docker container with the same configurations, the runtime behavior will be exactly the same in any PC, any environment. Reproducibility is not a convenience, it is mandatory for distributed systems. When we work with distributed systems, this is mandatory. Cleanup and reset pane. Local Kafka installs leave files, ports, background services behind, break future installations, require manual cleanup that is error prone. Like I said, if we uninstall Kafka, it might still need manual cleanups. It might break installations in future. So all these problems when we install Kafka in our local PC. And that is why local Kafka installs are not recommended. Now about Docker provides. Docker provides one command tear down. You can run the container with one command and tear it down with one command too. And we will talk about that commands as well. We will use it in the third concept of the same phase. So we can, Docker offers one command tear down and one command clean reset. Zero residue on the host system. Nothing. Residue means like the remaining. I don't know how to explain it. The basic term of residue. What is the basic term of residue? Residue is a small particles that are remain at the bottom level of, let's say, a container of water. If you mix, I don't know how to explain it. Yeah. So if you mix okay, if you have a glass of water and mix something like a sand or something into that water, that sand stays at the bottom, right? When you pour all the water out, still the sand stuck at the bottom of the glass. That is what basically called a residue. So what it means here is even when you uninstall all the setup, there will still be a residue if you install Kafka in your local PC, whereas in Docker, no residue at all. Nothing will stay. Everything will be wiped off cleanly if you tear down the container and reset it. That's it. If something breaks, you delete the container and start fresh, and no archaeology required. If something went wrong, and if you want to reset the whole container or delete and rebuild the container, you can just do that so easily with, like I said, with one command. That's enough, and you can just rebuild another container. You don't need to uninstall it and reinstall all the tools that you working with. You can just tear down the container and generate a new container again. It is so simple with just one or two commands. When to use Docker and when not to use Docker. Use Docker when learning Kafka, which we are doing now, building demos or tutorials, developing locally, local development, running CI/CDs, continuous integration, continuous delivery pipelines. Concrete examples: proof of concept, developer laptops, Local testing before deploying to cloud or production. Even in cloud or production, we still use Docker. We still install Docker in that virtual machines in the production as well. So for these scenarios, Docker is not negotiable. Okay, do not rely on Docker alone when running large-scale productions. You do not rely on Docker itself. When in production, it is so easy to rely on Docker because it is so easier to create a container and destroy a container. But in production, you have to be careful with those. Running large-scale production, you don't just rely on Docker. Needing fine-grained OS level tuning, managing hardware aware performance optimization. In production, Docker is usually paired with orchestration. Docker alone will not be used. Docker is paired with orchestration with the rest of the tools or replaced by managed Kafka services. But for learning, development, and testing, Docker alone is the standard way to go. Conceptual walkthrough. Kafka is not installed on the host system. Yes, we're not going to install Kafka on our host system. Kafka exists entirely inside the Docker container, entirely inside. So if the container goes away, Kafka goes away. No residue at all. Isolated from the OS. It is not connected to the local system's OS. It is connected to Docker and the container alone. One command setup, one command tear down. With just one command, we can set that up, set the environment up, and with just one command, we can tear that down. We can dismantle it. Removing the container removes Kafka completely. We talked about it. No residue. If you remove it, removes it completely. The host operating system remains clean and unchanged. Nothing happens to our host system. No files or nothing will be saved. No extra files will be saved in our host system. Everything will be removed if you remove that container. If the container is deleted, Kafka is gone. Yep. No leftover files, no background services, no broken environment. You might already face these kind of issues before when you install an application and uninstall it. There will still be a few background applications running even after you uninstall the main application, and you don't know how to get rid of those background processes. But when you do install that application in a container, there will not be any background services, no leftover files as well, no broken environment, nothing changes because the whole container is isolated from the local host machine. I mean, Docker is a pretty big concept, the topic. I may have to create a masterclass for Docker alone. I will do it. But for now, these are the basics you have to know when you install Kafka on Docker. Industry context to internalize. Docker is the default runtime for modern development workflows. Talked about it before already. Docker is the default runtime for modern development workflows. It is the most used tool in the production grade as well. CI/CD pipelines depend on containerized environments. Kafka setups without Docker indicate outdated practices. So if you set up Kafka without Docker, it is like you're not updated enough for the modern data engineering world. So you have to be so familiar with using the Docker for not just Kafka, for any other data engineering tools as well. So yeah, this is not a trend. This is a settled industry reality. Final technical takeaway, the abstract at the end. Docker is not optional tooling. It is the professional baseline for running Kafka reliably, reproducibly, and cleanly across learning, development, and testing environments. This is the whole idea for this whole concept. in just 2 lines. With that, we're done with our first concept of the phase 1. Well, this doesn't have a conceptual diagram because this is just a concept we have to know. We cannot picturize it with a diagram, and we don't have a lab 2 because installation will not be done here. It will be done at topic 1.3, concept 1.3, not topic. Okay. Now heading to our next concept, which is 1.2. Now heading to our next concept, which is why KRaft and not ZooKeeper. First, let's go for the definition first. KRaft stands for Kafka Raft, by the way, is the native metadata management and consensus system built directly into Apache Kafka, eliminating the need of Apache ZooKeeper. Have to tell you about this topic before we go further. So there used to be something called ZooKeeper in which has to be installed with Kafka. So Kafka, we install Kafka and also ZooKeeper, but we need ZooKeeper to run Kafka because ZooKeeper manages the metadata and also the coordination. It has some responsibilities given. So without ZooKeeper, Apache Kafka cannot be run in old days, not now though, but before KRaft even got introduced, there used to be ZooKeeper in the legacy machines. You can still find this ZooKeeper tool. And even in our project, I did use ZooKeeper in a lot of my projects when I used Kafka. Yes, there used to be ZooKeeper, and ZooKeeper is used to manage the metadata of Kafka and also the coordination between the tools that Kafka uses. I'm going to dive deep into it later, but now that is the basic concept, ZooKeeper. But in later times, I think KRaft came into picture on 2021, I think. And what KRaft did is, instead of installing a separate tool like ZooKeeper, KRaft took that necessary out. It is not necessary to install another tool like ZooKeeper. What KRaft does is KRaft will be the native metadata management and consensus system. So it also manages the tasks that ZooKeeper does, like metadata management and the coordination. And KRaft will be a native metadata management tool inside Apache Kafka itself, so you don't have to install another separate tool like ZooKeeper. So it takes away the purpose of ZooKeeper and keeps it native to Kafka itself. With KRaft, Kafka manages its own metadata. You don't depend on ZooKeeper now. Consensus is handled internally using Raft protocol, and ZooKeeper is no longer required. That's what I said. So we don't use ZooKeeper at all if we use KRaft. This is not optional or experimental. ZooKeeper-based Kafka is deprecated. KRaft is the present and future of Kafka. Why KRaft exists and problems it solves. Problem 1, Kafka plus ZooKeeper was over-engineered. Instead of just having one tool, configuring one tool, we have to configure 2 tools. The legacy architecture required, which is when I say legacy, I'm representing the ZooKeeper plus Kafka architecture here. So the legacy architecture required a Kafka cluster. We need one Kafka cluster separately and another separate ZooKeeper cluster as well to manage the metadata and the coordination of that Kafka cluster. So we need a separate cluster for ZooKeeper as well. 2 distributed systems to deploy, operate, and debug. That is the problem. And this resulted in high operational complexity. It is so complex to configure it because there are two separate clusters that had to be configured, more failure modes, and difficult root cause analysis during incidents. So if there is something happened, something went wrong, we have to uh, debug that error, right? But because we have two clusters or uh, two tools installed, we have to know which tool is causing this error, and that might be difficult to find that root cause. KRaft fixes this by removing ZooKeeper entirely, collapsing the control plane into Kafka itself, nothing else. So just one tool, which is Kafka, turning Kafka into a self-contained system without depending on another tool like ZooKeeper. Problem 2. ZooKeeper became a scalability bottleneck. ZooKeeper limitations in large Kafka deployments, poor scalability for high partition counts. It, it becomes a bottleneck. Bottlenecks means something like that holds back the capability of Kafka. So that is what we call bottleneck here. And then slow metadata updates, topic creations, leader changes. Because it is a separate isolated, it runs in a separate isolated container or separately, this metadata updates will be slow. But whereas in KRaft, it is all internally optimized, so it is a lot faster than using ZooKeeper. Fragile behavior during network partitions or failures. We already talked about how fragile goes into this technical environment. Fragile is nothing but breaking the system. So breaking fragile behavior, the viability of breaking during network partitions or failures. As Kafka clusters grew, ZooKeeper struggled to keep up. If we scale the Kafka cluster, ZooKeeper might find hard to keep up with that scalability. Metadata operations become painful and risky. KRaft provides better scalability characteristics, faster metadata changes because it is nothing but optimizing the Kafka system internally instead of creating an external tool like ZooKeeper. So this is faster for metadata changes, predictable behavior during failures because it's just one tool, it is predictable. Problem 3. Split brain operational mode. With ZooKeeper, Kafka brokers handled data. ZooKeeper held the metadata source of truth. So before you actually understand this phrase completely, you have to know about brokers, but we will talk about brokers later. For now, you just understand this. So Kafka has brokers. Brokers are nothing but entities of computation. Like let's say this PC, if I run Kafka in this PC, this will be one of my broker, and if there is another PC or virtual machine, that is another broker. So this is the broker. Kafka brokers handle data. So they handle the data, but ZooKeeper held the metadata, the source of truth. ZooKeeper has the metadata of this broker. This split caused confusing ownership boundaries, complex recovery scenarios, painful upgrades, and version compatibility because they run on two different basically containers. So this is hard to say the owners to determine the ownership boundaries and complex recovery scenarios. KRaft fixes this by making Kafka fully self-managed, assigning clear ownership of metadata to Kafka itself. So the ownership of metadata will not be handled to another external tool like ZooKeeper. It is handled by Kafka itself, eliminating cross-system coordination complexity because it is all managed in one single system. There is no cross-system uh, coordination complexity. One system owns everything. That is the basic line we have to say. When to use and when not to use KRaft. Use KRaft when running Kafka today. Learning Kafka. Building new clusters from scratch. Today, by the way. Concrete example, local Docker based Kafka cluster, new production deployments, cloud native Kafka setups. KRaft is the default choice for all modern Kafka usage. Do not use ZooKeeper when starting a new Kafka setup. Designing modern Kafka architectures. But you still have to know about ZooKeeper because you just have to know how ZooKeeper works because there are a lot of systems still out there in companies where they still use ZooKeeper because they created the whole environment a lot before when lot way ahead before this KRaft got introduced. So they still run on ZooKeeper. So you have to know about ZooKeeper as well. You have to have an idea of ZooKeeper. So they have to update to KRaft as well because ZooKeeper has a lot of downsides. ZooKeeper-based Kafka exists only for legacy clusters. When I say legacy clusters, they are the old clusters that are created way before KRaft got introduced. Migration scenarios during upgrades. Yeah, migrating the whole setup from the old legacy clusters to the new modern legacy clusters use KRaft. The same thing that I just said. ZooKeeper is not a design option anymore, it is technical depth. Concept diagram. The first diagram will be about the legacy architecture and the next one will be the KRaft architecture. Let's head to that. Let's create a new slide. Let me duplicate this. Take the whole thing down. First one will be the legacy architecture. That first, let me copy this box. So we have 3 brokers. Can't use the arrow here. We just need a regular line. That. What I'm trying to do here is, we already talked about Kafka cluster and the broker, right? So a Kafka cluster can have multiple brokers together. So in this case, I'm showing, let's say we have 3 brokers, which will be Kafka broker 1, broker 2, broker 3. And the metadata will be metadata and the coordination. When I say coordination, ZooKeeper is not just used to store the metadata, it is also used to manage the coordination actions, like assigning a controller privilege to a broker. I will talk more about the controller privilege and all the stuff, but I'm going to talk what is necessary for now. Okay. Yeah, I think this is pretty much good for the legacy architecture. Now, this Kafka cluster is depending on an external tool, which is ZooKeeper. ZooKeeper, and it uses ZooKeeper to manage the metadata and also the coordination. When I say coordination, when we have multiple brokers, Kafka needs to uh, make one of those brokers as controllers, which is much like a main broker out of the others, just like, let's say, like a leader and a follower. But we cannot use those terms because we're going to use these leader and follower terms again. So I'm not going to say leader and follower. Controller is like the one, like the admin of the rest of the brokers. It is like the main broker, so it acts like the main broker. So in the ZooKeeper decides which of these broker should be a controller. Whereas in KRaft, it doesn't depend on ZooKeeper. It has a different mechanism where we send all these brokers into the controller quorum, and that inside the Kafka itself, it decides which broker can be a controller. And there can be multiple controllers, by the way. There can be multiple controllers. One controller should be active, and the rest of the controllers which are eligible to be controllers will be on a standby mode. So when the active controller goes down, or some sort of failure happens to the active controller, one of these standby controllers will be assigned as an active controller. That's how it manages, because you don't want to lose the data, or you don't want to lose the flow, because you want to maintain this as a stream, and you don't want to break the stream. So you have multiple containers, multiple brokers, and we have these controllers as well. Controllers concept, we will know more about the controllers concept later, but for now, yeah, ZooKeeper will also manage that as well. Decides which broker can get the controller access. Controller, no, I don't say access, it is like a role, more like a role. Now legacy architecture is over. Now let's talk about, first let me take a screenshot of it. Okay, so this is the conceptual diagram of legacy architecture for Kafka plus ZooKeeper, with ZooKeeper. So this is pretty complex and fragile. It can break, it has more probability to break Then now let's talk about KRaft architecture. This will be the KRaft architecture. Let me just talking about the KRaft. We don't need these lines for now. Let's draw a data line first. An arrow. Yep, that looks straight. So this will be our data pane. Data pane. Now we connect these brokers to the data pane. It doesn't have ZooKeeper, by the way, so we take that out. Kafka broker 1, broker 2, broker 3. These should be connected. This will be a typical KRaft setup. Doesn't have any ZooKeeper, just the brokers inside the Kafka cluster, and the controller. There will be, like I said, there will be a few controllers, but only one broker can be an active controller, and the rest will be the standby controller. If a broker is eligible to be a controller, then it gets a controller role. Let's say this first one is a controller. And this will be active controller. Perfect. And this is not a controller at all. We leave it as it is. Now here, this will be a standby controller, just like a backup. So if this active controller, if something goes wrong with this active controller and it doesn't work, then this standby controller will act as an active controller then. So this is standby. Perfect. Like I said, we will talk more about these concepts, the controller, active, standby, later. But for now, this is how KRaft architecture looks like. Doesn't have a ZooKeeper. Everything, even the controller assignment and everything, metadata, controller assignment, all this stuff will be managed inside Kafka itself without ZooKeeper. Let's take a screenshot of this. Head back. Nope. Perfect. Now we have a conceptual diagram for legacy and one for KRaft architecture as well. Now the key points, older Kafka versions refuse to start without ZooKeeper. If the version, like I said, if you're working for a company and the company has a older version of Kafka already implemented in their setup, their infrastructure, you cannot just change the whole thing at once, right? So you have to be habituate or you have to adapt to that, and that's why you also have to know ZooKeeper, and you should not avoid ZooKeeper. You also have to know ZooKeeper because there might be a chance you will work in an environment where there is ZooKeeper still implemented. Then KRaft based Kafka starts independently. Like I said, doesn't need any external service like ZooKeeper. Metadata now lives inside Kafka managed logs, not in ZooKeeper. If ZooKeeper dies, legacy Kafka stops functioning because it handles the metadata and the coordination. So it of course stops. If the ZooKeeper goes down, Kafka will also go down. If a controller fails in KRaft, Kafka recovers internally. Okay. Like I said, the decision to make a broker a controller is made by ZooKeeper in the legacy architecture. That is what our architecture says. In the legacy architecture, ZooKeeper makes the decision to make a broker into a controller. Whereas in KRaft Kafka does it internally. It doesn't depend on ZooKeeper at all because it uses KRaft. Kafka evolution context. Kafka originally relied on ZooKeeper for coordination. We all know that. KRaft was introduced to remove that dependency. The primary reason to introduce KRaft is to remove the dependency on an external service like ZooKeeper. That is why KRaft is introduced. ZooKeeper is now deprecated for Kafka usage. Kafka's roadmap is clear and irreversible now. Final technical takeaway. ZooKeeper is legacy baggage for Kafka, the old systems. KRaft represents Kafka maturing into a simpler, faster, and fully self-managed system. Modern Kafka means KRaft. Anything else is transitional. This is the whole point of this concept. KRaft is a modern way. It is simpler, it is faster, and it is fully self-managed when compared to the legacy systems where we use ZooKeeper along with Kafka. That is it. That is it. With that last section, we are completed with this concept, which is 1.2, why KRaft and not ZooKeeper. Now let's head to the next concept, which is 1.3. Walking into the next concept, 1.3, which is Kafka installation with Docker plus KRaft. The code definition. This setup installs Apache Kafka in KRaft or Kafka Raft mode using Docker. Running Kafka as a self-managed broker and controller without ZooKeeper. This is the whole concept of us installing it. Sorry, there's something on the camera. Okay. That is what we're going to do in this concept. We're going to install Kafka in KRaft mode. Key characteristics: single node Kafka cluster. Single node, which means there are no any extra tools other than Kafka. KRaft enabled, so no ZooKeeper, obvious. Broker and controller roles in one process, of course. Fully containerized runtime. This is the modern baseline Kafka installation for learning and local development. Why this installation approach exists, problems it solves. Legacy installations teach the wrong Kafka. Instead of saying wrong Kafka, we might say expired Kafka instead. Older Kafka tutorials depend on ZooKeeper. So they have all these tutorials with ZooKeeper included in them. So which also includes how these controllers are assigned to the brokers by the ZooKeeper. So all these tutorials are based on how Kafka is also dependent on ZooKeeper as well. Use deprecated configuration patterns. Teach mental models Kafka no longer uses. So Kafka is no longer dependent on ZooKeeper, like I already talked. So instead of learning Kafka with ZooKeeper, it is always best to learn Kafka with the modern way to use Kafka, which is KRaft mode. This approach ensures you learn Kafka as it exists today. No unlearning or migration confusion later. Alignment with Kafka's forward roadmap. Manual installations hide Kafka internals. Traditional local installations abstract away startup behavior, hide lifecycle logs, mask configuration mistakes. Docker plus KRaft does the opposite, forces explicit configuration. So instead of masking all the configurations using the manual installations, Docker plus KRaft does the opposite, forces explicit configuration. We configure how we want the Kafka should be installed. Instead of installing it without configuring it, we can configure it. When we use Docker to install Kafka, we can configure how Kafka should be installed in our PC. And we will know how we can configure while we do the lab. Exposes every startup phase, makes failure visible and unavoidable. When you use Docker, you can see the failures. If something went wrong in the installation, you can see the logs and find the failures. So you don't mask them up. For learning distributed systems, visibility matters more than convenience. Well, it is easier to just install Kafka into your local PC directly, but it is not about convenience. It is about learning distributed systems and visibility, and also managing the resources or dependencies after installation as well. All these aspects, Docker is the best way to go instead of just installing Kafka into a local PC. Now, problem 3, ambiguous Kafka roles. Many learners struggle to understand what a broker actually does, what a controller is responsible for. We will talk about these concepts, but I just gave a brief introduction already to you in the last concept. How leadership and coordination work. We will talk about that as well. Leadership is about partitions. There is a concept which we talk about partitions and then we talk about leadership and stuff like that. KRaft makes roles explicit, broker and controller. This setup forces clarity instead of hiding complexity. Now, when to use and when not to use. Use this setup when learning Kafka fundamentals, running local demos, building proof of concepts. concrete example: developer laptops, continuous integration pipelines, local experimentation for all this. Even in production, you can use Docker alone when you are the application or the setup is at developer stage. This setup is intentionally simple and transparent. Do not use this exact setup when running multi-node production clusters, because in this setup we are going to also install Docker desktop with the UI, so we can actually see the logs on the UI itself. But whereas in production, you will not get chance to actually see the logs using the UI, because you will be working with, let's say, the virtual machines, the cloud, the virtual machines that run on cloud, and the only way for you to communicate to those virtual machines is through the CLI command line interface. You won't have this interface. You don't have this user interface to communicate with that virtual machine, right? So that is why, that is one of the reason uh, you don't use Docker desktop or this exact setup in production. Then what? Requiring high availability, operating at scale. They're all basically same. Production environments require multi-nodes, of course, separate controller quorum, proper networking and security. So you have to keep that in mind. Conceptually, however, the architecture remains the same. The architecture will be the same, but the nodes differ, and the rest of this basically the orchestration differs. That's it. But the architecture will be the same. Now, heading to the next section, which is the lab Kafka installation with Docker Compose, KRaft mode. This lab is intentionally minimal and explicit. So now in this lab, we are going to install Kafka using Docker. Now, the first step, you have to install Docker desktop on your PC. Again, like I said, because this is just for learning, or even when you work for a company, or when you work for an enterprise, you can still work on Docker desktop, because using Docker desktop UI is lot easier, but only in developer stage. But when you push that setup into a production stage, that should be different, because like I said, you cannot use UI on the virtual machine, because the only way you can communicate to virtual machine is using CLI. So you have to remember that. But for now, because we are just learning it, this is still the best way to go with. Install Docker desktop from the official site. Verify installation Docker version. Now we install Docker desktop. You can go to any web browser and search for Docker desktop, download. Click on the first link. Hover on this button, download Docker desktop, and you'll see which OS this Docker desktop should be installed at. And you have to choose your appropriate OS. Mine will be the AMD one, but I'm not going to download this because I already installed it on my PC. You just need to hit on this, and there you go, the download starts. Now you click on that file and install it with all the default settings. You don't have to change any settings. You just need to go with the default settings and install it. For now, I'm going to stop it because I already have that on my PC. Cancelled. Okay, I will also provide the Docker desktop download link for you. You can just download from that link, or else you can just navigate through these web pages to get that download link by yourself. Okay, let me close these two. After you install it, when you open Docker Desktop, if you're opening Docker Desktop for the first time on your PC, it might ask you for sign up, but you can still skip the sign up process. In my case, I did skip the sign up process. It still asked me to sign up. That is totally fine. You can skip it and you'll land on this page. And this is the home page, and here's where we can find the containers that we created. All right. So first step is done. This doesn't need to be done anyway. You must see both client and server output. Okay. So the first step will be install Logger Desktop from official site. And step 2 will be create a working directory where we can work. So I'm going to do that. Like I said, in the production environment, we're not going to use the UI for any of these processes. So now I'm going to use CLI for even creating those directories. If you never use CLI, the reason why we use CLI is to have more control over the tasks that we perform. Let's say here, like as in here, if you want to create a folder named Kafka Lab, like this, what you usually do, you go to File Manager, and then you navigate through all the paths and choose the path you want to create that folder in, like this, right? And here you right click and click on new and folder, and these when you're using Microsoft, I mean Windows, you do this. It is different for Mac OS, but whereas in CLI, it makes it more simpler and also more controllable. You can do tasks faster and you can control everything that you're doing. And also, this is what you use when you interact with a virtual machine in the production grade, or you know, with interacting with a cloud virtual machine. This is what you see. This is how you create folders, create files, or run tasks, install tools, run tools, everything from CLI itself. So it is better to habituate or adapt to the CLI instead of ignoring it totally. So instead of you doing this, I already showed you the example, right? Instead of doing this to create a folder, what we do is, by default, it is at C drive, users, and username. What I'm going to do is, here I'm going to create a folder just by this line. You see how easier and faster that is, and also you have more control on the task that you do. It has everything that displays. Now, what it does is it creates a folder in the desired path, and the defined the path here is we are inside the C drive users and the username. So if you navigate through your file manager to that path, which is this, you can actually find the file named Kafka Lab, which is the folder that we just created, right? And if you want to create another folder, let's say for example, if you want to create another folder inside Kafka Lab, you can go inside that folder and create one folder. To go inside the folder, we use cd Kafka Lab. So Firstly, we used mkdir to create a folder and cd to change directory. CD stands for change directory. Now we are changing the root directory, the directory that we are in here, from the username to Kafka lab. So now we're here. Now whatever the task that we perform here will be reflected inside this folder because we are inside here. So if I create something like that, creates a folder here inside the Kafka lab directory. That is how it works. But right now I don't need this. Yeah, but that's how it works. Well, this is just an example, but it is always better to work with CLI instead of using UI for all the tasks that we do. Just we just need to adapt to this CLI interface. Okay, we've done this step 2, by the way. Now heading to step 3, which will be create docker compose.yml, which means we have to create a new file named docker compose.yml with this code inside up to here. I'm gonna enclose that, the whole code, in the double quotes, so we differentiate between the regular text and the code. Okay. Now I will be using uh, Visual Studio Code Editor to actually write the code and run that. Just to write the code and create the files and stuff, because that makes it more uh, convenient for me to explain the code and the stuff while I write. But this is completely optional. It is not mandatory this tool. But I'm going to show you how we can install it. The same way, we have to search for VS Code Editor. I think you can also find this tool inside Microsoft Store as well. And yes, you can just download it. And I will also give the link for VS Studio as well down below in the description, so you can just click on that link and download it if you actually want to use it. If you don't want to use it, that is still fine. It just makes it a lot easier when we code. And by the way, this is also not a good production grade practice to do, but this is good for the development stage when we create the system first in the developer stage. But in production, we cannot use any of this. We only use CLI. So this is the Visual Studio Code Editor. Let me just take these down. Let me show you by deleting this folder first. I want to show you the default page, how it looks like. Okay, so this is when you click on the Explorer on the top left here, this is what you see. You see open folder and clone repository and nothing connected to the Code Studio. Visual Studio Code Editor. I spelled it wrong. I pronounced it wrong. From here, you click on open folder and connect the folder to the VS Code Editor, and then work on your files and codes from here. To do that, let me create the folder again. Okay, Kafka Lab. Now click on Open Folder. Select the folder that we created, the project folder, basically. Now, here, whatever we do here will be reflected to that actual folder, and also we can create files here. These also easier, but not a good practice for production grade, like I said. It is good for development and testing and learning. Now, here, let's create a file named to initialize or define a container in Docker. We write a code which we configure an image for that container and the configurations as well with the environment variables through code, through a .yml file, through a code, and then we run that code in the Docker and we create the containers. That's how it goes in Docker. Now we have docker compose.yml file created, but for the code, what I'd say is, if we copy and paste this exact code in that file, I'm sure there will at least be one error that gets triggered, because any code that we write cannot be copied from a Word document, because Word document has a lot of hidden uh, structures that we cannot see with our eyes, but if we copy that, the code will not work the same way. So what you have to do is, I already have this code saved in a different file. I'm going to open that file and copy paste it in this file. And for you, don't you worry. Every code that I write and every code that I use, every file that I use in this masterclass will be given to you through a GitHub repository link, and you can download them, all the files from that repository. It is that simple for you as well. For now, let me just get that file right here. I need up to this first. Paste it here. Now, talking about this code, first, the image, which includes the image of the tool that we are installing in the container, which is Apache Kafka, and we say latest to pick the latest version of Kafka available in the market. And then container name, this can be anything, but we say Kafka here. This is the displayed name on the container when it is created. This can be anything. This it is not supposed to be Kafka. It can be anything, but Kafka is the best to represent that container name. Now the ports. Before we talk about these ports, we have to talk about the rest of the configurations first. So we do that. All right. By the way, we don't need this. We don't need that, by the way. I tried to do something, but I thought it is not related to the masterclass, so I took it out. So I don't need that line. Okay, now we have environment. So these are the environment variables that I'm going to define now. First, Kafka node ID 1. Like I said, there can be multiple nodes, multiple brokers, not just this PC. There can be multiple machines working for the same Kafka cluster. So they need to have unique IDs to be identified, right? Now for this cluster, I'm naming it with ID as 1. And then we have Kafka process rules, broker and controller, Kafka controller, quorum, authors. Like I said, we are not going to use ZooKeeper here. So Kafka decides which broker is eligible to be a controller. So using controller quorum, and here we are saying this is the sorry. Okay. So we're just passing this broker as a into the controller quorum, and the algorithm decides which broker can be the controller. Now Kafka listeners, these are the ports that we define for the Kafka listeners, which includes 0.0.0.9092 plain text, and the external port is 29029. This is not supposed to be, I mean, these not particularly need to be plain text here. This can be anything that you write. We're just calling those ports. We're just naming, or they act like the port, uh, names basically. This is the actual port. Then there is controller. This is for the controller port, which is 9093. And there is advertised Kafka listeners, which includes 909 Kafka 9092, which will be an internal listener, and the external listener is host.docker.internal 29092. There are a few things you have to remember when you talk about or when you define a port here. So this is an internal port, like I said. So if we get into the Kafka container, we can talk to Kafka through this port, Kafka. Should I say, is that a colon? Yeah, Kafka colon 9092. You can use this port to connect to talk to Kafka if you're inside the Kafka container. But if you want to connect from outside the Kafka container, but the same machine where the Kafka container is running, let's say this PC, you can use this port, host.docker.internal 29092. That works fine because the host here will be your local PC. So it can identify using that port. It can be easily identified. But if you want to connect to the Kafka cluster from an other laptop, you have to expose here, you have to expose with your actual computer's public IP address here. But I cannot do that because of obvious security reasons. I cannot expose my public IP address on this video, so I use this. So if you want to expose your Kafka cluster or IP address, the port, so you can access it from a different laptop as too. You can use the public IP address for that in this place and use that as external port. But for now we don't need to do that. I'm not going to use a different laptop to connect. This PC is fine. So I used host.docker.internal here. Next, controller configuration. Kafka controller listener names, controller, Kafka inner broker listener name, plain text. Like I said, we're calling these ports using the names that we defined before. So here we're calling the controller port, which is this, with the name controller. And with the plain text, we're calling this. And we say inner broker listener. Like I said, this is the internal listener, and the other port, which is this, is the external listener. Kafka offset topic replication factor. You have to define this when you are using KRaft mode, but in ZooKeeper, you don't have to, but we are using KRaft mode to install Kafka on Docker. So we have to define these three configurations as well. Kafka offset topic replication. So since we are just replicating all the concepts just once, we are not using multiple PCs. All these values will be 1 anyway for Kafka offset topic replication factor, Kafka transaction state log replication factor, Kafka transaction state log min ISR. ISR stands for in state replication. No, I think it is in state replication ISR stands for, but yeah, I'm not sure about that. We will come across the topic. Kafka listener security protocol map. And then Kafka log directory, these where the Kafka logs will be stored. All the metadata and the logs. Okay, that is it. Now, when I run this, a container for Kafka will be created in Docker, and through which we can actually perform tasks through that Kafka cluster. Let's save this. And to run it, like I said, we use CLI to run it. But instead of using a PowerShell or a command prompt, let's use the CLI that comes with Docker Desktop. This executes the same way that PowerShell executes, but instead of using a separate terminal, it is better to use a terminal that comes with the application itself. That reduces the load, right? That is more efficient. So I'm going to close PowerShell and run it here. Right now, we are at the username directory, but we have to go to our project directory, which is Kafka-lab. To do that, we use CD, which stands for change directory. Did I told you what mkdir stands for? That is make directory. This is change directory. So we are changing directory to Kafka lab, which will be our root repository. There you go. And here is where docker compose.yml file is also stored. Now we can access it. To run it, when we talked about Docker Kafka installation, we talked about one command to set up and one command to destroy, right? Now I'm going to show you what that particular line means. We're just going to run one line command, and that creates the Kafka container. And that line will be sorry, what? Docker compose up means start the containers. Docker compose down means destroy the containers. And these -d represents anything that is like that is in that format with a hyphen before an alphabet. It is used to represent a flag. So this is a flag, -d is a flag, and that flag used to detach the process from the command prompt. I mean, from the terminal. If you run that Docker compose up without the -d, it still sticks to the terminal, and you cannot use the terminal. To make it more clear, I'm going to run it without -d at the end first. Okay, like that. Enter. Now this creates Kafka container, like I said. Here we can see the actual container that is created. To see the logs, to check on the logs, you can click on this container, or you can actually see that the logs in the terminal itself, because we haven't detached it from the container, from the terminal. We can actually see the logs right here. Or else we can click on the container which we created, this one. There you go. We can see the logs. So if something goes wrong, the error will be defined clearly in plain English right here in the logs. Or if you can't find the error, just copy paste the whole logs here and ask ChatGPT with your code that you used or any language model out there, and you can find the fix for that error. For now, yeah. So this is one of the mode. But if you take a close look here, now I ran that command, but now I cannot run another command because this terminal is connected to that. So to run a different command, I have to open a new terminal, and here I have to take those containers down. Okay. Now this will be disconnected because the containers are down. But when we use that -d flag, which is detach, the terminal is not polluted now. When I say that, you can still use the same terminal. You don't have to change it because it is detached. The terminal is detached from the Kafka logs. So you don't have to worry about that. You can still use this terminal. That is how this flag works. And this flag -v, when you down the containers, we use verbose to clear all the the files that came with that container. It is like clearing it out in the right way. It clears everything out when we use -v. That is stands for verbose, verbose. Okay, now we know at which part we are at, which step. We copy pasted that, and we ran the Docker Compose up. Now this is fine. In the step 5, observe startup logs. We will come to this part, by the way. There is one more part we have to talk about, which is UI. We will talk about it at the end of this lab. But for now, let me talk about this one. To check it, use Docker PS. So this should list all the containers with the container ID and the image that the container is using and the status. Here the container ID and the image, which is Apache Kafka latest, created about a minute ago. Status should be up. That is how you confirm the container is up and running. And it also exposes the ports that you defined. Observe startup logs. You must explicitly observe and understand the logs. What to look at: KRaft metadata formatting, controller quorum initialization, broker registration completing successfully, no ZooKeeper connection attempts. If you check on the logs, you will not find any ZooKeeper connections in those logs, which makes it clear that we haven't used ZooKeeper in this. If we use ZooKeeper, even in the Docker desktop, there will be a separate container created right next to Kafka that says ZooKeeper in the old versions, in the old setups. Even in my projects, I use ZooKeeper. So in all of my projects, when I use Kafka, you see a container for Kafka and a container for ZooKeeper as well, which manages the metadata and the coordination. But here, because we are using KRaft, we don't see any other containers other than Kafka. You see? So this is a folder name, by the way. This is a container. Don't confuse. This is not a container itself. This is the compose stack. See, this are the listed containers. There is only one container right now, which is Kafka. Okay. clear with that. Now, let's talk about the UI. We don't use UI, like I said again, we don't use a UI at all in production, but in development or mainly when you are learning Kafka, it is better to have a UI handy so you can see all your process reflected on the UI and you can make sure those process that you're doing is actually working by just looking at the UI. Talking about the UIs, there are a lot of UIs available out there, but now we are going to use the Kafka UI, the real one, which is the most used UI. But in my old versions, I also used KRaft. I think I only used KRaft in my other projects, but there is Kafka UI as well that we can use. I'm going to use Kafka UI for this. So to use Kafka UI, we also have to create another container with a different port just for the Kafka UI so that we can use it. And this is a compose file. But like I said, we cannot copy the codes directly from the Word document. We just need to copy paste it. So I already copied the main Kafka container code. Now I'm going to copy the Kafka UI container code. Paste it in our code, just this. Right there. Now save it. Now head back to Docker desktop, down all the containers, and recreate that. After saving this, by the way, you have to save the file first. Now create them again. -d, which is detach. Now we see two containers created, one for the actual Kafka and the other one for Kafka UI. To make sure the UI is actually working, you can go to the http // localhost 8080, which is this port by yourself, or you can just click here on the UI, click on the ports 8080. So you can go to this address, http://localhost :8080. You can go to that port, or you can just click on here and it redirects automatically to that port. Click on that. Now in any of your web browser, you maybe basically in your default web browser on your PC, this will open up. This is the Kafka UI. And this is the main dashboard. We have local Kafka here, which we connected. When we initialize the UI in our code, so what we did here is we, of course, defined the image, which will Provectus Labs. Basically, this Kafka UI name is Provectus Labs, by the way. Kafka UI latest. This is the provider of the UI, by the way. And container name will be Kafka UI. This is the display name on the container, which is this. So this is the display name. Depends on Kafka. Now this container is depends on Kafka, and that cluster bootstrap server is 9092, which is a listener in our actual Kafka cluster 9092. We're connecting UI with the actual Kafka using the listener port. Kafka is to 9092. And because this is inside the container, we can use the internal listener Kafka is to 9092, and it still manages to connect to the Kafka. Okay, that is how we created it. If we take a good look at the UI, these are the dashboards. dashboard that, like we said, and these are the clusters that are active. Right now, we only have one Kafka cluster that is active. Okay, and here we can see the brokers that are available. We only have one broker. If we create another container with another cluster Kafka broker and then connect that to this will change to two brokers. The broker ID will be, there will be two brokers here listed, then broker count will be 2. We can see the topics in this section. Let me zoom it in. I think now you can see that clearly. If you click on consumers, you can see the consumers that we created, the consumers, the consumer groups. So the consumer groups can be visible here in this section. Right now, let's close that UI. And yes, that is how we installed Kafka with the UI using the .yml code in Docker as containers. Heading back. We're done with the lab now. Oh, here. There is a section I created to explain the ports as well. Listener port, which is 9092 client listener. This listener is used by producers, consumers, Kafka Connect, Kafka streams, admin clients. Is this the right explanation about that? Now here, that is not what we used. This is what we used, 29092. In our case, this is what we used. We used 9092 for the internal listener. This is the external listener, which listens to producers and consumers. Well, 9092 will also listen, but just with the task, if the task or the producer is inside the container. That looks good. Kafka Connect, Kafka streams, admin clients. So all of those, these connectors can connect using 29092 port that we exposed as advertised listener, which is our external port, which is this. This is our external port. Then we have 9093 for controller quorum listener for KRaft. This listener is used only by controllers talking to each other, just for the controllers. We created a dedicated port just for the controllers to talk to each other. What flows here? Raft heartbeats, controller elections, metadata replication, cluster state updates. When I say controller elections, it happens and the algorithm manages the controller election. It takes all the brokers that are eligible to be a controller, and with the it 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 actually conducts a controller election with the algorithm, and it chooses a controller by itself. We don't choose the controller, the algorithm chooses on its own. So that's how controller election works. We use that port for all the controller processes that is dedicated for that. And we use this for the external services to connect. That is it. Kafka setup lifecycle to internalize, Kafka setup lifecycle to internalize. Configuration loading, KRaft metadata initialization. Controller election, we already talked about these things. Broker registration. Kafka ready to accept client connections. A clean startup is mandatory. If Kafka doesn't start cleanly, stop immediately and fix the configuration. Ignoring Kafka warnings is how unstable cluster and production outrages are created. So you have to make sure, before going to the next concept, you have to make sure the Kafka installed in the right way and it is working. It is working correctly. You can make sure about that by using the command that I told you, the docker, which is docker ls. And also by the UI, by looking at these dots, this solid green dots means it is running. If it is not running, there will be no green dots here. It's just a shallow circles there in that place. By using command, I already told you, we use docker ps, this command, to make sure it is up and running. You run that command. With that, we're done with our last section for this concept, which is Kafka installation, which is also our last concept for the phase 1 installation Docker. By the end of this phase, we installed Kafka using Docker in our PC in KRaft mode, like I said. So that is done. Now let's head to the next concept, which will be our next phase as well, which is phase 2. Okay, now walking into our next phase, which is phase 2. In this phase, we are going to talk about Kafka's core concepts. This phase is going to be quite longer than the other phases that we are going to go through, which will, where this phase will have like 9 concepts, 9 of them. And the rest of the phases, there are like how many? There are 4 more phases, but all those 4 have 3 concepts or 4 concepts maximum. But this phase has 9 concepts. This is going to be a pretty big phase. Okay, the first concept we're going to talk about here will be what is Apache Kafka, and the next one will be Kafka versus traditional message queues, and topics. What a topic, we'll know what are topics about, and we also will know what partitions are, and what offsets are, what producers are, what consumers are, what consumer groups are, and the other internal components that Kafka core has. Now, our first concept, which is what is Apache Kafka. Apache Kafka is a distributed, fault-tolerant event streaming platform that accepts events from producers, persists those events durably as an ordered append-only log, allow multiple consumers to read the same event independently at their own pace. We already talked about it when we talked about EDA, event-driven architecture, in the first concept or first phase, right? The phase 0, the same thing, because Apache Kafka belongs to that architecture, event-driven architecture. It is quite similar. So the definition says, Apache Kafka is a distributed, so it distributes, is a distributor, so it distributes between multiple machines. It can be distributed. Fault tolerant, if there is a fault that can be recoverable. So fault tolerant. If it is not fault tolerant, that machine might break if there is any fault occurred. But this is fault tolerant, which means if a fault occurs, it can get over it. That is what it means. Fault tolerant event streaming platform that accepts events from producers. Event streaming platform, it is a streaming platform that accepts events from producers. So it gets the events that producers emits, so it accepts events from producers, persists those events durably as an ordered append only log. Persist, so it stores those events that are produced by the producers in a log like structure, and these events are ordered according to the time it got produced. So it stores first in the event log, because it want to make it asynchronous. The producer and consumer should be asynchronous. So the producer saves those events in the event logs first, and then these events from the event log can be consumed by the consumer or multiple consumers, allows multiple consumers to read the same events independently at their own pace. So the consumer speed doesn't matter. When consumer's gonna get those events or consume those events doesn't matter. Nothing matters. Consumer can get the events whenever the consumer wants, in whatever the speed the consumer working on, doesn't matter at all. It allows multiple consumers to read. That is how Kafka works. Now, Kafka combines messaging, durable storage, and streaming delivery into single system. It has messaging. You can share messages from producers to consumers or throughout the consumers, and durable storage. So it stores the logs, and according to, and it is defined, and how long these logs will be stored depends on how we configure the retention time. We will talk about retention time as well, but for now, that is not the core topic here. So we're going to talk about durable storage. So it does stores the events in the log format, like we already talked, and streaming delivery. It is a streaming delivery. It streams the data. It is not just a message broker, and it is not just storage. It is both by design. The same point, said in a different way. That's it. Why Kafka exists? Problems it solves. Kafka exists because earlier systems failed to handle scale, durability, and fan out at the same time. We are here we're talking about the traditional request response systems here. We already talked about that when we talked about EDA, right? Event driven architecture. So these systems, to overcome that, EDA architecture was created, and this Kafka is part of that EDA architecture. Kafka follows EDA architecture. So the Kafka exists because earlier system failed to handle scale, durability, and fan out, whereas Kafka can handle scaling, independent scaling, to be particular, independent scaling. The producer, consumers, or the storage can be independently scaled without caring about anything else. Durability, it is durable, and the fan out, one to many relation, one producer or one data to many consumers. Problem one, it solves messaging systems without persistence. Traditional messaging systems delete messages after consumption. This is one of the points we have to talk about too. Often no reply capability, provide weak recovery guarantees. So traditional messaging system, once the message is consumed by the consumer, the message is deleted permanently. It is often no replay. Replay is nothing but, let's say, if the consumer wants to, if a consumer consumed all the data once, and if he wants to consume the data again from the beginning, which is nothing but, in other words we can call it replay. So if that consumer want to replay, so if you want to consume the same data from the beginning again, he cannot do that in the traditional messaging system, because the events are gone once they are consumed. So provide weak recovery guarantees. So if the consumer breaks and consumer lost the data, consumer cannot get that data again from the producer. Yeah, you get it, right? That is what it says, weak recovery guarantees. Whereas on the other hand, Kafka solves this by treating messages as stored events. It stores those messages in the event logs, retaining them for configurable duration. The term configurable duration means we configure the duration, the retention time. These events will be stored in the log, allowing consumers to replay data at will. So even if the consumer consumes the data out of that log, the data will not be deleted. it will still be there. So multiple consumers can still get the same chunk of event, and that is why it allows fan out and it allows replay. So even after the consumer consumes all the data in that log, he can go back to the beginning and consume the data again, consume the events again. And that offers the recovery. If the consumer goes down, consumer lost the data, it can get the data again from the beginning before the retention time expires, the configured retention time, the retention time which defines how long those events will be stored in the log. Before that time, the consumer can recover those data from the log. That is how Kafka's mechanism works, the architecture works. Consumption does not destroy data. The same thing, consumption. If the data is consumed, it is not deleted. Problem 2, storage systems without real-time delivery. Databases and data lakes. Store data reliably, do not push changes in real time, or optimized for queries, not event flows. So we're not comparing now the traditional APIs to Kafka. Here we're comparing the databases or data lakes with Kafka here. The storage systems, we're comparing the storage systems. Because Kafka also offers storage, now we compare the storage systems with Kafka. Where databases and data lakes store the data reliably, for sure, but they do not push changes in real time, right? Like Kafka does, and are optimized for queries and not for event flow. They are not optimized for event flows. They're just optimized for queries because they are databases. Whereas Kafka solves this by using append-only writes, enabling continuous sequential reads, turning stored data into live event stream. So this like combining a traditional API stream with a database, a storage unit like a database. It stores the data and it also streams the data. So it can store the data whenever the consumer crashes. It can recover the data from the log because it is also a storage unit. That's how Kafka works. Okay, we got that now. Yeah, like I said, append only means it is like combining the let's say the latest record will be added at the end of the events. If there are, let's say, event 1, event 2, event 3, event 4 that is coming in will be we cannot use merge, will be combined at the end, will be sticked at the end of the log. So that is what append means. If you already, I mean, most of you guys know what is append means, right? So I don't have to again, elaborate it, I guess. Yeah, that is. So it uses append only writes. It combines the latest latest incoming events at the end of the log. So the Kafka bridges the gap between the storage and the real-time movement, which we already talked. Problem 3, one producer, many consumers. With APIs and point-to-point systems, producer must explicitly fan out data. Each new consumer increases producer's load because of their mechanism. The consumers send the HTTP request and they need to receive the response from the producer because they are running synchronously. That increases a load on the producer, right? And the producer, if the producer capacity is low, that producer becomes a bottleneck, which will be, in other words, say a barrier or the barrier that pulls that producer, the process down, makes the process slow, basically. Kafka solves this by writing data once, letting many consumers read the same data independently, decoupling producer throughput from consumer count because they both are the producer and the consumer run synchronously. They are not coupled to each other, so they are decoupled. That's why fanout is a native property, not custom logic. Now, when to use and when not to use Kafka. Use Kafka when event volume is high, data must be durable. So event volume must be high. The volume of the events, the incoming events must be high. The data must be durable. If you want the data to be durable, to stay longer, you use Kafka. Multiple systems need the same events. You have multiple consumers which need the same data. Kafka is the way to go. Replay and reprocessing are required. If you want to replay the whole all the events that you already consumed back again, you can use that because you can replay all the events again. Now, the concrete use cases: application logs, matrix pipelines, CDC, change data capture. If you don't know what CDC is, CDC is a method where we can capture every change in the state of a data. So that is what called change data capture. We mostly see this in a database where the state of the data gets changed. It can be inserting a record into the database, or deleting a record, or dropping a table, or creating a table, anything like that. Everything comes under change data capture. So we capture every particular movement that happens in that database using CDC. That is what change data capture means. We use that concept CDC in one of our projects, and that project is banking modern data stack. You can check that project out if you want to know more about CDC. We use CDC concept there. In that project, we also used Kafka along with Debezium. Debezium is used to capture the changed data, use the CDC. So we used Kafka plus Debezium in that project. You can check that out. You can find that project in the modern data stack projects playlist. Okay, now moving on. Event driven microservices. Kafka excels when events are valuable beyond their first consumption. Even after the consumption is done by a consumer, still, if the event is valuable, Kafka is the way to go. Do not use Kafka when you need immediate request response semantics. Like I said, Kafka is near real time, but not real time. If you want no delay at all, if you want zero delay, you can go to the request response semantics where you have no delay at all. So yeah, that is one of the case when you don't want to use Kafka. You need simple task execution. If it is a simple task, you don't need to set up the whole infrastructure because it is a lot to deal with. If it is simple, don't go with it. Event volume is very low. Even if the events are not that many which are produced, don't go with the Kafka. Infrastructure overhead cannot be justified. Concrete non-example. CRUD APIs. CRUD stands for create, read, update, delete. CRUD. CRUD APIs. Background job queues. Simple notification systems. Because it is simple, you don't have to do that. Kafka is infrastructure, not a lightweight utility. It is a whole infrastructure is not a lightweight utility. You cannot do that with one step. So to make your work worth to set the whole infrastructure up, you have to be careful where you're using it. Now, talking about the conceptual diagram. So back to the PPT. create a duplicate slide for this, name it. I'm gonna just name it Kafka. It doesn't matter anyway. Just going to copy paste it in that document. But I will also give you this presentation as well, just in case if you want it. I don't think you want this because all these uh, conceptual diagrams are already added to that document, which I'm going to give you, the Word document, so the study material basically. So you don't need this, but I will still provide this document as well. Okay, take these things down. We just need one. So big. This is just a simple diagram. Nothing changes, right? It is basically the same as append only log. But just the names will change because this is a representation of Kafka cluster. Kafka cluster. Producer Kafka cluster. And the producer and the consumer are connected separately to the Kafka cluster. I'm going to insert shape, arrow. Oh, that is crooked. There you go. Now let me copy this. The producer sends the data to Kafka cluster, and the Kafka cluster acts as a storage log to store all the events, right? Now, from this Kafka cluster, consumer will consume the data whenever the consumer wants. So that's why we are separating them as two diagrams to just represent they both are separate, they are not synchronous. That should be plural, right? It can be multiple producers and multiple consumers. So I said plural here. Copy paste this. Then connect it. Send, consume, or receive. Consume will do. This will be the storage. So it stores the data in the Kafka cluster. Then it will be consumed whenever the consumer wants by the consumers. Get a little bit closer like that. Now let's take a screenshot. Add it to the document. I feel like it is a lot easier to use Lucid charts to create these diagrams than PowerPoint, but at the same time, I also want all those diagrams to be saved as, the slides or something. But Lucid Chart needs a premium subscription to save these, the the diagrams. And I cannot save. There is no way I can save all these diagrams at one place in Lucid Chart. That we need premium subscription. That's why I'm using PPT here. In case if you're wondering, but creating these diagrams in Lucid Chart is a lot easier. Now, use case 1 logs. Application emits logs as events. Kafka stores them durably for a while. Multiple systems consume independently. The consumers doesn't depend on the other consumer. They just independently consume the data whenever they want. Monitoring, alerting, long-term storage. Yep. Use case 2. Services emit metrics continuously. Kafka observes traffic spikes. Downstream systems process data at their own speed. They can process the data at their own speeds. They don't need to be aligned with the producer speed like the traditional API. They can process the data in their own speed, and the producer can emit the data on its own speed. They don't need to be synchronous. The same points repeated again and again just to make it stuck in your mind. That's it. Just because this is a material, this is a study material, these main points are, a few of the main points are repeated again and again. Kafka acts as a shock absorber between producer and consumer. By that sentence, it means it acts like a barrier, so the producer can work on its own speed and consumer can work on its own speed. So this is a shock absorber in the middle, Kafka, so they won't get collided and slow something down. If consumer slows, the producer should not get slowed. Because Kafka is here acting as a shock absorber, producer will not get slowed because of consumer. That's how it works. Now, CDC, change data capture. Database changes are emitted as events. Kafka becomes change stream. Like I said, I already implemented this concept in one of our projects that is in this channel. You can check that out. Kafka becomes the change stream, so it streams the changes that happened in the database. Consumers build caches, analytics, read replicas. Key point to state explicitly. Kafka does not process data here. It moves and stores events. So, key points. Key point. Yeah, the Kafka does not process the data. The consumer who's getting the data is the one responsible to process the data. Kafka just moves the data and stores the events. Kafka just moves and stores the events. That is what the responsibility of Kafka. And processing is the responsibility of consumer, and emitting is the responsibility of the producer. What Kafka is not. Kafka is a distributed event streaming platform. We already talked. A durable ordered log. Talked about it. Durability, it stores the data for a while, and ordered, it stores the data in order. Ordered log. A fan out, one to many. We talked about it. Kafka is not a request response system, which is a traditional API. No. A task queue. It is not a task queue. A database, not a database. It stores data, but not a database. It stores events, not data. It stores events, but not a database. Confusing these leads to broken designs. You have to make sure you are clear with these points. Now, the final takeaway of this concept. Kafka is distributed append only log that many systems can read from. The final takeaway. Treating Kafka like a traditional queue leads to incorrect assumptions, poor designs, and fragile systems. So treat Kafka in the right way. That is it about this concept. Now we head to the next concept, which is 2.2. Our next concept will be concept 2.2, which is Kafka versus traditional message queues. This one, okay. And this includes a traditional message queues deliver a message to a consumer and then delete it after consumption. We already talked about how traditional APIs work. It delivers a message and then deletes the message that is delivered to the consumer. So it is only allowed to be consumed once, and after it gets deleted. So that is traditional message queues. Apache Kafka, in contrast, stores events as durable append-only logs, allowing multiple consumers to read the same data, consumers to replay events later. The difference is not implementation detail, it is about data lifecycle and ownership. We already talked about these things before when we in the previous concept. So I'm not going to go deep into that. We go why this distribution exists, problems it solves. Problem one: fan out without sorry, fan out without duplication. In traditional queues, one message, one consumer. One message can only be consumed by one consumer. It cannot be fanned out to multiple consumers. So if one consumer consumes one message, the message will be deleted. It will not be there to be consumed by the other consumer. That is one of the problem. Fan out requires duplicating messages or adding routing logic. So because the message gets deleted right after a consumer consumes a message, the only way to implement fan out in a traditional architecture is to have is to create duplicates of the same message. You know, let's say if the event is, what should I do? Let me create a duplicate slide and just delete everything. So I'm going to use this as a whiteboard now. Okay, now, yeah. Fan out requires duplicate messages or adding routing logic. Let's say if you have a message that says, oh, that is terrible. That's fine. So that says order received. So if there is a message that says order received, the event, okay, if you want to fan this event out to multiple consumers, what you have to do is you have to create this order record multiple times. You have to duplicate these records multiple times. You know what? Let me erase this whole thing. I don't need that. You can just do that by shapes itself. Oh, that is why. Okay. Okay, let's say if there is an event saying order received, I'm so bad at spelling things. I'm not sure if it is the right spelling. No, it is not. Whatever. Okay. Let's say if there is an event saying order received. So in order to fan out this message in the traditional API, the only way to do that is duplicating this message multiple times in the producer side. So you duplicate it depending on how many consumers you want this message to get consumed by. So if there is 3 consumers, you duplicate the same message 3 times. That is how you make the fan out work with the traditional API. Whereas in Kafka, one event, many consumers. Fan out is native and effortless. You don't have to duplicate the message. You can just have one copy of that message, and still that will not be deleted when the consumer consumes a message. So that message still be read by multiple consumers. Let me delete that in the slide too. I don't want that slide. Perfect. Kafka is designed for the same data feeding many systems simultaneously. The same thing. It is talking about the fan out here with that point. Problem 2, replay and recovery. We talked about this already, but I think I just explained these topics way ahead of the concepts we are going through. So these are all already explained before. Okay, queues. Now, replay and recoveries. Queues operate on a delete on read model. Yeah, traditional queues. So it operates on delete on read model like we already talked. Once consumed, data is gone. No replay, no recovery if the consumer needs to recover without external backups. Kafka operates on retention. We talked about retention already. Retention is the way where we define how long a log stores the events in that. Events remain for a configured retention period. It depends on our configuration with the retention. Consumers track offsets, positions, not message ownerships. We haven't reached the offsets topic yet, but it is something like a checkpoint for consumers to check till if there are multiple events in that cluster, they use offsets to check until when they consume the messages. So they are like checkpoints for consumers basically. We will talk about offsets later, but for now that is the basic concept of offset. So consumers track offsets, not message ownerships. This enables reprocessing. It can backfills. The term backfill has a unique meaning about it. I already explained this topic backfill in Apache Airflow Masterclass. It is almost same. So backfill is like, let's say there are 4 events. Let me show you with an example. Okay, take these things out. So there are 4 events. Event 1, event 4. 4 events. Right now, your offset, which will be a checkpoint, like I said. So right now, you are maybe here. So your offset is here, your checkpoint is here. So the consumer read the data up to event 3. But the consumer want to read the data again from event 2. So what it does is we configure that consumer again, and so it backfills. It is nothing but it is similar to recovering the data. So it just goes back to the configured position, the configured previous position, and read the data again. That is what meant by backfill. So it goes back and fills that data again. So if we configure it to go to event 1 again, so it goes here, erase this, so it goes there again, and then starts reading these data again, 2, 3, 4 again. So it just backfills. That's how it works. Okay, that is done now. Delete the whole slide again. We don't need it. That is how backfills work. Consumer recovery after crashes. We talked about it. If the consumer crashes, it can recover the data again from the log, the Kafka cluster log. Debugging using historical data. To get the historical data. Decouple consumption speed. Problem 3. Queues enforce a processing pace. Slow consumers block throughput. Like I said, queues enforces processing pace. The consumer and the producer works on the same pace. Even if producer has the capability to go far ahead of consumer, producer cannot go because they are prohibited to be in the same pace. That's why slow consumers block throughput. If the consumer is slow, the throughput will be blocked. Like as I already talked about throughput, right? The throughput is defines how fast the data transfer is. Consumers drain messages permanently. Kafka allows consumers to read fast or slow. Depends the speed of the consumer and the producer is independent of the other systems. Pause and resume. It can pause. Producer or consumer can pause at any time and resume at their own times. And that won't break the system at all or slows down the system at all. Rewind and replay. We know about that. This separation of storage from computation speed is impossible in delete on read systems, which are the traditional API. It deletes on read. When to use and when not to use Kafka. We talked about it, but that's fine. Use Kafka when multiple downstream systems need the same events. We talked. Events represent facts, not tasks. Replay and historical processing are required. The correct examples: order events consumed by billing, analytics, and fraud systems, database change streams, logs, and matrix pipelines. Kafka excels when data has long term value. Do not use Kafka when each message must be processed exactly once by only one worker. This is new. I mean, do not point is new. You are distributing tasks, not recording events. If you're distributing tasks and not events, you have to go Apache Airflow, not Apache Kafka, because Airflow is the one that distributes the task. Yeah. Concrete non-examples: background job execution, email sending pipelines, image or video processing workers. Conceptual diagram now. One for traditional queues and one for Kafka style log. Okay, let's go to the PPT again. Duplicate this slide. First, for traditional queue. Traditional queue. What we do is we take all these things down. We're gonna copy this and we assign this block for queue. We see how we just represent how traditional queues work with this diagram. So say queue, and queue has the messages or events, right? Say events. This should be at the bottom of the box like that. Just increase it a little bit. Now inside I'm gonna draw a few more shapes representing the events. And for the color, let's go to white with the black border. black. Good. Event A, copy, copy paste it. Three events in the queue. How about event A, event B, event C. So this queue has three events now. Now I'm going to copy this box. Paste it here. And this will represent consumer. Now copy these two and go down a little bit. And here I'm going to say insert shape, align like that. Perfect. And copy paste one more like that. This event will be consumed by the consumer. Okay, that is perfect. Now what I'm representing here is perfect. So this represents how the mechanism works. Once the message is consumed by the consumer, here I'm representing the message, a queue with messages, three messages, A, B, C, three events basically. And once the event A is consumed by the consumer, which is this, so it is still in process here. Once it is consumed, the event will be gone forever. And the only place that event stays is at consumer side. It won't be in the queue. It will be permanently deleted. So that is what I'm trying to represent here. Now let's take a screenshot. Perfect. And paste it in under the conceptual diagram. Perfect. What this communicates: one-time delivery, no replay. It does communicate one-time delivery, no replay, ownership transfer. So the ownership of this event that is consumed, the event A, the ownership is now transferred from queues to the consumer. Now queues doesn't have any ownership for that event. That is what the line ownership transfer means. Now we talk about Kafka style log. Head back. We use something similar, so I'm going to duplicate this slide. Was that Kafka style log? To delete these whole boxes, all the boxes except these two. We need the consumer box and this one too. What I'm going to do here is I'm going to use two consumers. So two consumers like that. And name them consumer A and consumer B. Then I use a shape where, let's say, consumer A is now consuming the event A. Let's say it is consumed. Okay. And consumer B is consuming consume B. The event B. Now what I'm going to represent is, I'm going to copy, paste this right next to here, next to that, right here, and show the consumer A now consumes B and consumer B now consumes C. But still, after the consumption, those events will still be in the, not the queue. Kafka topic. Kafka topic is nothing but like it acts like a folder in our PC basically. We will know more about the topic. I think that is the next concept that we're going to learn about. But for now, that acts like a folder to distinguish between different variety of data that we get. So we just use topics as folders to save these events. Let's say this is Kafka topic. No. Perfect. Now let's say B is consumed by consumer A, and C is consumed by consumer B. But still, those consumed events are still saved inside the topic even after consumption. That is what this diagram represents, the concept. Now let's take a screenshot of this. I think this is perfect. To make it more clear, I'm going to add one more thing here. I'm here. I'm going to name this thing say consumer A offset to make it clear. Offset is a checkpoint, right? and this one as consumer B offset. Same thing for this. This one too. Perfect. Now that looks perfect. Now let's take a screenshot. Okay, that is a pretty big screenshot. Now we use that. Drop it here. Perfect. We got it. Now what this communicates? Independent consumption. So consumer A and consumer B are independent in the diagram. Replay capability, shared history. Perfect. Now conceptual replay walkthrough. This is a thought experiment to lock in the model. Event sequence, E1, E2, E3, E4, consumer behavior, consumer consumes. Okay, so this is like a conceptual replay walkthrough. What we just learned, just for a replay, for the replay. Let's assume we have four events: event 1, event 2, event 3, event 4, ordered in this sequence: 1, 2, 3, 4. Okay. And consumer behavior, consumer processes event 1 and event 2. So now consumer processed event 1 and event 2. Now the offset is pointing at event 3. Now consumer crashes. All right. On restart, consumer resumes from offset E3. E1 and E2 still exist in Kafka because it does have offset on E3, because offset is checkpoint, like I said. So it starts from E3 again, not from the beginning. No, it starts from E3. So it starts from the point where it stopped, where it crashed, and not from the beginning because of the offset. Critical clarification: Kafka does not track who consumed the message. Kafka tracks where the consumer is in the log. So it tracks a checkpoint, not who consumed the message, which consumer consumed which event. It doesn't track that. It tracks the consumers, where the consumer is in the log. It tracks the offset, not just the offsets. Queues cannot do this because the data no longer exists after consumption. Technology positioning. These are the few examples for tasks for these traditional APIs, which includes RabbitMQ is an example for task and message queue. Amazon SQS, which is a classic example for managed queue service. Apache Kafka is a distributed event log. Now we are talking about distributed event log, which is Apache Kafka. These systems solve different problems. None replace the other. They all solve their different problems. They have their own applications. That doesn't mean they can replace another tool. All these tools have their own applications. Final technical takeaway: Kafka stores events as histories, not jobs to be executed. Right? Treating Kafka like a traditional queue leads to incorrect assumption, broken replay logic, and fragile system design. So we should not deal. We should not treat it like a traditional queue. We have to know about Kafka and how the mechanism of Kafka works, or else we can break the whole pipeline design. That is it with this concept, which is 2.2. Now let's head to the next concept, which is 2.3. Like I said, we're going to know about topics. Now, our next topic, which is 2.3, sorry, not our next topic, next concept, because the concept name itself is topics. So our next concept is about topics. A topic in Apache Kafka is a named append-only stream of events. So we name a set of events and we call that as topic. Like I said, the topics acts like a folder in our local PC or disk. So we use these topics to separate certain type of data. If you want to save, let's say, if you want to save users, if you're working to a company and if you want to save user data separately and the sales data separately, you can create one topic for users and the other topic for sales. That's how you divide the data. That's how the topic works here. Key properties: events are written in order. Events are not deleted on read. Just like we talked before, events are written in order. Append only. We talked about that as well. Topics are shareable by multiple consumers. So one topic can be shared across multiple consumers with no problem. A topic defines the data contract in Kafka. A topic is the unit of organization, ownership, and governance in Kafka, not a transient pipe. So it is a unit of organization to organize the data. We use that to organize the data too, so we can separate those data types like we already talked. Not data types, data categories. We can separate them, segregate them according to the data category and the ownership and the governance. For a solid example, if you know about SQL, you know how these schemas work, right? The same way, here we use topics to separate them. Why topic exists? Data separation, the first problem it solves. Without topics, all events flow into a single stream, no matter what the data category is. If it is about personal information of a customer, goes to the same data stream. If it is the sales information, goes to the same data stream, event stream. So we don't want that. Consumers must filter aggressively. If all these different categorical data is in the same event stream, when the consumers get this data, consumers have to filter them, right? And it increases the load on the consumers. To reduce that, we can segregate them before we actually store the data in the Kafka cluster, so those particular consumers can connect to those topics according to the data category they want and then get the data out. Data boundaries become implicit and fragile. Topics solve this by logically grouping related events. The events that belong to the same category, they group them. Creating explicit, enforceable data boundaries, and then making intent visible at the architecture level. Okay, now problem 2, ownership and governance. Topics enable clear producer ownership, clear consumer expectations, independent configurations per data stream. For the first point, so it clears out the producer ownership. Instead of the producer having the ownership of all all categories of events, we can sort that ownership to only one particular category by the topic, by giving ownership to that topic and nothing else. So we can do that. Clear consumer expectations. When consumer is trying to consume a data, by topic we can make sure the consumer gets that particular category of data because we segregated this data already by categories. Now, independent configuration per data stream. We can configure independently throughout across the different data streams, however we would like to configure. Now, without topics, no one owns the data, right? Retention and access policies become impossible to manage because when we create a topic, we can configure the retention time or period according to the topic, and we can change the retention time across the topics. One topic can have a different retention time or other configurations, and the other topic have another retention time and other configurations to it. So we can retention and access policies become impossible to manage. We cannot manage them without topics throughout the data categories. Kafka degrades into one ungoverned pipe. Without topic, it degrades into one ungoverned pipe because all the data is stuffed into one data stream. It becomes an ungoverned pipe, right? Problem 3, scaling and lifecycle control. Kafka manages data per topic, including retention policies, partition strategies. We will know about partitions more in the next topic. Yeah, in the next topic. Kafka manages data per topic, including retention policies, partition strategy, access control, ACLs, access control lists. Topics are structured primitives, not optional labels. So we can control the access as well according to the topic we are working with. Retention, we talked about that. Partition strategy, we will talk about that in the next concept. When to use and when not to use topics. Use topic when event belongs to distinct business domains. Like I already gave an example, right? The orders or the personal information. Multiple systems depend on the same event type. Data lifecycle must be managed independently. We use topics, so because to manage the lifecycle independently, we can configure that according to the topic, independent to the data category. According to the data category. Now, concrete example: orders, payments, user activity, inventory updates. These four cannot be in the one single data stream. That confuse the consumer. So we can split the orders in one single topic, payments in one topic, and user activity in one topic, inventory updates in another separate topic. So we can segregate them accordingly. Each topic should represent one kind of fact. Do not create topic when the topic has no clear owner. The topic exists just in case. You are splitting data too finely without justification. You just need to split the data with justification, with few categories, but not, diverse. I mean, insanely diverse categories. Just need to split into, basic categories. That's fine. When I say that, what I mean is, if you delete the categories like orders, payments, that's fine. But if you be more precise and want to divide these categories into orders accepted, one topic for order accepted, one topic for order declined, and one topic for order shipped, that makes it more complex. So make it more justifiable. Too many tiny topics cause metadata overhead. So every topic has its own metadata created. So that might overload. Operational complexity, you working on it will still feel complex to differentiate between them or work with them because there are too many segregations. Systems that are hard to reason about. More topics is not equal better design. You should have topics that are just enough to segregate the data, not you should not overwhelm the system with the complex segregations. Now, talking about conceptual diagram. Let's go back to the slide. Okay. Duplicate this. Say Kafka topic. Now, instead of all this, delete everything. We don't need these many for this diagram. This is a simple diagram. Okay. What we do is we just want this container alone. Make it bigger. Switch the position to top. And then this is a Kafka topic as usual. We represent these as events. Separate them. C, B, A. Basically the same. What else can we use to represent this conceptual diagram of topic? That's it. What I'm going to do is I'm going to annotate this as ordered to say they are all ordered, maybe. And then an arrow showing the direction saying append only. Oh, it's the other way around. Perfect. Yep, that's it. That's it. That is simple. There's no other way to represent a Kafka topic, right? Okay, this is it. Let's take a screenshot first. Starting from here. Add it to the document. There you go. That is pretty much it. Now, this is the first concept where we're going to start with the lab. Now, this is the second concept. Now we're going to actually work with the Kafka. We installed Kafka. Now we are going to work with Kafka. We're going to create a topic, our first topic. Okay, this is the first real Kafka interaction. Nothing happens implicitly, everything is explicit. Kafka topic creation, Kafka CLI, runs inside the container. So what we're going to do is, in Docker, we're going to enter the Kafka container and then create a topic. To enter the container, the Kafka container, we have to use this bash command, CLI. What we can do is we can just copy from here. But remember, when you're copying this, oh, this will copy fine, totally fine. You can just use Control C from the Word document and then paste it. Go to Docker in the terminal. Let me make it bigger. Let's see if we can zoom it. Oh, this search, okay. Not sure if I can zoom it. I don't think I can. Okay, that's fine. Now here in the terminal, I'm going to paste that command, which is docker execute it Kafka bash. Now I'm going to enter the Kafka container. Hit enter. Now this random serial number or serial code confirms that you are inside that container. Here, whatever I run here I am running it inside the Kafka container, by the way. Now next what I will do is I change the directory inside the Kafka container and go to opt/kafka/bin. Bin is where all the basically files, the .sh files, the bash files that are related to Kafka are present. So if I copy this, but remember, from here, right after you enter the Kafka container, you cannot just use Control-C and Control-V to copy paste this commands. What you have to do is you have to right click, copy, go back to Docker, and then right click, paste. This is the right way. You might think, doesn't matter, right? But no, it does matter. If you use Control C to copy, and then to paste it, if you use Control V, wait a minute, Control C, Control V, it doesn't work. And if you use copy here and Control V here, it still doesn't work. You have to copy it using right click, copy, right click, paste. That's it. Now we're changing the directory to bin where all the bash files present. When I say bash files, what I mean is, let me show you. If I run ls, which lists all the files, that are in that repository. The bin repository includes all this. You can use any of these files. These are all the methods that you can use when you interact with the Kafka container. There are a lot of things that are here. Let me give you an example. We use Kafka console consumer to create a consumer. And we use Kafka console producer.sh to create a producer. In the same way, there are a few things I know about. Nobody can know about all these bash commands. We just know about a few. According to our use, we search on Google or we ask AI for the exact appropriate command, and then we use that. So here, Kafka topics.sh, we use that to interact with the topic, to describe it, or do some sort of actions to the topic, or to create it as well. Now, here, when you're here, you have to run this command. Run this command. What this command does is, it creates a topic named orders. Let me explain the whole command first, okay? Copy it. Now first place it or paste it in Notepad first. And there is a reason why I do this as well, okay? Now first you paste it in the Notepad. Why I did this is, like I said, a Word document hides a lot of things. And you have to make sure nothing is in this copied statement, or else if that command, if you paste that command as it is into that terminal, it will trigger an error, any error. What I mean is, here you see that there's a gap between each line. There should not be a gap, so you remove that. And also the most common one is, after each line there is a space, there is an empty space. You see that? There should not be an empty space. You have to clear that as well for every line. Except for the last line, you don't need to clear that. That still works. But these lines you have to clear. Now, talking about the command we are using here, like I said, we are using Kafka topics.sh bash file. It is part of the list right here. right? Here is part of the bash files that Kafka has. We are using that file, and I already told you why we use that file. Use that to create or to actually do tasks on topics. Here we are doing create task. We are creating a topic and double hyphen topic name orders. This is the topic name, and the topic has 3 partitions. We don't know what partition is yet. We will know about it, but yeah, remember we are creating a topic with 3 partitions. That's it. Replication factor is 1. Remember this as well. We'll talk about it later. Bootstrap server host docker dot external and 29029. Like I said, these are our advertised external port that we can connect to Kafka cluster. We can use this, or we can also use the Kafka -9092 because that is our internal port. We can still use it because we are running this command inside the container. Remember, we entered into the Kafka container. So here we can still use this port as well. Which port it is? Let me show you. So we can still use this port as well. Instead of host.docker, we can use this internal port. It still works because we are inside the Kafka container. Okay, now we are going to use the external port. That is what the command is. And by the way, these forward slashes represent a new line. If you write this whole command without the forward slashes, like this, everything in one single line, this will still work. This single lines will still work as this the same way, but for the readability and not to make the whole terminal clumsy, we can add these new lines and continue our command in the next line. That's how those forward slashes work. This is not part of Kafka, by the way. This is a part of command line interface. Okay, now we have this command. Now we took all the extra spaces out. Now we right click, copy, paste it using right click, paste inside this terminal, run it. Now the output is created topic orders. That confirms the topic is created. To double check the topic is created, what we can do is we can just head to the UI. Remember, we created the UI, we defined the UI container. Go here, refresh. Now head to topics on the left pane. Click on topics. There you go. The topic we created, which is orders, will be listed here with 3 partitions we define, 1 replication factor. For now, number of messages is 0. There are no messages yet. So obviously the size is 0 bytes. Out of sync replicas. We'll talk about the replicas later, or we can talk about it now itself. So what are replicas means? So in this broker, this container, this particular container acts as a broker, right? Acts as a Kafka broker. Let's say if there are multiple brokers. So, and let's annotate this container that we are working on as broker 1, and there are broker 2 and broker 3 as well. And this particular topic is replicated across all these 3 brokers. Okay? All these 3 brokers just as a backup. And the main reason for replication is if one broker goes down, the other 2 brokers can be has the same data replicated, so they can use those brokers to get the data out. That is what replication means. And that is how these controllers also work. So the main broker will be the controller, which will be this one. So the main broker and the rest of the brokers replicates the controller broker data into the topics into those broker clusters. When I say out of sync, when it says out of sync, let's say a producer produced a new event. Let's say producer produced an event E. First, it stores in one broker, which is the broker controller first, okay, right? So the broker controller will store that event first and then replicates through these two other brokers, which are basically following the replica, the controller broker. So before replicating this event into those two brokers, if we come here, we can see the out of sync brokers because it is not synced yet. The event is still replicating, in process to replicate. It's not replicated yet. So here we can see out of sync replicas as 1 or 2 depending on the delay. That is what out of sync means. Yeah, that's pretty much it. That is how we create a topic. I'll head back to here. Verify the topic is created. Instead of verifying it through UI or by the output log that got printed in the terminal, we can use this command. This command lists all the topics. Now what we do, we copy it, we paste it in the notepad first. So this command, what this command does is, it uses the same bash file, Kafka topic.sh, but here it uses list. So it lists all the topics from the server. Now we take out the extra spaces, copy, paste here. Now this okay, something went wrong. What is it? Okay, there is an extra space there, I think. Let me run that again with deleting this space, removing that. Now let's copy that. There you go. I hope you can see it. So it lists all the topics. Right now we only have one topic, so it listed that one topic, which is orders. That is how we conform it. So we have that, expected output orders. What this proves, topics are explicit entities. Kafka does nothing until topic exists. Data organization is intentional, not automatic. So the data is not organized automatically. You have to do that manually, intentionally, by yourself. To exit the container, type in exit. Now, here in the terminal, you are inside the container, right? To exit this container and to go to the regular terminal, you can just type in exit, hit enter. That's it. You go back to the regular terminal. Okay, we're done with the lab. Topic design principle to internalize. Topics represent facts, not actions. Names reflect business domain, not technical verbs. You got it right. It is talking about the naming convention. So you have to name the topic carefully so you can recognize, you and your team members who are working on the same project can recognize the topic name. One owning team per topic. Configuration follows data importance, not convenience. So configuring the topic should be dependent on the data importance and not convenience. Topic design is architecture, not syntax. Final takeaway, a topic defines what data exists, who owns it, and how it lives. What data exists, who owns it, how it lives. These three factors. These are defined by topic. It is a contract, not a transport mechanism, and treating it otherwise leads to ungoverned Kafka systems. That is the final takeaway. That is it with this concept. Let's head to the next concept, which is 2.4, partitions. All right, let's start our next concept, which is partitions. 2.4, by the way. Starting with the definition, a partition is a physical, separate, ordered, append-only log inside a topic. In Apache Kafka, a partition is a physically separate, ordered, append-only log inside a topic. So it is a physically separate partition. Oh, well, it is a partition. So it is a physically separate log from the topic. So the data inside a topic, we're just separating the data inside a topic again using partitions. And each partition is ordered just like the topic, just the topic. And it is append only as well, just like the regular topic without partitions. So, but we just separate those data into different logs, separate logs, sublogs we can call them. So inside a topic, we again partition this data, and we will know the reason. Okay, there is a reason for that. We will know about it. In Apache Kafka, all scalability and parallelism exist only because of partitions. That is the main reason for partitions. It is responsible, or it offers scalability and parallelism at the same time. Key facts you must internalize. A topic is divided into one or more partitions. A topic can be divided into multiple partitions. Each partition is written to and read from independently. So they're not dependent. The partitions are not dependent on each other. It is independent. Ordering is guaranteed only within a single partition. We cannot guarantee the order throughout across the multiple partitions. We can only guarantee the order in single partitions. There is no global ordering across partitions. The same point. We cannot have a global order across all the partitions. We can only confirm the order in one single partition. If the same data has, let's say if you generated a data events, let's say event 1, event 2, event 3, event 4. Event 1 and event 2 are stored in partition 0, and event 3 and event 4 are stored in partition 2. So the order that is stored in partition 1 is not dependent on order stored in partition 2. That is how the relation works. They're not related. The order is not related between partitions. Why partitions exist? Problems they solve. Throughput units, the rate of the speed of data transfer. A single log has one write, becomes a hard bottleneck under load. Whereas partitions solve this by allowing multiple writes in parallel, distributing load across multiple brokers, turning vertical limits into horizontal scale. Basically, let's say a topic with one partition. So if you create a topic without configuring any partitions at all, like this here, we did create the topic here, right? But we configured the partitions as 3. But if you haven't configured this line at all, if you haven't wrote this particular sentence at all saying configuring the partition, by default the topic created has one partition. So if you do that, yeah, multiple producers still can produce the data and store it in that topic at the same time, even with one single partition, but still only one producer at a time can use that partition, and the other producer waits until this producer sends that event, and that event gets stored in that partition. So that is a bottleneck. That is what it says, becomes a hard bottleneck under load. So there are multiple partitions, multiple producers writing to the same topic, which has one partition that cannot handle the load, because only one producer can store an event in one producer at a time. It, I mean, multiple can, but at a time, only one. The other producer waits for that producer to be completed. Now, now allowing multiple writes, what happens is if producer 1 is, let's say, producing a data, producing an event A or something, producer 1, when it produces an event, that goes to partition 1. If the producer 2 also produces an event at the same time, that producer will be assigned to another partition. If producer 1 gets producer 0, uh, producer 1 gets partition 0, producer 2 gets partition 1. So they can actually write the events parallelly to the same topic. That's how partitions work. That is what the parallelism means. That's how the partition work. Consumer scalability as well, not just the producer scalability, it is also about consumer scalability. You can increase the throughput at the consumer side as well. Without partitions, only one consumer can efficiently read the data. Adding consumers does not increase throughput. Let's say if multiple consumers want to read from the same partition, the consumer has to wait until the one consumer is completed. Whereas in partitions, what we can do is we can create a few partitions, multiple partitions, and then we can create a consumer group. We will talk about consumer group later, but now it is just a group of consumers, and then these group of consumers read from a group of partitions. I mean, from a topic with multiple partitions, and every consumer from these group will be assigned to a particular partition. In that way, it makes it a lot faster to read the data. Partitions enable one consumer per partition. Horizontal scaling using consumer groups. We already talked about consumer groups. A coordinated set of consumers sharing work. So they share work across all the consumers inside the consumer group, and each consumer will be assigned to a set of partitions, and the rest of the partitions will be assigned to another consumer of the same group. In that way, they read the data parallelly and makes the work done more faster. Now, parallel processing without coordination at application level. This is why consumer scaling is tied directly to partition count. Now we talk about fault isolation and distribution. Partition allows Kafka to replicate data across brokers, handle failures independently per partition, distribute storage across the cluster. Failures do not take down a topic globally, they are isolated at partition level. Critical truth, Kafka does not scale topics. Okay, so yeah. They also play a major role in replicating the data across the brokers. We already talked about replicating the data to multiple brokers. So if one broker goes down, the data that is replicated throughout the brokers, so another broker can act as an active controller, which from which a consumer can consume the data. So for that, in that use cases, the partition will also uh, plays a major role. You will know a lot about partitions by the end. Partition is, in my opinion, it's a big concept to know about. You will know everything about it by the end. When to use and when not to use. Use partitions when event volume is high. You need higher write throughput. You want multiple consumers processing data in parallel. Events are, if the event volume is high, if there are a lot of events flowing in, you need partitions because it increases the throughput, write throughput, and it also increases the consumer processing time because multiple consumers can process the data in parallel, so it also optimizes that. Now, typical examples: high volume order streams, click stream and user activity data, logs and matrix, logs, metrics, and telemetry. In real systems, partitions are not optional, they are mandatory. In real systems, we definitely use partitions because of their applications, their advantages that we get using partitions. Do not rely on partition when you require global ordering. If you want the order to be global across the topic, do not use partitions. Event must be processed strictly in sequence across the data. The same thing. Important constraint: Kafka cannot guarantee ordering across partitions. Oh, that's the same line, okay. Order exists only written order exists only written on sorry order exists only within one partition. So when we divide the data into partitions in a topic, one particular event one particular partition has its own order. You cannot just define the order throughout the partitions. Order can only be defined in one particular partition alone. If strict global order is required, Kafka may not be the right tool, or the design must force all related events into a single partition. Or you define by using key values to make all the data that you want to order in the same way to go to the single partition. We will talk about that concept as well, but not in this concept. That is a different concept where we use key values to separate the partitions between the types of data that is stored. Now heading to the conceptual diagram. Duplicate this. What I'm going to do is I'm going to make this a big box. Like that. Okay. Name this partitions. Delete this, delete this. Keep it aside. No. Uh, I'm going to create a small block inside here and say event A, copy paste. Paste. I'll leave that like that. That's fine. Okay, now copy this whole thing, paste it right next to that here, paste it again, and another partition. Now what I'm trying to do is and this as partition 1. This is partition 2. Three. That's good. Now what I'm going to do is I'm going to randomly give this events order. Say event A is here and event B is here and event C is here and event D is here and event E is here, event F is here, event G is here, H here, I here, A, B, C, D, E, F, G, H, I. Okay. Now, we just generated the events without any key values. These events goes to random partitions. I mean, it is not random. Kafka follows an algorithm by which it divides or uses a partition accordingly, but for us it might look like a random choice. So this how it might look like, and it is not ordered across the partitions. It goes in random directions, but it is only ordered in one single partition like this. A comes first, C comes second, F comes next. It cannot order across all the partitions. This is what I'm trying to represent here. Now, with the last, finish off with this. To represent, that is the event flow for every partition. I think this is a pretty good representation of a partition. Now let's take a screenshot of it. Right here maybe. Okay, perfect. Head back to the document. Paste that screenshot in the conceptual diagram. And the key point, ordering guaranteed per partition, only per partition. It cannot be guaranteed globally across all the partitions in the topic. Perfect. Now the lab includes Kafka is already running from previous lab, right? Enter Kafka consumer container again, Kafka container again. If you're out, you enter that again using these commands. Let's enter copy, paste. Perfect. We are inside the container now. Now run this command. Before running the command, we have to paste it in Notepad and take care of the extra spaces. Here, here, here. And also, what this command does is Kafka topics sh, it uses the same bash file. And now we are using describe action. So we describe what the topic orders. So we describe the topic orders. So it describes the topic now. Copy, paste, and run. There you go. I hope you can see it. Here it shows topic orders and all the three partitions, because we created the topic with configured with three partitions. So it shows all the three partitions starting from 0, 1, 2. And talking about the leaders and followers, I think this is the right time to talk about the leader and followers. Let's say we already talked about replicating the data across all the brokers. And we said partition plays a major role in that as well, right? What that means is we can replicate the partitions, the data in the partitions. So we can replicate the partitions in a broker in multiple brokers. When we replicate it, one partition out of all those replicas, one partition will be the leader and the rest will be the followers. It depends on which broker the partition is created, and what the main reason behind the splitting between the leader and follower is whatever the partition changes that happens in the leader partition will be replicated across the follower partitions. And if one broker goes down, let's say the leader goes down, the replica broker, which will be having all the data that is replicated from the other broker, can act as a controller, and this follower becomes the leader, and then the other follower, the other partition will be stayed as follower. This will become the leader, and that's how the leader and follower relationship between partitions behave like. Now, the replicas define how many replications for this particular partitions are there. The replications are one, not there are only one replica for that partition. There are no replicas at all. And then ISR, in sync replicas, which is one, because there is only one replica, which is this PC. There is no replicas, extra replicas. So ISR stands for what did I say? I just forgot. In sync replica, and ELR stands for, I forgot these acronyms. Okay, eligible leader replicas. So what is ELR means? When we have multiple replicas of a particular partition, one will be the leader, like I said, the other will be the followers. Within those followers, a few will be eligible leader replicas, which means if something happens to the leader partition, the eligible leader replicas take over the spot of leader, and the other ones follow this partition. That's how the ELR and leader and follower works. This is one of the topic you have to know about the partition as well. And in sync replicas is nothing but how many are in sync with the leader and how many are not in sync with the leader. It is about replicas. Replicas that are fully caught up. That is what the number says. So this the describe task, that describe action that prints. We can do that, or we can just see that here, right here in the UI, but this is not that. Now this is that, this also describes it well. You see that when we click on the topic, we can see the partitions. Partition ID 0, 1, 2, and replicas 1, 1, 1, first offset, next offset. First offset is of course 0, next offset is 0 because there is no data in it, but if the data changes, the offset increases, the next offset increases, and the message count determines how many messages are in that partition. Okay, there you go, in sync replicas, ISR, and we don't see ILR, eligible replicas, here. Okay, yeah, UI have their own downside. They cannot show everything, right? But the commands does. That's why it is always good to know about the commands rather than checking them in the UI. So we're done with that. So expected output includes topic name. Of course, topic name is printed, orders, partition count 3, 0, 1, 2, leader, replicas. Right now, all the partitions are leaders because there are no replicas of those partitions. So all of them are leaders. Replicas which are 1, there are no extra replicas. ISR in sync replicas, ELR eligible leader replicas. ELR should be empty, I think. Yeah, they're empty because there are no extra replicas. And no, that's not the reason, because this is the actual leader replica, right? So that's why it says. So leader equals 1 defines 1 means leader, 0 means not leader. What to call out explicitly? While I wrote this for my script, what to call explicitly. Say what to know about. While sorry, not this one. Each partition is listed separately. Each partition has its own leader, its own replica set. Kafka treats partition as independent units. You see that? So it prints the independent units separately. At this stage, no producer, no consumer. We haven't created a consumer or producer yet, but we will create in the upcoming topic, concepts. Now, design implication you must remember. More partitions is nothing but more throughput. More partitions is nothing but more parallel consumers. More partitions is nothing but more operational overhead. It also increases the load. It also increases operational capacity. Partition count is a capacity planning decision, not a cosmetic one. Changing partition count later is possible, but it has real consequences for ordering, key distribution, and consumer behavior. Once the partitions are created, let's say 3 partitions, and if you want to reduce them to 2, there are their own consequences you have to take care of before you go down in partitions. Final technical takeaway: partitions are the scaling unit of Kafka. Throughput, parallelism, replication, and consumer scaling all exist only because of partition exist. Topics define what data exist. Partitions define how far Kafka can scale. Okay, that is clear, right? Topic defines what data exists. Partitions define how far Kafka can scale. It is about scaling. Now we are done with the partitions topic as well. Now let's head to the next topic, which is 2.5. Next concept. Sorry, I keep saying topic, it should be concept because I cannot say topics here. So the next concept is 2.5. Let's head to that. Now, talking about our next concept, which is offsets, concept 2.5. In Apache Kafka, an offset is a monotonically increasing position number that represents where a consumer is within a partition. To be clear, for every line, so an offset is a monotonically increasing position number. A monotonically means one increment at a time. So it goes one step ahead every single time. So monotonically increasing position number, a checkpoint basically, that increases one event at a time, one position at a time, that represents where a consumer is within a partition. So it represents where a consumer is at in a partition. Key facts you must lock in. Offsets belongs to consumers, not to messages. So it belongs to the consumers, not to the messages. Message doesn't care about the offsets. Consumers do, because multiple consumers read the same messages, can read the same messages. So messages should not be caring about offsets because multiple consumers are reading from the same messages. Offsets are tracked per partition. So every partition have their own offset per consumer. Kafka does not track message consumed. Kafka tracks consumer position in the log. It doesn't track the messages consumed. It tracks the consumer position in the log. That makes sense, right? Because there are multiple consumers, we cannot track messages consumed because another consumer might consume the same message. So that is not the way to track. It tracks a consumer position in the log. That is the way to track. So it can track multiple consumer positions. This distinction is foundational. Kafka is position based, not message ownership based, like the traditional APIs. Why offsets exist? Problems they solve. Replay. Without offset, once the data is read, it disappears. Reprocessing is impossible. Debugging historical data is not feasible. Offsets solve this by allowing consumers to rewind to any position, enabling rereading historical events. I'm not explaining them again because I explained these concepts already. So I'm going to read them down. That's it. Just not to waste the time. Making backfills and recomputation first-class capabilities. We talked about backfills. It goes back to fill that data. Failure recovery. Consumers crash, nodes restart, deployments fail. Offsets allows consumer to remember their past position before they crash, so they can continue from that. Restarting from the last committed position, the same thing. Continuing processing without losing data. Choosing trade-off between duplication and loss. Kafka does not guarantee no failure. It guarantees recoverability. Cannot guarantee there will not be any failures, but it can guarantee the recoverability of the data. Even if it fails, it can recover the data again. Independent consumers. Multiple consumers can read the same partition at different speeds. With different offsets. They can read the same partition. Like I said, they can read the same partition, but not at the same time. That's it. At different speeds with different offsets. Let's say a consumer A can be at offset 2 and consumer B can be at offset 1. That's still fine. They can be in different offsets and read the data from that partition. Each consumer maintains its own position. This model is impossible in delete on read systems where data no longer exists once consumed. When to use and when not to use, when not to expect offsets to help. Use offsets when replay is required. Recovery after failure matters. Multiple independent consumers read the same data. Common scenarios are rebuilding downstream state stores, debugging or auditing pipelines, backfilling analytics after logic changes. Offsets turn Kafka into a time travel capable systems. That makes sense, right? Offset turns Kafka into a time travel capable system because of the checkpoints they store. Do not expect offsets to help when you expect messages to disappear after being read. You are modeling tasks, not events. Kafka will not retain data regardless of offsets. Important clarification, by the way. Data is removed only when retention rules, time based or size based, apply. Offset control where you read, not whether data exists. Conceptual diagram. Let's head to the PPT. Duplicate this slide. But now what I'm going to do is delete. Now first let me resize this to this and delete these two partitions because this topic is not about partition, this is about offset. Take this down, take this out. Name this a Kafka topic. Now when events enter partitions, well, the partition number should start from 0, not 1. Okay, partition 0. And they all have, every event in that partition have its unique offset. Starting from 0, offset 0, offset 1, offset 2. Now the Kafka saves consumer position, remember? So what we're going to do is we're going to copy this and paste it here. I'm going to use this as that and say consumer offset. To be more particular, let's say consumer A offset. So now consumer A at this position, it is reading this event. After it read this event, the offset changes to offset 1. So if the consumer A crashes at offset 1, when it comes back on, it reads the event at offset 1 and not offset 0 again. That is how it works. Let me rename these two because they're not in the order. Let's see. Perfect. Let's take a screenshot now. Oh, that is not good. Let me take another one. Perfect. Go back to the document. That is not where I am supposed to paste it. Supposed to paste it here. Perfect. Now the key points: offsets stored separately from the data. They're not stored with the data, they are separately stored. The offsets are stored separately. I will actually demonstrate it while we go further. I will actually show you how the offsets are stored. The data is stored separately and the offsets are stored separately in a different, they are segregated separately, basically. I will show you how they are segregated. Consumer position moves. Consumer position moves across the offsets. Lab, observing offsets and consumer log. Consumer lag. There is a factor, consumer lag, we have to know about. I will talk about it. Enter the Kafka container. Again, we already entered. I never left it, but if you left it, enter that again. Okay. Let me add this topic as well here. In case if you left it, run these two commands again. Start the console producer. Already? Okay. Paste it here. Take out the not necessary spaces. Now what this does is, we are using Kafka console producer.sh bash file. I already told you why we use this file. We use this file to work on the producers. If you want to create a producer, describe it. No, if you want to create a producer, we use this. Kafka console producer.sh. And the producer is linked to topic orders. Okay. And the bootstrap server host, and this is the port. Now we're creating this producer. Inside the Kafka container. Now this gives us access to actually produce the data because we created a producer now. All right, now what's next? Type a few messages manually, and these are the messages: order 1, order 2, order 3, order 4. Let's type them in. Exit the producer with Control C. Okay, got it. Order 1, order 2, order 3, order 4. I did produce them. Now to exit, Control plus C. There you go. I exited the producer. Now we did produce the data. Let me show you. Let me show the UI for you. Now we did produce the data, right? Now if you go to topics, click on orders. Now it already shows the number of messages as 4 because we produced 4 messages. The size of it, when we open that, all these 4 messages went into one partition. Like I said, it looks quite random, but Kafka behind the scene follows an algorithm. Based on that, these events will be assigned to that particular partition. But we can control the partitions using key values. We will talk about that, like I said. But we haven't used that concept yet. So all these messages are randomly given to these partitions, which is here in this case, all the 4 messages given to partition 2, partition ID 2. Now it says the first offset, of course, will be 0. The next offset will be 4. Message count is also 4. And if you switch to messages section, we can actually see the messages that are created with the offset and the partition the message belongs to. All the messages belongs to partition 2, and the offset 0 starts from 0 to 3, 4 to 5, 6 to 7, 8 to 9, 10 to 11, 12 to 13, 14 to 15, 16 to 17, 18 to 19, 20 to 21, 22 to 23, 24 to 25, 26 to 27, 28 to 29, 30 to 31, 32 to 33, 34 to 35, 36 to 37, 37 to 38, 39 to 40, 41 to 42, 43 to 44, 45 to 46, 47 to 48, 49 to 50, 51 to 52, 53 to 54, 55 to 56, 57 to 58, 59 to 60, 61 to 62, 63 to 64, 65 to 66, 67 to 68, 69 to 70, 71 to 72, 73 to 74, 75 to 76, 77 to 78, 79 to 80, 81 to 82, 83 to 84, 85 to 86, 87 to 88, 89 to 90, 91 to 92, 93 to 94, 95 to 96, 97 to 98, 99 to 100, 101 to 102, 103 to 104, 105 and the value which is order 1, order 2, order 3, order 4. Remember I said key, so we can define this. So using keys we can actually make the data, all the data that is related to one particular thing can go only into one single partition by using keys. I will tell you how, but for now, yes, we got the data here. What's next? Start a consumer, run a console consumer. Okay, we're going to start a consumer here. Copy, paste it in the notepad, take out the unnecessary spaces. This. Using Kafka console consumer, we are creating a consumer. We used Kafka console producer to create a producer. We use this to create a consumer and consume from this topic, which is orders, group orders. So we're creating a consumer group, orders consumer group. We're creating a consumer group. We'll talk about the consumer group later in the next later concepts. And this is the offset. We are saying start from the beginning offset. So it goes to offset 0 and starts from there. But once you run this and you stop it before it reads all the events and you rerun this and take this out from beginning, this consumer starts from where it stopped. Like, you got it, right? So this consumer group saves the offsets, and if you run it without this line, this consumer starts where it stopped. That's how it works, because the offset, the checkpoint is saved. Right now, we don't even need this, to be honest. Now let's just copy. We only need that from beginning command when you're running the consumer for the second time and want to begin from the first offset again. But for now, that is fresh. So we can exclude that. Run. Trying to figure out what happened here. Okay. Now, when we switch to consumers, the consumer group is created. I think it by default, it went to the earliest mode, which no, it went to the newest mode. So only the new messages will be consumed. Maybe we have to include from beginning here. So if we include from beginning and copy that, go back to the Docker terminal and stop this and paste this again. Now the already produced messages will be consumed. No? I think I'm missing something. Well, I just found out the error. It turned out to be we have to use this line from beginning to configure, or else by default, when we create the consumer group, it is by default set to the latest offset, which means it don't read the old messages or events that are generated, that are produced, which in our case, when we ran this exact command without this from beginning line, it took the configuration by default as latest, and it only waits for the latest messages, and it ignores the old messages that we produced using order 1, order 2, order 3. That's why we haven't got any. And the offset is already set to the group. And even if you run that command again, still the offset is already set to the latest, so we cannot change it. So I deleted the group, the consumer group totally, and then now I'm pasting this again. Oh, sorry. So I deleted the whole consumer group. Now I'm pasting this command again. Paste it. Run it. Now, because now we are saying from beginning, it creates, it consumes all the events from the beginning of the log, the partition, or the topic. That's how we got all the data now. So yes, this line is important. I thought it is not. And then what else? A consumer group was created. Consumer group equals coordinated consumer sharing work. Offsets were committed for each partition. Now let's go ahead and check on the consumers. Now first, the consumer group is created. Okay, number of members, just one consumer. Number of topics, one topic assigned to one topic. Coordinator equals 1. This is the topic that is assigned it to. And it shows the consumer lag. How many messages or how many events this consumer group is lagging when compared to the topic. Now, right now, it is not lagging at all because it consumed all the 4 orders that we created. When we go to topics, remember when I said offsets will be stored separate to the data? This is what I meant. When we start working with the offsets, when we consume the data, it creates a consumer offset separate to the data, which is this. So this is the data and this is the offset. These are the offsets. These offsets will be saved separate. Here, orders. Yes, that's it. That's it about that. We got it. Now, let's run this. To inspect consumer group log, run this command. Paste it here. Take out the extra spaces. Now what this does is, it uses the Kafka consumer group .sh bash file, which describes a consumer group, and the consumer group ID will be this, which we just created. Let's copy this whole thing. Paste it here, run it. Now this describes all the consumer groups and lists all the partitions the consumer group is assigned to. Partition 0, 1, 2. And it says current offset. And on partition 2, where all the data is saved, the offset is at 4, which means it read all the data, all the offsets. Lag, no, log end offset. So this is the ending of the offset, and this is the current offset. I'm trying to make it bigger, but I'm not sure how. I don't know how to make it bigger. I hope you can see this. See that there are 2 columns. One says current offset and the other one says log end offset. You have to check on those. The current offset says the consumer's current offsets. If it is at 4, which means it read all the data, and the log end offset is the offset where the log ends. So the end offset is 4 and the current offset is also 4, and that is why the lag is 0. When we talk about these factors, here, the current offset, where the consumer is now, the log end offset, latest event in the partition, the lag, how far behind the consumer is. If the producer generated 5 records, which means it has 4 offsets, and the consumer is still at 3rd offset, the lag will be 1 because it still has to read the last 4 offset number 4. That is how it is calculated. It is basically calculated as lag equals log end offset minus current offset. That is how we calculate the log. The lag. This proves three critical facts. Kafka tracks position, not message deletions. Kafka knows exactly how far a consumer is behind by the lag, right? So it knows how far the consumer is behind. Messages still exist even after being consumed. They are still existed. See, even after we consume the messages through the consumer, the topic still has the messages in it, right? So that is what it means. Now, offset lifecycle conceptual understanding. At a high level, offset flows look like this: consume records, process records, commit offsets, resume from committed position on restart. So this is how it works. It consumes records and process the records and then commits the offset. There are two types of committings, but if we say auto commit as true, it commits before the processing is done. This is a quite complex concept. This has a separate concept where we talk about it, but for now, this is how the flow goes. It consume records, process records, commit offsets, resume from committed position on restart. If the consumer restarts, it restarts from the committed position and not from the beginning of the log. Where you commit offsets determines your delivery guarantees. This is where this will matter later when reliability is discussed. Offsets are what makes Kafka reliable. This is the final takeaway, by the way. Offsets are what makes Kafka replayable. Data retention and consumer position are intentionally decoupled. Kafka deeps history, and consumers decide where to read from it. Okay, that is the final takeaway from the producers, from the offsets. Now we're done with that concept. Heading to the next concept, which is 2.6. Now let's talk about our next concept, which is 2.6, producers. Talking about producers, the definition of producer is: in Apache Kafka, a producer is a client application what writes events into Kafka topics. We already came across this uh, word producer a lot of times in this masterclass, so I don't it doesn't need a special introduction or special definition again. We know what a producer is. What producers actually do: append events to partitions inside topics. Do not wait for consumers because they are asynchronous. Decide delivery guarantees via configuration. So how depends on how we configure the producer. It can guarantee the delivery of the events that are produced. Critical truth: Kafka itself does not decide reliability, producers do. Why producers matter? Problems they control. Problem 1: data durability. Every write raises hard question. Did the event reach Kafka? What is written only to leader or also replicator? Will it survive broker failure? If the data is replicated, it does survive the broker failure, right? Kafka exposes these answers through producer configuration. We can configure the producer in the way it follows all these, it answers all these questions and make sure everything follows is in the right pattern or in the right configured in the right way. Not magic defaults, okay. If your producer is misconfigured, Kafka cannot save you later. Throughput versus safety. There is no free lunch. There is no free lunch. Faster writes. No. Okay, throughput versus safety. There is no free lunch. Faster writes. Weaker guarantees. Stronger guarantees, higher latency. So if you want to make sure the rights, if you want to guarantee the rights that the producer is producing, it takes time, right? But the faster rights takes less guarantee. It takes time to make it a guarantee. Kafka is explicit about the trade off instead of hiding it behind the abstraction. This is intentional. Production system need conscious choices. Partition placement. Events must be distributed correctly. Load must be spread across the partition. Ordering must be preserved where required. Producer control this via keys and partitioning logic. We talked about keys and values before when we talked about partitions. Remember, we can use keys so we can separate one type of data, go into the same type of data to be saved in the same partition. That is what this line means. Kafka never randomly figure it out for you. We have to configure it. Producer configuration. Only what actually matters. ACKs, acknowledgements, controls how many brokers must confirm a write before it is considered successful. We can actually control this using a configuration called ACKs equals, and then we say how many uh, brokers must confirm the write before it considered that write is a successful write. So let's say if I have 4 brokers that replicates the same data. When we write using a producer, the producer waits until at least if we say ACKs equals 2, the producer waits until at least 2 brokers confirms the write. Until then, it stays there. If those 2 brokers confirms the write, and only then that is considered as a successful write, or else it just waits. ACKs equals 0, fire or forget, faster and unsafe. So if it is ACKs 0, it just writes and it doesn't care about the acknowledgement that broker sends. ACKs equals 1, only leader partition acknowledges the write and then it conforms. It is okay. Then there is ACK equals all, leader plus all in sync replicas, higher durability. It makes sure every replica, the write on every replica is successful, or else it is not considered as a successful write. So that is how this particular configuration works. And there is another configuration we have to talk about, which is retries. Control retries or transient failures, network blips, leader election, temporary broker unavailability. Without retries, transient failures equals permanent data loss. So when a producer emits an event, if some sort of error occurs and it is not successful, it retries again. If we configure the retries configuration and say a certain number of retries, and it follows that configuration and retries until that configured retries exceed. If you don't configure it, transient failures equals permanent data loss. So that data will be lost. Retries are not optional in real systems. Idempotency. Idempotency, we talked about this concept. If you watch the Python masterclass, you would have already know about what idempotency is. Idempotency is nothing but, let's say if you run a task over and over again, still the task should produce the same output. No matter how many times you run the same task, it should still produce the same output. That is what idempotency means. It ensures retries do not create duplicates. That is one single line definition. So it makes sure retries, whenever you retry to, emit the event, it doesn't produce an duplicate event. That is what idempotency means. Exactly once production semantics, producer side only. We will talk about these semantics later, but so it ensures exactly once production semantics. This is what it is talking about. Right now, you will not know what exactly once semantics means, but we will know what. There are a few types of these semantics, and we will know about it when the time comes. Modern Kafka producers must enable idempotency. If idempotency is off, retries can corrupt your data stream. So yes, so idempotency is another configuration. You have to turn it on, or else the retries can corrupt the data system, can create the duplicates. Now coming to the conceptual diagram. Head to the slides again. All right, let me just duplicate this slide. Duplicate it. Say producer. Say partitions. We're not going to talk about events yet. So for this, I'm gonna rename this as partition 0. Two. That should do, and we take out this offsets. Move it to this side because producer should be on the left, because that makes it easier to understand. And copy this block from this slide and paste it here. Say producer. Now I'm going to connect a few lines from producer to partitions. This is not so convenient to draw. PowerPoint is not so convenient to draw these conceptual diagrams, but I'm trying my best. And one more line like that, and that goes to partition 2. Perfect. Okay. So it writes into the topic. It only cares to write into one Kafka topic, but the partitions, it doesn't care about that. The data that is, or the events that are produced by the producer will be distributed all across the partitions. Only, I mean, it doesn't care about anything. It just uses a logic, internal logic that we don't know. It just distributes the events to all the partitions, and that's why I used 3 lines to represent the incoming events, and I connected all the partitions to the producer. I think that's perfect. Now let's take a screenshot of it. Perfect. Paste it in the document. That's it. The key points: one producer, many partitions. One producer can write to many partitions. Partition selection via hashing. We haven't talked about it yet, but remember that. Hashing nothing but keys. Deterministic routing, not randomness. Routing is not random. It does have a logic, like I said, but we can route it to a particular data to a particular partition using keys. Like I said, we will talk about it for sure. Now comes to the Python producer lab. For this, we need Python installed in your PC. So make sure you installed it, and the version should be higher than 3.10. To make sure you have the right version, just copy this, go to Docker. Now, instead of Docker, open PowerShell here. And root to our repository that we created. Now here, now you don't for this command, the Python version, you can run it anywhere. By the way, you don't have to go to the repository. I don't know why I did that, but you don't have to go to that. You can just run it from anywhere. You can get, and you will get the Python version installed. Mine is 3.13, which is above 3.10 or higher than 3.10, so that works. Now, to run Python, we're going to create a virtual environment. This is nothing but a container. This nothing like nothing but like a container in a Docker where we create something, an entity which is totally separate from the host machine. Just in the same way, we are going to create a virtual environment when I run Python or when I install any dependencies of Python, so that if I want to uninstall those dependencies again after I'm done with that, I can just delete or remove that environment, the virtual environment that I'm going to create now, and everything, all the dependencies that I installed inside that virtual environment will be gone with the environment itself. Now I'm going to copy that, paste it here, but this command should be run inside our repository that we created, the Kafka lab. This will create a virtual environment inside the repository. This might take a few seconds. And if it returns nothing and asks you for another command, that is how you confirm there is this folder got created. This virtual environment got created. You see that? Kafka env. So the virtual environment got created successfully. Now what we do here is, if you use Linux, you use this command. If it is Windows, it is this command. Mine is Windows, so I'm going to say Kafka env. Activate. And like that, now our virtual environment is activated. Now anything we install here will be inside this environment itself. No, you don't go outside the environment. Okay, that is clear. Now here we install this in the virtual environment, like I said. Okay, pip install Kafka Python. We want Kafka Python to be installed in our environment to actually connect to the Kafka. So that is installed. The next step is create a file with producer.py as name. Let's do that. Go to VS Code Editor and create a file here. Name it producer.py. Now paste the exact code, right? Paste the exact code in the code editor. Now make sure about the extra spaces, but Python doesn't care about these extra spaces anyway. It cares about the indentation, these spaces. If you're not sure, if you're not familiar using Python, I recommend you to check out my masterclass on Python for data engineers, which will be a 10-hour video. By the end, you will know how these things work, the indentancy and everything. Everything will be included in that masterclass. If you're new to Python, go check that out. So Python doesn't care about those spaces, so those won't trigger any errors. It only cares about this indentancy. Well, it is not changed, so this looks fine. Now what this code does is, it imports Kafka. Now from Kafka, it imports Kafka Producer. If it is a consumer, we import Kafka Consumer, but now we are initializing or defining a producer, so we import Kafka Producer and say producer equals Kafka Producer, and inside the parenthesis, we configure that producer. First, with this bootstrap servers, we configure the bootstrap server where we have to connect to Kafka. Since I am running this on my host machine, which is outside the container, I have to connect through this port. And I'm using AC case as all, which we already talked. So this makes sure the writes are confirmed on all the replicas. And then retries. If it is fail, retry for 5 times. Enable idempotency. No duplicates. So idempotency equals true, there will be no duplicates. That is how we confirm it. Now, producer.send of orders. So producer.send of, this should be the topic name, orders, comma, B of B codes order created. So this is the part which this is the only part that we're going to send as a message, as an event. But what is this means? We are defining it as a byte. Here's the thing. Whatever the message that you send through Kafka should be in bytes, should be encoded in bytes. There are a few methods to convert a message into bytes. This is one of the method. This is not reliant, but if it is a small message, you can use this method to convert that string or anything into bytes. Now here using as B, we just define B right next to that order created. So we are configuring it as bytes. By the way, this will be converted to bytes before it enters Kafka. So this is handled by Python itself. So we're converting this into bytes. Now producer.flushoff make sure all the data, all the produced data is reached before we run producer.close, which closes the producer. So it makes sure everything is flushed, every events are sent in the right way, and then it closes. These are all best practices. Let me tell you what. You don't need all of this. If you just want to send a message and you don't care about any of these best practices, the only code you have to use this to send these messages, let me show you. Take these things off, these two things off too. This is the only code you want if you want to just send that message and doesn't care about any best practices. But like I said, the producer should be configured in the right way when you work on a real project. So it makes sure everything goes correct. And that is why these configurations work. Without these configurations, the producer still works, but there are a lot of consequences that you may face when you work on a real system without using these best practices. That's how it works. Okay, now we have the producer. What's next? Now run the producer. To run the producer, we use Python to run it. First save this using Ctrl S. Now head to the terminal. Here, say We're already inside our repository that we created, which is Kafka Lab. And our Python producer.py file is inside that repository. To run that in Python, we say Python producer.py. When I hit enter, this will emit that event, and the event will be sent to the log, to the topic, which is orders. It don't give you any confirmation, but if that doesn't generate any error, that is how you confirm the data is sent successfully. You can include logs like printing some statements saying message sent or event sent right under here somewhere to use it, but just to show you, this lab is just to show you how these configurations go together and how producer works. That's why this is a simple one. Now this is sent. What's the next step? Expected behavior. Script exists silently, like it did. No output. Yes, for sure. Event is returned successfully. Silence here means success. Verify the message. Enter Kafka container. Okay, we enter the container again. Well, I'm already in the container, so I'm not going to enter again. I'm just going to run this command instead right away. So we're running the consumer again, right? But here we're not creating a consumer group. We haven't configured a consumer group here like the last time. Remember, what was our last command for the consumer? So for our last command, we also defined this group as order consumer group. So we define the consumer, but here we're not going to define the consumer. Now what happens if we run this is Kafka will temporarily create a random group name with a random consumer group name, and after this the consumer is stopped after this executed and read all the the messages or the events, that group ID will be gone. So there are no offsets created. If you don't configure a group ID here, there will not be any offsets created for that group ID, and group ID will not disappear after this consumer consumes all the events. Let me show you in practice, okay? I copied this using copy. Now I run it here. All right, run it. Okay, it did consume the messages. If I go to the UI and hit on the consumer, I will see the consumer group ID, a random consumer group ID created, right? It has number of members, number of topics, coordinator, everything is created. Everything works fine. And the output in the terminal also shows the new order that we just produced, which means the producer worked fine, and we got our new produced event, which is order created. Now, when I exit this consumer using Control C, exited the consumer. Now, what happens is the consumer group will automatically vanish. It takes a few seconds, but it will vanish. Oh, this will vanish, but it takes a few seconds, all right? We will come to that later, okay? But that is how it works. There won't be any offsets created for that consumer. It acts like a temporary consumer. It gets into that, consumes the data it wants, and it goes away. If it crashes out in the middle, it cannot get those. It is not secured enough to get those data back again, or the offset, or start from the same offset, because the offset is not stored because the group ID is not created. That is one of the topic I have to talk about. And then, yep, order created is there, and then that is done. What producers do and do not. Producers do write events. They write events, of course. Choose partitions, sure. Control durability and latency, right? Producers do not track consumers. Yep, for sure, because they are asynchronous. They are not related to consumers in any way. Manage offsets. They don't manage offsets because consumers do. Guarantee downstream processing success. They don't guarantee the downstream. They just sends the data. They just emits the data and confirms if the data is reached according to our configuration. The final technical takeaway: producers decide how safe your data is before it even reaches Kafka. Durability, duplication, and latency are producer side decisions, and hard defaults here create irreversible damage downstream. So you make sure when you work with the real system where you're serious at, to make sure to create all these uh, configurations that are necessary. You don't just leave the configurations to default configurations. Okay, you have to make sure to configure it in the right way. That is it with this concept, the producers. Heading to the next concept. Now our next concept is consumers, which is 2.7. In Apache Kafka, consumer is a client application that reads events from Kafka partitions by tracking offsets. We all know that. Key characteristics of consumer is reads data sequentially from partitions in order. So it reads data in order, like we already talked. Maintains its own position using offsets, nothing but checkpoints. Decides when data is considered processed. It can also, according to the configuration, decide when the data is processed. Use a pull-based model. Kafka never pushes data. So it uses a pull-based model. Critical mental model. Kafka stores data. Consumer decides how and when to read it. We talked about it. Kafka is nothing but Kafka log. So it stores the data in the Kafka log, which will be in a topic or partitions. And consumer decides whenever it wants to consume the data out of that Kafka log. Why consumers exist? In real architecture, in idempotent processing across systems. In real architectures, the same event stream is often needed by analytic systems, monitoring and alerting, search indexing, fraud detection, notification. Each system processes data differently, runs at different speeds, has different failure characteristics. So consumers solve this by tracking their own offsets, operating independently of other consumers. So no system blocks another, no coordination required. So they all work independently, and that is what makes them applicable to all these applications that we talked: analytic systems, monitoring, and the rest. Controlled processing semantics. Kafka deliberately makes no assumptions about whether processing succeeded, how long processing takes, whether processing must be ordered across systems. Instead, consumers explicitly control when to read data, when to commit offsets. We can configure them. This design keeps Kafka generic, scalable, suitable for many workloads. Failure tolerance and recovery. Failures are normal. Consumer crashes. We cannot control it. But what we can control is to recover the data that lost. Application restarts, deployments happen. Because consumer track offsets, they can resume from the last committed position. Because of the offsets, they are saved. The positions are saved. Avoid unnecessary reprocessing. It doesn't go to the top again to reprocess again. Recover deterministically. This is why Kafka consumers are stateful by design. When to use consumer and when not to use. You need asynchronous processing. Multiple downstream systems exist. Uh, processing speed varies per system. Replay and recovery matters. Common examples include the same analytic pipelines, notification service, fraud detection engines, search indexing, data enrichment pipelines, all this. Do not expect consumer to behave like webhooks, push-based APIs, one-time task executions, short-lived bad jobs. They're not. They're like streams. They're not bad jobs. Kafka consumers are designed to be long-running, stateful, continuous polling systems. If you need fire and forget execution, Kafka is the wrong abstraction. Now, coming to the conceptual diagram, let's head to the presentation again. Duplicate this slide, name it consumer. And because we want this consumer to be on the other side, we just copy these things and drag it to the other side of the slide like that. We need this thing should be here and rename this as consumer. Keep it aside. Arrows, the direction of arrows doesn't change. What changes is consumers can read from multiple partitions, but not at the same time, right? So it can read from multiple partitions. So consumer can have multiple offsets for multiple partitions. Let's say the offset here can be 1. Okay, and the offset for this partition can be 5, and the offset for this partition can be 0. It may never have read yet. Okay, you know that, right? For every partitions there are their separate offsets. Offsets are not global throughout all the partitions in the topic. Every partition have their own offsets. For example, for partition 0, the data in partition offset start from offset 0. Let's say there are 5 events stored in partition 0, then the offset starts from 0 to 4. And at the same time, if the partition 1 has another 6 records, that partition 1 offset start from 0 to 5. It is not global. Offset is uh, you know local for every single partition. They all have their own partitions. I mean, they all have their own offsets for the data. So this is perfect to represent that. Now let's take a screenshot like that. And go to pictures, screenshots. Perfect. Now lab, Python consumer from 0. Kafka and Python environment already exist from producer lab. We already have that, right? Python environment and everything exists already. If you deactivated it, activate your environment again because we're going to use it. Ensure this is installed. We already installed it. Now create a file named consumer.py. Perfect. And the code is this. Now we're defining a consumer. All right. From Kafka, like I said, for producer, we import Kafka producer. For consumer, we import Kafka consumer. We import Kafka consumer here because this is a consumer code. And then consumer equals Kafka consumer. And these are the configurations. The first one will be the topic from which the consumer gets the data from, which will be orders is our topic. Next one is the port, the listener port, which is this. Now, this configuration says to listen to no, sorry. So for auto offset reset, there are a few methods. There are 3 methods, namely they are, first one is earliest, and there is latest, and there is none. So what earliest does is, now what latest does is, by the way, if you never configured this line, let's say if you never configured this line at all, if you say this, by default it takes latest as the configuration here. Okay, so it takes latest. What latest means is, if you start consuming the data and before you start this consumer, if the Kafka topic already has the data in it, before you start this consumer, the consumer will avoid the past data. It only focus on the latest incoming data. That is how it works. And then whereas earliest is, it goes to the, I think it goes to the, wait a minute. Okay, now, so latest is, I already told you, it just reads the data from, it ignores the data that is already, present in the producer. It only focus on the newly upcoming data. Whereas earliest is, if there is no offset at all before you run this consumer, it just starts from the first record of that topic or partition, or yeah, let's say topic. So it starts from the first event from that topic. If there is any offset, it starts from that offset. If there is no offset at all, it starts from the very beginning of the topic. Whereas none raises a failure or error if there is no offset at all. But if there is already an offset before for this same consumer, and when you run it, if there is an offset, it starts from that offset. If there is no offset at all created before, it just pops an error. It triggers an error. So that is how these 3 auto offset resets work. Now for now, we're going to do earliest. If there is no offset, go to the first record or first event of the producer, or if there is, just start from that offset. That is what we're saying here. Now enable auto commit is nothing but right when it consumes the data, it commits the offset before it is processed before it is even processed using this. So before even running this command, right after it consumes the data, it commits. That is what it says. It auto commits right after that. If we state this thing as false, it won't commit until we manually commit the offset after we process whatever the data, whatever the process we want to do, and then use commit here instead. That is how enable auto commit equals true work. So I will show you an example where we say auto commit equals false, then you will understand more about this. Now let's save it. And then what? Key configuration explanation. Start from the beginning if no offset exists. The same thing that I explained. Kafka commits offset automatically right after it consumes the data. Now run Python consumer. Okay. You see that? By the way, the temporary consumer group that is created is not here anymore because it is temporary. It is gone. Now let's run this again. Now let's run the consumer now. Python consumer.py. You see that? That's how it works. That's how the consumer works with Python. Previously consumed message are not read. The consumer resumes from its last committed offset. This behavior exists only because offset exists. Kafka did not remember messages. The Kafka consumer remembered its position. So if we stop this, so it still reads those messages because we haven't defined any consumer group. So there is no offset created by default. But if we create a consumer group, if we define a consumer group, let's say group ID equals, and I name a group ID as consume orders. Save it. Now if I run this, stop this first and run it. I forgot the comma. Okay. So I forgot the comma here. Okay, now let's run that again. You see that does now that did consumed. Now if I stop the consumer using Control C, interrupt it. Okay, and now run the consumer again, because now we did created a consumer group which is consume orders, right? And it does have an offset now. If I run this again, it will not produce any events because the offset is already set, and the offset is set to the latest event already, and there is nothing else, no new events that are emitted. So there will not be anything printed here. That is how offsets work for the consumers. Think you got that concept. Now I'm going to stop it using Control C as well. Control C, interrupted. Okay, that is done. Heading back. What consumers do and do not. Consumers do read data from partitions, track progress using offsets. I already demonstrated it. Handle failures and restarts. Consumers do not receive pushed messages, delete data after reading. They won't, like the traditional APIs. Guarantee business level processing success. Kafka jobs is delivery and storage. Processing correctness is the consumer responsibility. And the final technical takeaway is Kafka consumers are stateful, long running processes. Offsets are their memory, defining progress, recovery, and independence. If you misunderstand consumers, you will design brittle pipelines. With that being said, I will also add this line of code in the lab. So when you run it, you will remember that. Like that, much formatting. Perfect. With that, we're done with this concept, consumers. Now let's head to the next concept, consumer groups. We are also familiar with consumer groups because we already talked about consumer groups when we talked about partitions. Now let's dive deep into it. In Apache Kafka, a consumer group is a set of consumers that coordinates to read a topic together. So a group of a consumer group will be assigned to a topic. So all the consumers in that consumer group read all the partitions in the topic in a coordinated way, where each partition is assigned to exactly one consumer within a group. A partition is read by only one consumer per group. Multiple consumers share the workload. Offsets are tracked per consumer group. Consumer groups are Kafka's unit of parallelism. Think of consumer group as one logical reader implemented by many processes. These are all topics we already covered, but there is one thing I have to say about. Yeah, a partition is read by only one consumer. What that means is, in a consumer group, uh, when a consumer group is assigned to a topic, a partition in that topic, one partition will be assigned to only one consumer in that consumer group, and it will not be assigned to multiple consumers at the same time. Only one partition, only one consumer in the consumer group will be assigned to one partition. But multiple partitions can be assigned to one consumer, but one consumer cannot be. Now I don't know how to okay, let me keep it like this. Multiple partitions can be assigned to one consumer in the consumer group, but multiple consumers cannot be assigned to one partition. Should be one partition. One partition should only be assigned to one consumer in the consumer group. That's how the relation goes. I think the statement is correct now. Okay, why consumer group exists? Scaling consumption. A single consumer reads sequentially, has finite throughput, become a bottleneck as volume grows. They all talk about the parallelism, all these points. Consumer groups solve this by allowing multiple consumers, splitting partitions across them, enabling horizontal scaling. I already explained it. That's how they divide the task equally between the consumers in the consumer group and make it faster. Preventing duplicate processing. Without consumer groups, Every consumer reads every event, work is duplicated. Downstream systems waste resources. If you want to do this same parallelism with multiple consumers without consumer groups, the data will get duplicated, and that's why consumer group exists. And because we make sure every partition is only read by one consumer in the consumer group, the data will not be duplicated. That's how consumer groups work. The logic, I think you got the logic, right? You just, if you don't get it, just move back, just rewind back a few seconds and listen to those statements that I just said. One partition to one consumer, only one consumer, but one consumer can be assigned to multiple partitions in a consumer group, by the way. Fault tolerance via rebalancing. If a consumer crashes, it's stopped, loses connectivity, Kafka automatically detects the failure, reassigns the consumer's partitions, continues processing with remaining consumers. Let's say a consumer in a consumer group crashed. What Kafka does is the partitions that are already assigned to that crashed consumer will be reassigned to the other consumers in the same consumer group and make sure the task, those partitions are consumed. No manual intervention, no data loss. Everything is handled by Kafka. Temporary pause is normal, permanent failure is not. When to use consumer group and when not to. Use consumer groups when you want horizontal scaling. That's one point. And then processing is parallelizable. Each event should be processed once. You don't want any duplicates. Typical examples: order processing systems, log ingestion pipelines, stream processing application, ETL system consumers. Do not use single consumer group when every system must see all events. Then you have to use multiple consumers with multiple consumer groups. That is the only way. Examples: analytics, monitoring, alerting, auditing. In these fan out scenarios, use multiple consumer groups, one group per downstream system. Rule of thumb. Okay, when you think about consumer groups, you should not think about consumers grouped into multiple. Let's say, when you think about consumer groups, you should not think about multiple consumers, separate consumers grouped together. You have to think about it is just one consumer. I mean, what to say? Not sure. So yeah, you don't use consumer groups to consume the data from multiple, what to say, uh, multiple topics at the same time. You use one consumer for one topic, one consumer group for one topic. You cannot use half of the consumers in the consumer group to one topic and the other half to another topic. One consumer group should be assigned to one topic, and those the partitions in that particular topic will be separated or distributed throughout the consumers in the consumer group. That is how the logic goes. Now, coming to the conceptual diagram, let's head to the PowerPoint slide, duplicate this. I'll leave this thing like that, but what I'm going to do is just going to take this out and extend this a little bit like that and say copy this here. consumer A, and consumer B. This whole thing is a consumer group, and this whole consumer group is assigned to one Kafka topic, right? So this whole consumer group is assigned to one consumer topic, but the partitions will be distributed across the consumers in the consumer group. And remember the relation I said? One partition should only be assigned to one consumer in the consumer group, but sorry. Yeah, is that right? Yeah, multiple partitions can be assigned to one consumer in a consumer group, but multiple consumers cannot be assigned to one partition. That should be the relation here. To actually represent it, what I'm going to do is, I'm going to assign partition 0 to consumer A. Say offset as 1, that's fine. And then I'm going to assign the partition 1 to consumer B. Offset is 5, that's still fine. What next is offset 0, I'm going to assign it to consumer A. Now you see the statement, how it works, right? Multiple partitions. Here in this case, partition 0 and partition 2 are assigned to one consumer, which is consumer A in the consumer group, okay? But multiple consumer groups cannot be assigned to the same partition. That should be the logic. Because that doesn't make any sense. If multiple consumers in the consumer group is assigned to same partition, that doesn't make any sense. That's how the logic goes. That is it. Now, yeah, take a screenshot. Head back, paste it here. Okay, the key points, one partition, one consumer. The same thing, I repeat that again and again. No duplication inside group. Now, lab, running multiple consumers in one group. Kafka and Python environment already exist, right? We already have that environment ready. Now create this file again, group consumer.py. And for the code, copy paste this. Wait, this is the same thing. No? Oh, okay, I got it. So what we're going to do is we're going to save this. And then what? Run multiple consumers now. Within the same consumer group, we are going to run two consumers, okay? Let's run that. Within the same consumer group, which is orders processing group. Did I still already created that orders processing group? No. So I'm going to run two consumers within the same consumer group to show you how the consumers work. Now let's go back to PowerShell, and I'm going to open two PowerShells at the same time to run two consumers at the same time. cd Kafka lab. Kafka env /script/activate. So in both the PowerShells, both the terminals, I did open the environment. Now what I'm going to do is I'm going to run the same code twice. So that I create two consumers in the same consumer group. Copy that name. No, why would I do that? I can just copy this. Okay, in the first terminal, I run it. Now it did got the orders from that producer, from that, sorry, Kafka topic, which is orders. Now if I run the same thing again in a different terminal, you don't get any, because all the partitions are already assigned to this consumer, right? So this consumer, the other consumer that I just opened will not get any partitions left to be assigned. And because of the rule, one partition should be assigned to only one consumer in the consumer group. This will not be allowed. And if you go to the UI, and which is this, you can actually see the number of consumers in that consumer group. Number of members equals 2. You see that, right? That's how you say how many consumers are in that consumer group. Okay, I'm gonna stop this. End this as well. That is good. You now have two consumers in the same group. Oh, my bad. My bad. Okay. Okay, my bad. I was have to do that again. Okay. Now I already created that group, the consumer group. What I can do is I can just delete the group. I cannot do that from here, UI. I can delete it, but you know what? I just run it. I don't delete it. But you know, right? For now, the consumer already has the offset. This consumer, this particular consumer. I don't know how. I think I have to delete the consumer group. Let me delete it. Okay, this is the command to delete the consumer group. I'm gonna delete it. And the consumer group name is this. Now with this command, I'm just deleting the consumer group that I created. Okay, paste it. Yep, now I deleted. Now let me run that again. Okay, go back here. Now what should I do? So I have to run this in both terminals. I have to run this. So let's do that. I'm gonna run that here first. Because we deleted the consumer group, the offsets are also deleted. Now this is a fresh consumer group. That's why it consumes again. Now I'm going to run the same thing in the terminal again. Oh, in this terminal again. But this one doesn't get any partitions left because all the partitions are already assigned to that consumer, to this consumer. Now what's next? You now have two consumers in the same group. In another terminal, run this command. So now what we're going to do is we're just going to add a few more events using producer console. Copy. Okay. Oh, there's something wrong. What is it? Now copy, paste it here. I'm going to now send those events from 10 to 13. Okay. Order 10, order 11, order 12, order 13. I did send it. Perfect. Now you see that, right? Because we have two consumers in the same consumer group, when we run this, because we run this first, this consumer first, this consumer got assigned with the partition where all these messages are stored, which will be which partition? Let me open the UI, topics, orders, which will be partition 2 and partition 1 are assigned to the consumer. So the partition 1 and partition 2 are assigned to this consumer, and the partition 0 is assigned to our next consumer, this one. Now how I know that is, if I switch to messages and check on the messages here, you can actually see for this first consumer, let me like that, for this consumer, I got these messages, I consumed these messages, which include order created, which is this one, and order 1, 2, 3, 4. Right? All these 5 events belongs to, let me minimize them. So these 4 events belongs to partition 2, and this order created belongs to partition 1, which means these two partition 1 and 2 are assigned to the first consumer that we started, and the rest of these 4 messages are part of the partition 0, and that partition is assigned to our second consumer that we created, and that's why only those messages are consumed by this consumer. That's how the partition assignment work for the consumer group. I think you got it. And by the way, you look at that. There are 3 partitions, right? And for all the 3 partitions, the offset or resetted. For this partition number 2, the offset starts from 0 to 3. And for this partition, which is 1, starts from offset 0. And for this partition 0, it starts from 0 and ended at 3. That is another point that I told you I'm going to prove. I'm going to demonstrate. That is the demonstration as well. And that's it with the consumer group demonstration. The lab, basically, that's how we demonstrate it. We're done with that. Now, what else? Key constraints, you must remember, maximum parallelism equals maximum number of partitions. Max consumers than partitions, idle consumers. Rebalancing causes temporary pause. Partition count is a capacity decision, not a cosmetic one. Final technical takeaway. Consumer groups enable parallel processing without duplication. Kafka scales consumption by dividing partitions, not copying data. If you misunderstand consumer groups, you will either underscale or accidentally double process the data. This is the final takeaway. Okay, with that, we're done with this concept. Let's head to the next concept. Now, our next concept is internal components. Now, for the code definition, we have in Apache Kafka, internal components coordinate to store data, replicate it safely, and ensure the cluster continues operating despite failures. Now, here in this concept, we're going to talk about the brokers and the controllers, like I told you before, and the partitions, how the leaders and followers work. The core internal components are brokers. Brokers are the Kafka servers that store and serve data. It can be this PC or it can be this container that I'm running. And the controller, the broker responsible for cluster-wide coordination. I already talked about this, right? One broker from the group of brokers or from the given brokers will be selected as a controller, and the controller will be responsible for cluster-wide coordination, the replication and stuff like that. So that is what controller does. It manages that. And then partitions, which are ordered logs that hold data for a topic. We already know. Leaders, the authoritative replica for each partition. So that has the authorization. So if you have 3 partitions, the leader is the one which have authorization for the replicas. And the followers are replicated copies that provide fault tolerance. If there is any fault happened to the leader, follower will take the role of leader in case of any tolerance or in case of any fault. That is what it says. Copies provide fault tolerance. Kafka's reliability does not come from single component. It emerges from control responsibility separation across these roles. Broker, what is a broker? A broker is a single Kafka server instance. Each broker is responsible for storing partition data on disk, serving read requests from consumers, of course, handling write requests from producers, replicating data to other brokers, participating in cluster coordination. Brokers are stateful. Broker holds some partitions as leaders, some partitions as followers. Brokers are symmetric. Any broker can become controller. Any broker can host leaders. Get that point right? Any broker can be a controller. Any broker can host leaders. Leaders are nothing but the authorized partition in a group of partition replicas. What brokers do not do? Brokers do not execute business logic. Brokers do not coordinate workflows, do not interrupt data meaning. And now what is a controller? A controller is a special broker role, not a separate service. It is a broker role. It is assigned to the eligible broker. Exactly one broker is active controller. All the other brokers act as standby controllers. The controller is responsible for tracking broker liveliness, managing topic metadata, assigning partition leaders. So controller is the one responsible to assign the partition leader and to decide who will be the partition leader and who will be the follower. Controller will decide that. Assigning handling broker failures, triggering partition leaders re-elections. These are all internals. We don't see them. We cannot demonstrate them to see with a lab or any other code. These are all internals that happens behind the scenes. But you have to know about these concepts. Controller election. In modern Kafka, KRaft, like I said, KRaft controls the controller election, whereas in old Kafka, ZooKeeper controls that. ZooKeeper is responsible for the controller election. In modern Kafka, Controller election is handled internally, no ZooKeeper is involved. A quorum of controller-capable brokers participates. One broker becomes an active controller. All the brokers that are capable will participate. Only one broker will get the controller. Others remain standby. If the active controller fails, a standby is automatically promoted. We already talked, right? If the active controller fails, the standby will get the control. So that is also part of fault tolerance. Metadata consistency is preserved. The cluster continues operating. But if we only have one broker, like as in this case, in our case, we only created one container. So if that container closed or got interrupted, it is done. Everything is done. But if you have multiple containers or multiple brokers running, even if this is a controller among all the brokers, this is an active controller. If this PC or system goes down, the rest of the brokers take control. So the process will still go on. Active versus standby controllers. Active controllers execute cluster decisions, update metadata, handles failures. Standby controllers stay synchronized, do not do nothing unless promoted. They do nothing. They are just replicas. They just synchronize with the controller broker. Exits purely for fast recovery. Now partitions. We know about partitions, so I'm going to skip that. Partition leadership. Exactly one replica is the leader among the partitions. Replica among the partitions that are replications. All writes go to the leader. All reads are served from the leader. Okay, all writes go to the leader first and then replicated by the followers later, and all reads are served by the leader too. So leader is the main head of the remaining rest of the replicas of the same partition. Follower replicas replicate data from the leader. Replicate data from the leader. Do not serve reads or writes. They do not serve unless the leader goes down for any reason. Exit solely for fault tolerance. In sync replicas, we already know. Replication, how Kafka prevents data loss. For partition with replica factor 3, one leader, two followers. For a partition with replica factor as 3, the partition is replicated into 3 partitions. One partition is replicated to 3 partitions. Now, one of those partitions will be the leader and the rest of the 2 will be the follower. And we already know what privileges or what role it plays, the leader plays and what follower plays, right? Why replication exists? Replication solves broker cache crashes, disk failures, network partitions. We know all of this. What Kafka is not doing, conceptual diagram. Wait. You know about leader follower, how all components work together. We talked about it as well. What Kafka is not doing internally, load balance message. You know what? Let's just go to the conceptual diagram right away. Go to the slide. This is going to be a big diagram. I'm going to name it components. And take all of this out. We don't need that. This one too. I'm going to name this as broker 1. Take this out. Perfect. Extend the length. Same with this. Okay. copy this to the bottom here. And then for this, say topic users. So now I'm representing a broker, which is broker 1 with 2 topics in it. First one is topic orders, and the other topic is users. And they both have 2 partitions, partition 0, partition 1, partition 0, partition 1. What I'm going to do is, but name this as follower, leader, follower. Copy paste this as broker 2 right here. Copy paste this as broker 3 right next to it. This should be segregated in the right way, or else it won't fit. Okay, if I just move it a little bit like that, and perfect. This will be broker 2. Now we replicated all the partitions in broker 1 to broker 2 and broker 3, right? All right. So for every partition, we have 3 as a replication factor, which means every partition has 3 replications, but only one of those replications will be the leader, right? For partition 0, this one will be the leader, the rest should be the followers then. This should be follower, this should be follower too. And here as well, this is leader, so this should be follower, this should be follower too. And for the rest of these 2 replications, I'm going to say this as leader, and here this as leader. And like I said, the leaders are elected by the controller broker. And here this will be the controller, which is in active state. And this is also a controller eligible broker, but this will be a standby. This will not be active. All right, so active controller decides which partition should be a leader, right? And it decided for partition 0, this partition will be the leader and the rest will be the followers. And for this is the leader. For this is the leader. And for this partition, this is the leader. Now, if broker 1 goes down, For partition 1 in topic orders, uh, in the orders topic, partition 1 is not affected by that because it is just a follower partition. The leader is at top broker 3, so that doesn't care. Whereas in partition 0 of users, that is also follower, so that doesn't care as well. But whereas in partition 0, the partition is itself the leader. So if the controller goes down, the next eligible controller eligible broker, which is this one, controller standby, will take the role of the active controller, and then it assigns the leader to one of these two for this partition 0 in orders topic, to one of these two topics. Let me draw it. So after it take the role, the controller role, the active controller role, it gives the leader role to one of these two partitions, either this or that, according to which is eligible the most. And then the same thing, this one here, topic partition 1 for topic users also has the leader. If this broker goes down, crashes, this role, the leader role for this partition, will also be given for this one or this one. That's how it works. Now let me just erase everything. Okay, take a screenshot of it. Oh, I think I am running out of energy. Okay, so that is the conceptual diagram. We are done with that. Final technical takeaway. Kafka's internal design follows a strict philosophy, one leader per partition. I already talked about it. Many followers for safety, one controller for coordination, many brokers for scale. That is how it works. We don't necessarily have to have all those replicas, but if we have those replicas, we have all these advantages: fault tolerance. If anything crashes, we can have the backup, something like that. We don't lose the data, or we don't break the pipeline. So that is it with that topic, that concept. Heading to the next concept, which will be the phase 3, working with Kafka. Okay, our next concept which is our phase 3, working with Kafka. Our next concept is Kafka CLI Tools. And by the way, I think it is already a big masterclass. Now I'm going to make the rest of the concepts faster. I'm going to explain them faster, but make sure I'm clear for every concept, okay? Starting with the Kafka CLI definition, Kafka CLI, command line interface tools, are built-in command line utilities provided by Apache Kafka to administrator, inspect, and interact with Kafka directly. Without writing application code, these tools allow you to create lists and describe topics. Create list and describe topics, which we already done using the CLI, right? So this is basically the CLI that we used. Without writing any code, we did created a producer here, and we did consume the data as well, and we did described as well. So that is what we're talking about here, the CLIs. So we can create list and describe topics, produce events manually, we did, consume events directly from topics, which we also did already, inspect offsets, partitions, and consumer behavior. Debug Kafka at lowest possible level. Kafka CLI tools communicate with Kafka exactly like real clients do. There is no abstraction layer. Why CLI tools exist? Graphical user interface hides Kafka fundamentals. Graphical tools often abstract away partitions, hide offsets, consumer position, suppress or soften failure signals. Like I said, if we use CLI, command line interface, we have more control than using UI. That is why it is necessary. And when it comes to Kafka, it is mostly mandatory to use CLI instead of using UI. You cannot use UI basically. You can, but yeah, it is like more like mandatory to use CLI when you deal with Kafka. This leads to superficial understanding, false confidence, poor debugging instincts. Kafka CLI tools force you to see raw topic and partition behavior, observe offsets and ordering directly, read failures instead of ignoring them. Think in Kafka's native mental model. If you can't explain Kafka from CLI, you don't actually understand Kafka. And by the way, like I already said, anyone cannot remember all the CLI commands we use to interact with Kafka, but according to the situation or error or anything you are in, you just go to Google and search for that appropriate command that you have to use in that CLI, or else you can ask any language model like ChatGPT to get that CLI command. Debugging Kafka without application code. When someone breaks, the first question is not, is my application buggy? The first question is Kafka behaving correctly? Kafka CLI tools lets you produce a known text event consumed directly from a topic, validate brokers, topics offsets, isolate Kafka from application logic. So if we do this from CLI, so we can make sure the topic is actually working, right? No, there is no, the bug is not with the Kafka. It is something with the code that we used in the external, let's say .py code or something. So that is how we can debug it. This removes ambiguity. No frameworks, no SDKs, no excuses. Operational reality in real times. In production environments, SSH access exists. SSH means nothing but the CLI. In production, to actually communicate with a virtual machine, right? In production, we don't get any fancy UI with this PC, right? We have to work with the CLI. That is the only way to communicate with the virtual machine. And the virtual machine will run on cloud. So SSH means that. Terminal access exists. Dashboards may be missing, outdated, or restricted. Kafka CLI tools are always present with Kafka. Version compatibility with the cluster, trusted by operators and one-call engineers. Every serious Kafka incident is debugged from CLI first. When to use and when not to use Kafka CLI tools. Use Kafka CLI tools when learning Kafka fundamentals, debugging production or pre-production issues, validating cluster behavior, demonstrating Kafka concepts clearly. Common uses, topic creation and inspection, which we did. Offset and lag analysis, which we already did, that one as well. Replay testing, we haven't done. Verifying producer consumer behavior, we did. Now, heading to the lab, we don't have any conceptual diagram because this is about CLI. It doesn't make sense. So we go to lab, core Kafka CLI. This lab demonstrates direct Kafka interaction, not application development. Like we did before using these codes. This is about CLI interaction with Kafka. Topic administration. Now, these are a few other examples that we can use, but we already used this. We already ran this command, so we don't need to run that again because this command lists all the topics that we have. We ran this command, remember, to list all the topics that created. So that is that topic. What this proves, broker connectivity is working, Kafka is reachable, topics are first class entities. So if there is any error in your environment with your code or something, you can debug it using CLIs. So you can know the error is not with the Kafka, but the error is with the code that you configured the producer or consumer with. That is how you can use CLI as well. Console producer, Kafka console producer, topic orders. There's nothing but creating a producer. We already done it at the same CLI. But what to understand? Each time you type an event, no schema validation, no retries unless configured, raw byte level production. You know what happens when we run this, right? We just give orders to it. Let me show you. Right here. That is what we did here, right? We just opened the console, the producer console, and emitted these events into that. Okay, console consumer. We did that as well, using command line to consume the data out. Now, the practical rules you must internalize. CLI tools show truth, no convenience. If CLI behavior surprises you, your mental model is wrong. Every Kafka concept becomes obvious at the CLI level. Everything, every concept. Production outages are debugged here first. Any outages in production should be the debugging should start at the CLI level first and then go to the application level. Now, the final technical takeaway. This doesn't need any lab or any conceptual diagram as well. For the lab, we already done the CLI command, so we don't need that lab. It just wastes the time. Now, the final takeaway is if you don't know Kafka CLI tools, you don't know Kafka. Framework comes later, dashboard comes later. The command line interface is the foundation of all of this. You have to know about these command lines. That is it. That is it with this concept. Now, let's head to the next concept, 3.2. Our next concept will be 3.2, message keys. In Apache Kafka, a message key is an optional field that Kafka uses to deterministically decide which partition a record is written to. Remember when I said we can control where our events go to? This is the topic that I'm talking about. We can use keys to determine which partition my emitted record goes to, that I'm going to demonstrate in this concept. So stay tuned. Formally, Kafka applies a hash function to message key. Okay, the hash result maps the record to one specific partition. That is how a message is directed to that particular partition using the hash function. Same key, same partition. As long as the partition count remains unchanged, message key do not affect the message value or payload. It doesn't change anything. The message key doesn't change anything. It just defines to which partition that message belongs to. They strictly control partition placement and ordering guarantees. That is what I said. Now, why message keys exist? Like I said, if a message doesn't have a key, those messages or events will be distributed evenly or will be distributed throughout across all the partitions in a topic, right? And if you want to have a particular order for these events, you cannot because they're all distributed all over the partitions. So if you strictly want an order to be followed, you can define that particular data with a key. So every data that has the same key goes to the same particular partition. So all those, the events belong to the same key will be ordered in the same way because they're all stored in the same partition. That's how the message key works. Why message keys exist? Ordering guarantees. Kafka guarantees ordering only within a single partition. We know that. Never across an entire topic. Not across all the partitions in the entire topic. It only guarantees ordering in one partition. And that is why by using keys, we just store all the data that is related to that one single category using a key so that we can order them inside one single partition. Without keys, records are distributed in a round robin fashion. Round robin fashion is the method that Kafka works when distributing the data, the events that the producer produces to distribute across the partitions. Round robin is the method. Relevant events can land in different partitions. You see that? So relevant events can land in different partitions, which means all those relevant events cannot be ordered because they are on different partitions. Ordering across relevant events is lost. The same point I just mentioned. But by using message keys, solve this by forcing all events, all relevant events with the same key. We assign a key for all the relevant events, and the key will be the same for all the events that are relevant into one partition. So whenever you create another event and you want to relate, you feel like that event is related to that group of events that you already uh, assigned that particular key, you just give that event also the same key. I mean, you might feel hard to understand while I explain it with vocally, but when I actually demonstrate how these keys work, you will get the concept. Trust me. Now, example, user ID equals 42. All events of user 42 are returned to the same partition by just using a unique key for all the user ID, all the events that are related to the user ID 42. Order is guaranteed for that user, not for the whole topic. Kafka ordering guarantees per key via partition, consistent and not correctly processing. Many real-world systems require entity-level consistency, sequential state transitions, no concurrent updates for the same entity. Typical examples include order lifestyle events, account balance updates, inventory state changes, device telemetry streams. Message keys ensure all events for an event are processed by a single consumer. No race conditions across partitions. State updates remain deterministic. Without keys, correctness becomes accidental. Predictable and safe scaling. Message keys enables Kafka's core scaling model. Parallelism across entities, serial processing within an entity. This balance allows Kafka to scale through throughput without sacrificing correctness. Keys are the mechanism that lets Kafka scale safely, not just fast. When to use and when not to use message keys. Use message keys when ordering matters per entity. Event belongs to same logical identifier. Common key choices: order ID, user ID, account ID, device ID, something like that. Rule of thumb: if you care about correctness or order for something, it needs a key. You get it, right? The same point that I'm trying to say. If you care about the correctness or order for something, for some set of events, you need a key for all those to be assigned for all those set of events. Do not use message keys when events are fully independent. Ordering does not matter. Maximum throughput is the goal. Typical examples: logs, matrices. Logs, uh, we don't bother about the order of logs, right? So it doesn't matter. Matrices, traces, fire and forget notifications. In those cases, let Kafka distribute records evenly. Avoid articular hotspots, maximum parallelism. No key means no ordering guarantee by design. Conceptual diagram. Let's go to the conceptual diagram. Let's go to the slides again. Duplicate this. And no, not this. Let's duplicate this slide. Then I'm going to do take this down, change the heading as message keys. To the top. And let's copy this thing. Let's say user ID equals 101. For this text, I'm gonna reduce the size to 16. Another one, and another one. I'm gonna change this user ID to, let's say, 205. Now, if the producer produces the events and assigns a key, for every event, let's say for this event, if 101 is the key for these three events, this, and the last one, but for this event, the key is different. These are, it may, distribute through the partitions. What happens is the event with the same key goes to the same partition, like that. Because they should go, the event with the same key will go to the same partition, but the event with a different key can go to a different partition. This is how it works. Because the ordering is only guaranteed in one partition, these all events to go to one partition because they have the common key, but with this different key, it goes to a different partition, doesn't go to the same partition. That's how these message keys work. That's how we can control where our generated events go in those partitions. Okay, let's take a screenshot of this. Right there. Perfect. Head back to the document. Pictures, screenshots. Right there. Okay. Now the key points include key hash partition, ordering preserved per key. So the ordering is preserved for this key. So everything belongs to this key, which is 101, will be ordered in the right way because they all go to the same partition, and ordering is only permitted per partition. Now let's go to the lab here. What we're going to do is we're going to enter the Kafka container again. If you are already in the container, you don't have to run this first command. Straight away go to this command. Copy, paste it in a notepad, take out the extra spaces. Now what this command does is, here we are creating a topic which is orders. Wait. No, sorry. We're not creating the topic. What we're doing here is we are emitting the events to the topic orders. But while we emit the events, what we're doing is we also configuring the produced data with the property by parsing dot key equals true. We are saying the Kafka, my event does have a key, and with the next property we say key dot separator equals colon. So anything separated through this semicolon, no, the colon will be taken as key. That is what we're doing there. Now if I copy this, paste it here, run it. Now I'm inside this producer. Now I can produce the data. What I'm going to produce is, so order 101, order created, order paid, order shipped, order canceled, order created. Okay, let's do that. Say 101 colon order created. That's one message. 101 colon order placed. That's one message. I did send that as well. If I refresh the UI, you see that under the messages, these two which have the same key went to the same partition, which is partition 2. Now whatever I create with the key 101 will go to the same partition, which will be the partition 2 here, the same partition. That's how these keys work. Now let's say if I create an other event with a different key, which will be 205 colon order created. This might go to a different key as well, different partition as well. Let's see which one it chooses. Oh, well, it did choose in the same partition. What we can do here is, what I'm going to do here is I'm gonna stop this producer now, paste the producer again. So it chooses a different partition this time. Okay, now I'm going to use 206 as a key now. Okay, and say order created. If I refresh this, now this went to a different partition, right? It went to the partition 0. That's fine. But if I create another order, other event with 101 as the key, we already defined that key before, and say order shipped and enter. This key definitely goes to the same partition which already assigned to that key, which is partition 2. So if we refresh this, you see that, right? 101 went to the same partition 2. Even the event that is before that is produced before this event went to partition 2, but this event still went to the partition, sorry, even the event that is produced before this event went to partition 0. This event still went to partition 2. That is how we can control which data can go to which partition. So we can make sure that particular type of event have the same order. That is how the message keys work. Perfect. Now let me close that producer, and observation goes to the different partition. That's the same thing. Practical rules you must internalize. Kafka ordering is partition level, enabled by keys. Message keys define data integrity, the data locality. Consumer don't enforce correctness, keys do. Scaling without keys risks correctness. Bad key choice is worse than no key. So you have to choose the key the right way. In this case, we chosen the user ID as a key, user ID 101 as a key. So you have to pick the right key for the right situation. Final technical takeaway: message keys are the foundation of Kafka correctness. They decide where data lives, who processes it, what ordering guarantee you get. Bad key choices lead to broken system. No key means no ordering. Kafka will not save you from poor key design. That's it with the concept message keys. Now let's head to the next concept, 3.3. Beginning with the next concept, which is 3.3, serialization. The code definition of serialization. Apache Kafka serialization is a process of converting structured data into bytes. We talked about converting data into bytes, right? When we produced, when we emitted the events using producer, we did use this B. Why? Because Kafka only reads bytes. It cannot read syntax, or it cannot read integers or strings. It only reads bytes. It only reads the message or event in bytes. In Apache Kafka, serialization is the process of converting structured data into bytes. Serialization is nothing but converting a structured data into bytes so Kafka can understand. So Kafka can store and transmit it. That is what the basic concept of serialization. Key facts you must internalize. Kafka does not understand formats like JSON. You cannot directly send the JSON formatted event, Avro, or protobuf. They're all file formats, by the way. Kafka brokers only store byte arrays. Producers serialize data before sending. Producers, the responsibility is on producer. Producer have to serialize the data before they send it. They have to serialize it into bytes. Consumer have to deserialize the data. This is the role of consumer. Consumer has to deserialize the data after reading. Kafka never intercepts, validates, or interprets message contents. It cannot read the messages. If you send the bytes, it just transfers it. That's the only job Kafka does. Serialization is in your hand. It's not formatting detail. It is a data contract between producer and consumer. Why serialization exists? Kafka store bytes, nothing more, nothing else. Kafka brokers do not inspect message payloads, do not validate schemas, do not enforce structure on types, nothing. Without serialization, data cannot be transmitted meaningfully. Consumers cannot interpret payloads. Kafka becomes unusable for structured data. Serialization defines how data is encoded into bytes, how those bytes are decoded later, whether data is interpreted at all. Kafka is passive storage. Data evolution over time. Real systems changes, fields get added, fields get removed, or data type evolve. Without a serialization strategy, producers break consumers. Old data becomes unreadable. Backward compatibility fails silently. Your serialization choice determines whether schema evolution is possible or not. How painful future changes will be, whether historical data remains unusable. Most Kafka failures are serialization failure in disguise. Cross language and cross system compatibility. Kafka ecosystems are rarely single language. Python producers, Java consumers, stream producers, analytic systems, it is diverse. Serialization enables language agnostic data exchange, consistent interpretation across systems, decoupled producers and consumer life cycles. Without serialization, discipline Kafka becomes fragile integration point. Serialization options. For JSON, JavaScript object notation, human readable text schema, less by default, extremely easy to start with. This is one of the file format, and there is Abro. These are about the file formats. We don't have to know about that, but that's fine. And there is protobuf. These are all formats. When to use and when not to use file format, each format. We use JSON for learning Kafka, prototyping pipelines, working on low risk. JSON is acceptable where breakage is cheap. So these are all the file types that we can use, file formats basically. Now let's jump right into the conceptual diagram instead of just talking about the theory. We know the main concept of serialization, right? JSON, because Kafka only reads data in bytes, it has to be serialized before it is sent, and even before it is consumed, it should be deserialized. That's how it works. Now for the conceptual diagram, let's head to the slides. And let me duplicate maybe this one, duplicate, and drag it to the bottom here. Say serialization. Take this thing out. No, we don't have to. This thing stays. What we do is we're going to add one more block in between producer and the event log, and the consumer and the event log too. And just resize this arrow, copy paste. Something like that, and then goes like that. Here, before producer sends the log to event log, the events will be serialized into bytes, so the Kafka can store and transmit that bytes. Same with the event logs to consumer. Before consumer receives it, consumer process it, it should be deserialized. So we do the same here. Oh, what just happened? I just duplicated a slide. Okay. Drag them a little bit backward and then copy paste that right there. So before the consumer process the data, because it is receiving bytes, it has to be deserialized before you process. So it gets to its old state. If it is a string, it get back to the string from bytes. That is how deserialization. It is nothing but encryption and decryption. Producer encrypts the data, and consumer decrypts the data before it processes it. That is perfect. Now let's take a screenshot like that. Add it to the document. That's it. Kafka store bytes only. Producer and consumer must agree on format. So they both should be agreed on format. If they don't know what kind of data or what kind of no, they should be agreed on data. They should be not synchronized. One should be a serializer, and the other one should be deserializer for the data. So to get that, to have that original format of that particular event. So I'm going to demonstrate it with a Kafka code using pip install. What I'm going to do is I'm going to create a producer file again. Okay, a producer file again. It should be JSON producer. This is the code for that. Here, if we take a close look here, all right, so of course, we are importing Kafka producer because it's a producer code, and then we import JSON because we are dealing with a JSON file here. When we configure the Kafka producer, bootstrap servers with the port, we use value serializer. This is the encryptor basically in the producer. What we're doing here is using json.dumpsoff, we basically converting an a dictionary into a JSON file here. You see that, right? So yeah, here, this is a dictionary. And now we are converting dictionary into a JSON file using json.dumpsoff dot, and then we are encoding it, which is serializing. So we are encoding using dot encode of UTF-8. We are serializing it into bytes. First, we converted this dictionary into a JSON file, and then we converted that JSON file into bytes to send it to the consumer. That is how it works. If you don't know about, if you're not familiar with these methods that I'm using, go check that Python masterclass out. I talked about these things already, the file handling with the files using Python. So you'll get an idea of it. So that is how it works. Now what it does is it serializes, basically it converts that JSON, this dictionary into a JSON file and then into bytes, and then send it to Kafka, so it transmits it. Okay, that is good. Now what we do is we run that using Python JSON producer.py. Oh, did I close the partial? I don't know that. Okay. Now run it. JSON event sent. We customized our code to print this string at the end after it sent the data to it. That is why it is printed. Now, when we go to the topic, our topic messages, we will be able to see the whole thing, the whole dictionary saved, the whole JSON file basically here. And what else? Now we create a consumer, I think. Yeah, we create a consumer here. So we use this consumer to consume that data and see how output looks. Yep. And if we go to Docker, paste it here, run it. There you go. It does include our dictionary, which is a JSON file that we serialized. Now it is deserialized. That is what the lab actually says. So the output is a raw JSON string. Kafka did not parse or validate it. Kafka stored and returned the bytes only. Practical rules you must internalize. Kafka does not enforce schemas. You must. Serialization defines compatibility, not Kafka. Schema evolution is a design decision, not a feature toggle. JSON breaks silently, Avro fail safely. Changing serialization later is painful and risky. Serialization mistakes compound over time. Final technical takeaway: serialization is not a formatting choice, it is a long term data contract. JSON is easy, Avro is correct. JSON is easier, but Avro is correct. I haven't gone through all those file formats, but yeah, they all have their own applications. Protobuf is strict with the rules that we define. Ignoring these decisions creates permanent technical debt, and Kafka will not protect you from it. With that, our concept serialization is also done, but I would recommend you to go through all those file format and what each file formats offers. And yes, but because this is a Kafka masterclass, I don't think I have to go through all those concepts because it is already a lot of time. I've been filming this masterclass. I think I have to be quicker. I hope I'm still making every point make sense to you. Now, let's go to the next topic, next concept. Now, our next concept is consumer commits, which is our phase 4, reliability and guarantees. From now on, I'm going to just talk about the concept by my own. I'm not going to read every single line because I'm running out of time. So, talking about consumer commits, in Apache Kafka, a consumer commit records the offset position that a consumer or a consumer group has successfully processed. We all know that, right? It commits, the consumer commits the offsets. But in this concept, what we're going to know about is there are a few methods about committing the offsets. Remember when I said when we defined this concept, when I said we can use enable auto commit as true, or we can define it as false, and then we commit whenever we want. So we are going to talk about the methods that we're going to use where we can commit in a different parts of that code or process. But we have to remember you cannot commit too early, that might cause data loss, or you cannot commit too late, that might cause duplicate processing. And committing strategies includes auto commit, which we used before, and manual commit, which is turning this auto commit off and then manually committing by yourself. That is what it is about. Okay, now let's go for the conceptual diagram first. Wait, I think we don't have a conceptual diagram for this topic because it doesn't make sense. So I'm going to take that out and change these sections numbers. Doesn't make sense, right? It is about how we commit the offsets of consumers, not so it doesn't have any. You don't have any conceptual diagram. 6. This will be 7. Perfect. Let's go straight into the demonstration now. I mean the lab. We create another consumer file, commit consumer.py. What we're going to do is we're going to copy this code where we configure the auto, sorry, is this the right one? Yeah, in which we configure the enable auto commit equals false, and the rest of this is same. But what we're going to do is we're going to enable the auto commit as false, and then we commit it manually inside in the middle of the process. And the part where we're going to commit the offset depends on your requirement. If you use commit after the data is processed, you will not lose the data. Let's take a scenario where you configure this auto commit as true. What it does is right after it gets the data out, right after it gets the event, it reads the event from the log, it auto commits the offset and it goes to the next event before even processing it. When I say processing it, I mean these things, whatever the process that we do later with that data. So right after it gets the reads the data out of that Kafka log, it commits the offset, it is changed to the next one. So if the consumer crashes before the process is done, and when it comes back again on, the offset will be on the next data, right? The offset will be on the next data and the next event. So we cannot process the other consumed data. I think you got it, right? To be clear, I want to show you with an example. Let's say these are the events that you have. You have 1, 2, 3, 4. All right, these are the events that you have. And if you set this enable commit as true instead of false, let's say true, and then here you have a process to be done, which is for message in consumer, you're going to add that message or multiply that message times 2. So this is the process that you're going to commit. I mean, this is the process that you're going to do with the data that you consumed from that event, that Kafka log. And let's say you just now consumed 1, okay? You just consumed it with the auto commit as true. So when right after you consume this, the offset will be auto committed, and now the offset is at 2. Here is the now here is the consumer offset, because it is this auto enable commit is set as true. It will save the offset automatically, and the consumer offset is here now. Okay, but what if the consumer crashes? This thing crashes before it processes the data. Let's say message times 2, and you save this data somewhere in Snowflake. Let's say you write a full lengthy Python program where you save this event in Snowflake. So you consume the data. Right after you consume the data, the offset changed. And before doing this processing for that particular event, where multiplying by 2 and saving the data to Snowflake, if the consumer crashes and the consumer, if you run the consumer back again, it starts from 2. It starts from the second event, not the first event. The first event is gone, which means you did lost the data. That does have data loss, right? We does faced data loss. Now, this is one scenario, and there is one more scenario, which is where we set this as false. Then we manual commit using this line. We manual commit at the end. Now what it happens is, because auto commit is false, even after we consume this event, right, and the offset will not be committed yet because it is set to false. The offset is still here. So the offset is still here even after consuming. And then it goes to this. It gets the message from that consumer, and then it is multiplied with 2 and then saves to Snowflake. And only then consumer will commit the offset. So if the data is consumed and before processing, if the consumer crashes and consumer got back again, it will still process this data because the consumer is not saved automatically. So it will still process from this data, and we don't face the data loss. This is one scenario where we don't face the data loss unless it gets to this statement and commits. After everything, all the data processing is done and reached to this line, and it is committed, the offset is committed. And then the offset changes to, only then the offset is changed to 2. Only then only after the whole processing is done, only then the offset is changed to the next offset. There is one scenario, and there is one more scenario you have to take care of, which is, let's say you have multiple processors, you have multiple process to be done, which includes, one is to save to Snowflake and the other one is to save to CSV. Let's say the data is saved to CSV, okay? And you just, so now the consumer offset is at the first event 1, and you consumed it, and it doesn't auto commit because it is false. Now it goes through this process, and it does message times 2, and it saves to CSV. But before saving that to Snowflake and committing it, what if the consumer shuts down? Now when the consumer turn back up, what happens? It again consumes the same data, which is this event, and then does this same process again. It multiplies with 2 and saves to CSV again. Now what happens? It is already saved to CSV before committing, right? But it is not saved to Snowflake though. But now it is saving the same event again to CSV, which causes duplicates. So that is why we have to care about these consumer commits carefully to balance these, to balance the positioning of manual commits, so it don't create duplicates. At the same time, it don't leads to data loss. Now I think you got the whole concept, right? That is how this concept works. The committing of offsets work. You have to make sure where you commit the offset to avoid data loss and to avoid data duplication too. Here what we did is we set auto commit as false, so it don't commit the offsets automatically, but only when it printed processing message value, only then we commit the offset, and then we print offset committed. Okay, that is saved. Next step is to run it. I hope you got the concept correct. What it is. So it says assertion error required group ID. So it doesn't have a group ID? Oh, it doesn't have a group ID. Okay. Oh, it doesn't have a group ID here itself. All right. Let me give it a group ID. And call the group ID as orders consume and say manual offset. That's a random name. That's fine. I'm going to use this same and a comma at the end. Let's use this in our code as well. Now let's run it again. What is it again? Group ID? Why? Oh, I haven't saved it. Okay. I have to save it. Now run it. Now what happened? Oh, the quotes should be an open code, and then here should be this. Okay. Oh, in that case, I have to copy paste this in the Word document too, so you don't get the error. Merge formatting. Perfect. Now, did I save it? Save it. Run it again. There you go. So for every record, it prints the offset committed for every record we get. And yeah, that is how manual committing works. I think you got the concept, right? That is how manual committing work. And the auto committing works. You have to be precise of choosing where you commit the offsets. So you avoid the data loss or data duplication. That is the whole concept. And that's it with this concept. Let's head to the next concept, which is 4.2, idempotent producers. Now, our next concept is idempotent producers. We already talked what idempotency is, right? No matter how many times you run the producer should not create any duplicates. That is what the concept is. That is what the definition is as well. In Apache Kafka, an idempotent producer guarantees the event that even if a producer retries sending the same message, Kafka will write it only once to the log. That is what the basic concept is, and this is managed by Kafka because Kafka broker tracks the producer and also the events that are produced by that producer using PID for the producer and sequence number for the events that are produced by that producer. To make it clear, let me draw something, okay, right here. So let's say, so this is a producer. What happens here is, 4. So this is a producer. Let's say this is a producer. When producer generates events and emits events to a Kafka broker, the broker assigns a PID, which is a producer ID for that particular producer. So it can recognize it with that unique ID that is assigned to that producer. So this producer will get assigned with the producer ID, and also the events. Let's say these are the events produced, and all these events get a sequence number. Let's say for this 1, 2, and 3 for this. So all these events get a sequence number assigned to those events, so that the broker not only tracks the producer with the producer ID, it also tracks the events with the unique event sequence number. So if the retry tries to emit the same event twice, it can recognize it with the sequence number, and then it only sends one sequence. It only sends one event with the same sequence number. It don't allow duplicate sequence numbers to be injected into the Kafka log. That is how it filters these things, the duplicates out. So you know how we use retries in producers, right? We can define retries like as in this producer. You see that? We can configure the producer to retry if something goes wrong. So whenever it retries, if it sends the same event, the Kafka won't accept it because it tracks all the events that were sent by that producer with the same producer ID and the event with the same sequence number. That is how it differentiates between the producers and the events that the producer sends. That is how idempotency works in Kafka. This whole thing is about deep dive of that top concept, basically. Well, this doesn't have a conceptual diagram too, I think. You know what? It does have a conceptual diagram. Let me draw that. For that, I'm gonna use, let's say, this slide, duplicate it. And here, let's say idempotent. What I'm going to do here is take this whole things out. We don't need that. And this goes here. Producer, and take this whole container out. We just resize this. We don't need that bigger container. Okay, we do that. Perfect. Instead of partitions, we're going to call that as event A. Take this out. Like I said, every producer is identified with a PID by the Kafka cluster. So let's give this a PID, a random one, 1, 2, 3, 4. Now if we copy this, paste it, and under the event, we say and all these events get assigned with a sequence number, right? Yes. Now what we do is we copy paste another block here. Call this a Kafka log. Now I'm going to draw an arrow, insert shape, arrow, 2 arrows actually. Okay. Two arrows. Now copy, paste this right underneath, like that. Now I'm gonna copy paste this thing and say this transfer will be the first send, and I'm going to send the event with event, and that is assigned with the sequence as 0. All right. Now what it does, it does accepts it and appends that to the log. Right? So it accepts it and appends to the log because that is the first send for that sequence number, which is event A. Now, if something happened and the producer retries to send the same event for the second time, which is already stored in the Kafka log, and say call this retry send with the same sequence number, but this time because the sequence 0 is already appended to the Kafka log, this time it rejects it. This time it rejects it. That is how it makes sure the idempotency of the producer, and we can configure it using enable idempotency equals true. That is how we configure the producer. These one of the major these one of the important topic you have to know about. We already talked about idempotency, but this visual makes it more clearer in how it works and what are the parameters that a Kafka log saves to identify which event is a duplicate and which is not, right? Now let's take a screenshot of this. Perfect. Head back to the document. Pictures, screenshots. Here, I'm going to paste it. Now what this diagram shows, duplicates detected, no append. If the duplicates are detected, not appended to the log. That is how it works. And for the lab, this is just the actual producer code that we already ran before. Quite similar, right? The same producer code, this producer code, it is so similar to that. So I don't think we have to run it. It's actually exactly similar. It just changed the message that we're going to pass as an event. That's it. Exactly the same, the configuration and everything. So I don't think we have to demonstrate it. And because we are running out of time, we have to skip these type of labs and repeated concepts. And yes, that is it with it. The final takeaway will be idempotent producer eliminate an entire class of Kafka failures, make retries safe, protect log integrity without duplicates, reduce downstream complexity. If the producer generates more, duplicates that become more complex for the downstream systems like consumer and stuff like that. So if we make this, if we configure the idempotency as true, we can have these applications and we will make sure not to do this. Retry safe, protect log integrity, and reduce downstream complexity. There is no valid reason to disable them. There is no valid reason at all. It is always best to enable them. They are not optional, they are foundational. That is it with the concept. That is it with the idempotency producer. Idempotency in producers. That is it. And now let's head to the next concept, which is 4.3. Now let's talk about the delivery semantics. This is one of the important topic too. A delivery semantics define how many times an event may be processed when failures occur. And yeah, it basically says how many times an event may be processed without failure when failure occurs. And there are three types of delivery semantics, which include at most once, at least once, exactly once. And they all three of them have their own advantages and disadvantages and applications too. Why delivery semantics exist? Failures are normal, not exceptional. Producers crash, consumers restart, networks drop, acknowledgements, broker rebalances and recovers. When something fails, do we lose data, duplicate, or retry safely? Delivery semantics define the answer explicitly instead of hiding it. Now we're going to see the difference between these delivery semantics. First, at most ones, behavior. Producer sends a message, no retries on failure. That is what at most one says. So it only sends message once and no retries even if the producer fails. Consumer commits offsets before processing, which means we talked about this before, right? Before processing, which means the consumer has the enable auto commit equals true. So it commits the offsets before processing. That is part of at most one's semantics. And there is no retries on failure, which means the producer is configured as retries as 0 or not configured at all. And so by default, the retries will be 0. I mean, retries will be 1 by default, so no retries. It only tries once. It only tries to send the data once, and it won't retry. So if there is no retries on failure and consumer commits offsets before processing, that is part of at most one semantics. Now, what will be the failure outcome from this? Data loss is possible because if the producer fails once, it will not be retried, right? So the data loss will be possible because of that. But the good thing is there will not be any duplicates in the data. Because it won't retry anyway, right? If it fails, it won't retry. When it don't retry, there is no chance of getting duplicate events. Even if we don't configure the idempotency at all, because it doesn't retry, there is no duplicates. These are the two parameters if the failure outcome occurs at most one semantics. It is like the semantics are like how we structure the relation between producer and consumer. That is what defines what semantics we are working here with. So that is it with the utmost ones. And now we talk about at least ones. And at least once, like the name says, producer retries on transient failures. If the producer fails, it retries again. But consumer commits offset after processing. All right. So what it happens is basically the system is like this. So producer retries on transient failures. Producer does have retries, okay, right? But it is not configured with enable idempotency here. It is not configured with this. So, but it does have retries on failure, but consumer commits offset after processing, which means like this. The enable auto commit will be false and only commits after the processing of that event is done. And the failure outcomes will be no data loss at all. No data loss because it retries, because we configure the retries in that semantics. So there will not be any data loss. But there is a duplicates possibility because we retry again and again. There is a possibility of duplicates. Those are the two failure outcomes. Now talking about exactly ones. Here, producer uses idempotency. Remember when I said at at least one semantics, we will not use enable idempotency, but whereas in exactly once, we will use enable idempotency as well. And messages are written within transaction. Consumers read only committed transactional data. So we configure these producer and consumer relationship so they're written within transactions. So the data will be treated as transactions and not events. Failure outcomes: no data loss and no duplicates as well. That is what exactly once is good at. Good at. Now the requirements for this semantics includes idempotent producers. The producer should be idempotent, which means it should be enable idempotency should be true, and transactions enable. There is one more concept called transactions. We have to enable the transactions for that producer. So the events will be sent through transactions and not single event at a time. We will talk about it in this concept itself about transactions. Correct consumer isolation and commit logic. Using the commit logic manually with the correct isolation, with the correct format. These are the two requirements, and the third one, transactional enable. We will talk about that. I will demonstrate that in the lab. Now, when to use, when not to use, they all have their applications and downsides and upsides. And yes, now heading to the conceptual diagram. We have three conceptual diagrams for this concept. One for at most once, one for at least once, one for exactly once. First, let's go to the slides, and then I'm gonna duplicate this slide and drag it to the bottom. Change the heading as Delivery Semantics. Then what I'm going to do is just going to take everything away. We don't need that. And the first heading, copy this. The not bold one for the subheading. And the subheading for this will be at most once. First one with the producer, and then paste it. Another block saying fail. Copy paste this. Change the size of these blocks. Perfect. Say no retry. Insert the shape which are arrows and connect those arrows from producer to this, and one more arrow, shapes arrow, from fail to no retry. So this indicates if the send fail, it don't retry, because in at most one semantics it is not retried. So we are trying to indicate that, annotate that with no retry block. Then just copy paste this right here. But what I'm going to do is like that, draw another arrow, copy paste this arrow from producer to consumer. What this does is consumer commits the offset before the event is processed. So it commits the event first, right? Perfect. And then it processes that event. That is how at most one semantics work. I think this is a good representation of a conceptual diagram. Let's take a screenshot. Head back to the document and pictures. Paste it here. Head back to the slide. Now I'm going to duplicate this slide. Copy paste. Now we talk about at least once. Talk about at least once now, where the producer retries. So this will change. Okay, so the producer will retry if something goes wrong. And these will also change. So consumer first process the data, process the event before it commits the offset. I think this is perfect representation for that. Perfect. Now take a screenshot of that. Head to the document. Copy paste it here. Now for the exactly one semantics, again copy paste it. What changes here is the diagram will stay same, but something extra will be added, which is the producer is idempotent. So there is no chance of duplicates. And also the events are transferred in transactions and not single events. So a transaction fails, it retries the transaction again. And because of that, and the idempotency enabled at the producer, there will not be any chance of creating duplicates, or there is no chance of getting data loss. That is the conceptual diagram, and let me take a screenshot of it. Go back. There you go. Now for the lab, we're going to name the file as producer retries. These for the at least ones, by the way. And also, we don't have to demonstrate all of this, but the codes are ready here. You can use those codes to run. So what is basically at least once? We say we talking about at least once. The producer should have retries configured like we did here, but we already did before with the producer already, so I don't think we have to demonstrate that again. It just eats the time. And then at the part of consumer, the the auto enable auto commit should be false, so we manually commit the offsets when we process the data. The data processing is done. That is what at least one semantics is about. And what is at most ones? The same code, but enable auto commit should be true, which commits the offsets before even the event is processed, and there will be no retries configured. That's it. That's the difference between these two. And there is exactly one semantics, which, like I said, it is configured with a transaction. So we say the transaction ID as my transaction producer here. So all the events goes through transactions. So it says here, so we use try and accept here, exceptional handling, by the way. So we use producer.begin transaction, so that begins a transaction and tries to send producer.send, tries to send this event to this topic and producer, and then if that is successful, then commit the transaction, the whole transaction. It will not commit the offset until the whole transaction is completed. So we start the transaction begin the transaction using dot begin transaction and commit the transaction using dot commit transaction. That is how transactions work. Nothing different, but we just introduced this concept transaction when we use exactly once. It does also have retries, by the way, and idempotency is equals true, so which stops the duplicates. And in the exception, if everything goes right, only then the offset will be committed, or else except producer.abort transaction. The transaction will be aborted and will not be committed. The offset will not be committed. And then producer close. The producer will be closed, which makes sure there is no data loss and there is no way to create duplicates. These are the transactional processing in exactly one semantics works. I think you got it. You got this concept correct. Now, final technical takeaway. At most one trades correctness for speed. At least one trades simplicity for duplication. At exactly one trades complexity for precision. These semantics is complex when compared to these other two semantics, at most ones and at least ones, because it introduces transactional processing, but still it is complex but precise. That is how exactly one's semantics work. Right now, I'm not demonstrating this because I don't have enough time, but maybe in my next video, I'm going to, you know what? Let me take a second here. You know what? I will demonstrate this lab because I already skipped a lot. So let me copy this file name here, create the file with that file name, producer idempotent, copy paste this whole thing. You see that the Microsoft Word added a lot of unnecessary spaces and new lines. You have to take care of that. Well, Python doesn't care about these new lines, but for the readability, I'm going to take those away. Okay, saved it. Now, let me just run it. I already explained the whole code, so I'll just run it right away. Python. Message sent with exactly one semantics. Now let's check if the message is added using the UI. There you go. Order 101 added at the time. That is what we added with the producer, right? Order 101. That is how exactly one semantics works. We begin the transaction and we abort the transaction if something goes wrong. If everything goes fine, we commit the transaction. That's it. That is the major difference between these three semantics. It is not worth it to actually demonstrate the other two semantics, but transaction, this exactly one semantics does need to be demonstrated. That's why I demonstrated that. And that's it. We're done with the whole concept, that the delivery semantic concept as well. Now let's head to the next concept. Now we talk about advanced Kafka, phase 5, and topic the concept 5.1, retention policies. We already know what retention means, right? In Apache Kafka, retention policies define how long data is stored in a topic and under what rules it is removed or compacted. We already talked about it. It defines how long the data should be stored in the log. And when we define this configuration, this should be defined when we create a topic. Or even after we create a topic, we can alter the topic configurations and include this configuration, retention.ms, if you want to define the retention time with microseconds, or I mean milliseconds. And if you want to define the retention time with hours, you use retention hours. And if you want to define it with the bytes, and how this works is deletes data when a topic exceeds a size limit. So if a topic exceeds a size limit, regardless of the age, it deletes the events. And this can be configured using retention.bytes. So there are types of retention policies, and there is one more configuration that can be done, which is cleanup policy, cleanup.policy equals compacts. Right now, till now, these retention policies depends on the data that the event that the topic has, which is if the events in the data exceeds a certain time limit, it can be deleted using time-based retention, and by size-based retention, it can be deleted if the size exceeds if the topic exceeds the size limit. And we can define the size limit by bytes. That is one of the ways. And there is log compaction, where we say cleanup.policy equals compact. When we define that, what happens is if the data in the partition have the same key, it compacts the log, and only the latest value of the latest key, only the latest value of that particular key will be stored, and the rest will be taken out just to save the space. So only the latest value of that key will be stored. That is what it says. Topic represents a state, and any latest value per key survives, and the rest will be gone. These are the three major configurations that we can do in retention. Now, for the conceptual diagram, from now on, I'm going to use these I already did these diagrams, the conceptual diagrams. I'm going to use them because I'm running out of time. This is first for the retention time. So if the retention time exceeds, if these two particular events right here, let's say if these two events exceeds the retention time, they will be taken out. So to represent that, what I did is, this is a topic log. If the retention passed, AB will be removed. This is a good way to represent it. Now I'm going to take a screenshot of that, add it right here. Like that. Now coming to the compaction is this one. Like I said, if multiple values belong to the same key, which as in this case, the same key 101, so multiple values belong to the same key, it only takes the latest key. Oh, so it should be this. So it only keeps the latest key, which is order shipped, and the rest of the old keys will be removed just to save that extra space, to make topic more, to save the storage on that particular topic, that particular broker. So this is one of the way for retention. And before, this is the before and this is the after applying this configuration, cleanup policy equals compact. Now, of course, a screenshot. And then use it here. And the lab includes creating a topic with these two configurations, which includes configure retention.ms. We are here defining retention.ms in milliseconds, and the seconds will be 864. Now, wait, 8,640,000, which means a day. So this is nothing but a milliseconds in 24 hours. So the retention for this is a day. And the cleanup policy equals compact. We know how it works, right? So this is nothing but creating a topic with these two retention policies, the configurations. Okay, let's just demonstrate it, all right? So I'm going to copy this, paste it here, remove that, remove that, remove that, remove that, remove that. Nope. Copy the whole thing, copy. And I'm already inside the container here, the Kafka container, so I'm going to paste it here. Click enter. Now that creates a new topic, right? Okay, that creates a new topic, all right? Now our next step is we're going to produce the data. Okay. We're going to do that and produce the data. We are separating the keys, by the way, here. So we go there and paste it. Oh, something went wrong. Wait a minute. Okay. No. Oh, something went wrong. Did I take out the spaces? I did. Now copy that again. Paste it. Oh, I forgot. I forgot to add this at the beginning. I have to edit the document as well. Now paste it. Now here, I'm going to generate or produce the events. 42 active, 42 suspended, 42 active. Okay. Say 42 active and 42 suspended. Okay. And again, 42 active. Now what happens is, even if I send all these three, it only, wait a second. Let me go here, the topic and the messages. Okay, I messed up with the last one. There you go. Now that is perfect. Now we have three, right? Now we have three events for the same key, 42, 42, 42. But this is the latest one. And we created this topic with the configuration as cleanup policy equals compact, which means this topic will take down these two events down and only keeps the latest event, which is active, to save the storage space. But this might take a few minutes to actually react to that. So I may not, I, I think I cannot show that to you right now, but because it takes a few minutes. You see that? So yes, that's how it works, by the way. Okay, heading to the next one, the final technical takeaway. Deletion manages capacity because we delete the unused or not required ones out, the events. So to save the capacity, compaction manages the correctness, and durability does not mean infinity. These are the final technical takeaways. And with that, the retention topic is also done. Concept is also done. Now let's head to the next concept. Talking about log compaction, which is our next concept, we already know how log compaction works. We already created a whole the conceptual diagram already for the log compaction and how it works, right? We just compresses all the values which belongs to the same key and gets the latest one stored so that it saves the space. That is how it works. And this concept is nothing but diving deep into the log compaction even with the same lab that we already done. So I don't think it is worth to go through the whole concept again. So let's skip this concept and go to the next concept, which is Kafka streams. Okay, from this concept onwards, I thought it is not worth it to explain every single thing in that concept, because from now on, there is no demonstrations at all from the rest of the concepts, because I cannot do that. And I will also explain why I cannot do that. Okay, starting with Kafka streams. Kafka streams is a Java-based stream processing library that is part of Apache Kafka. Use it to read data from a Kafka topic and process in real time and write the results back to a topic. That comes with the Kafka itself. But the reason why I cannot do that or demonstrate that here is because Kafka streams is a Java library. So it should be coded in Java. We have to use Java to actually use Kafka stream. And that is the reason why we cannot demonstrate it. And in the lab section, I clearly mentioned it in the document also. That's why. But we have to know about this concept that exists, which is Kafka streams, where we can pull the data out of a topic and process it and then write the data to another topic, a different topic. And this processing can be anything: aggregation, summation, or windowing methods, anything. But we have to code it, we have to use Java to write to use Kafka streams, and that's why I cannot demonstrate it in this masterclass. But I will show you the conceptual diagram, which is this one. So this annotates topic A, gets the input from topic A, and stream processor, it processes the stream, and local state store, it stores the local state. This is the Kafka stream application, and the output will be sent to topic B. This is the basic conceptual diagram. Now, I'm gonna save it there. Now heading to the next concept. From now on, these are the advanced topics, and there are a few topics you have to know about, and they don't have any demonstration. That's why I'm going to go definition to definition and say what the topic is about, and just leave it. Because they don't have demonstration, we don't need to spend much time on it, because this masterclass is already exceeded the expected time. So I want to make it quicker. Now, talking about Kafka Connect. Kafka Connect is used to connect to an external service. Let's say Kafka Connect is a data integration framework within Apache Kafka used to move data into or out of Kafka reliably using pre-built connectors. We don't have to define a connector like we did in this Python code. We don't have to define a connector. We can do that through a pre-built connectors. We can connect to an external service, get input from it, or push output to it. Let's say an example. If you want to push the data into a Snowflake, you can use connector. You don't have to configure it like this, but it only works with the files or databases, or yeah, files or databases, something like that. Whereas Snowflake is a database, so it is used to connect to Snowflake. Yes, that is basically it. So that is the concept of Kafka Connect, but I cannot demonstrate it because I don't have any access. I don't have access to any of these tools, GCP or Azure or any Google cloud platform or any Google cloud storage right now to actually connect to that storage. But I do have connection. I do have access to Snowflake, but still, it is a complex process to set Kafka Connect, because it includes the authentication and IAM configurations at the Snowflake side and also at the Kafka side. So it is quite complex to actually include that demonstration in a masterclass. So I want to exclude that demonstration here. But there is a concept. But if you want to know more about this Kafka Connect, I will definitely make a dedicated video, just a project where we connect to an external source and get the data streamed, or push the data as a stream into one of those cloud platforms or cloud storages or databases. Okay, for the conceptual diagram, this is the conceptual diagram. There are two types: a source connector where we get the data from, so that is called source connector, and there is sink connector where we push the data to. The source connector includes external system, which can be anything: Snowflake, Google Cloud Storage, or anything like that. We use connector to connect that and get the data from the external system through the connector to Kafka topic. And we have sink connector where we connect to external system. Through connector, we get the data from Kafka topic and then store it inside the external system. That is what called sink connector. Take a screenshot. Save it here. Oh, like that. Perfect. Now let's head to the next topic, next concept, which is in phase 6, scaling Kafka. In Apache Kafka, scaling means increasing throughput, parallelism, fault tolerance by distributing data and workload across the clusters, which includes partitions, right? Partitions are nothing but scaling, and also brokers, multiple brokers, scale the clusters itself. We can scale the brokers itself. We haven't talked about this concept before. We not only can scale using partitions, we can also scale using brokers as well by creating multiple brokers to share the same data. I mean, not exactly the same data, but the data that is related to each other. We can split the data through across the set of brokers as well. And the conceptual diagram will be more clear for you. Okay, so in a Kafka cluster, we can create multiple brokers, right? It can be multiple virtual machines running as a Kafka cluster, and broker 1 can have the same set of data, the same related data, and it can have partition 0 and partition 1 in broker 1, and the same category, the same data category can be saved in broker 2 in partition 2 and partition 3, and whereas in broker 3, partition 4, partition 5. We can also split the data between the brokers like that. And that is one of the thing we haven't talked about. That is one of the characteristics of Kafka scaling. We can split the same categorical data between the brokers, which belongs to the same partition, same topic. Instead of using brokers just to replicate, we can use brokers for this as well. We already talked about an example where we replicate the same partitions between brokers, where right here, right? We just partition the same data, we replicated the same data across the brokers, but here it is different. We are saving different data, but splitted those data throughout across the brokers. So this will also, offers parallelism. This one sort of parallelism, and partitions are one another sort of parallelism. That is done. That is it with the concept. We already talked about scaling with partitions, and now we talked about scaling with brokers. Let's take a screenshot of that. And perfect. And our next concept is monitoring and lag. We talked about lag. So in Apache Kafka, monitoring means continuously observing consumer logs, throughputs, and broker health. That is what monitoring means. We have to continuously observe those parameters. And we already talked about this. By using a command, we described the topic. We did describe it, right? And then we checked the lag between the consumer and the end of the offset. You see the log end offset. So this is the formula. This is the actual formula. Lag equals log end offset minus current consumer offset. This is how we calculate lag. And we talked about it before. Does this have a lab? Oh, it does. Oh, the lag doesn't show anything. The same thing. The lag just simulates the lag here by processing it slowly using time.sleep of 2. So this delays, what this does is, this delays the iteration for 2 seconds. And that's it. That's how we delays that. And we check it using this. So we describe the consumer using this. We already did. And then we check out the current offset, log end offset, and we calculate the lag by subtracting it. We don't calculate it. Kafka by default calculates it. So we monitor that. So that is what logging and monitoring means. We already talked about it a lot of times throughout these concepts. So I don't think we have to go deep into it again. That's the same thing basically. But if you want to know more about it, if you want to know in practice, you can just run this lab. But for now, I'm going to go here. Oh, these a demonstration. These are conceptual diagram for lag. A producer last sent message will be event D, right? So this will be the last sent message in this partition. If the consumer offset is at offset 0 and the producer last sent event be event D, the difference between the consumer offset and the log end offset will be the lag. This is the lag. This is what the lag means. Okay, this is a good conceptual diagram, so I'm going to take a screenshot of it as well. Where is the conceptual diagram? There you go. Paste it here. Now, heading to our next topic, which is Kafka in real data engineering. We'll see how Kafka is used in real data engineering. Again, no demonstrations, no conceptual no, there is conceptual diagrams, but no demonstrations. So in modern data platforms, the core idea, Apache Kafka acts as a central event backbone that reliably moves data between systems. That is the main job of Kafka, right? But it does not orchestrate workflows. To orchestrate workflows, we can use Apache Airflow, like I said. To execute business logic, we can use Spark. To perform analytics, we can use Snowflake. It doesn't do anything, it just transports the data from one place to another. That is the basic concept of Kafka. Now, we talk about two patterns here. Two most usually used patterns, which is pattern 1, Airflow, Kafka, and Spark. What happens is Airflow schedules the producer to send the message, and that scheduled time the producer will produce the event, and then it will go to Kafka. Kafka streams it to Spark, and Spark will process the data. This is one of the pattern, the most common used pattern. And one more pattern, which includes Kafka to Snowflake. Instead of going to Spark, the Kafka sends the data to sends the events to Snowflake. This is one of the other patterns that is mostly used. That is for Spark, and this for Snowflake. And there is a conceptual diagram for both. This is pretty easy. Like I said, Airflow schedules the trigger, and the events will be then streamed to Spark. Whereas in first, let me save this. Okay, in conceptual diagram, where is it? Right here. Perfect. And for the pattern 2, Kafka cluster, streaming buffer, connection layer. We talked about connection layer, right? Connection layer is used to, Kafka Connect is used to connect to an external source. We use connection layer here to connect to Snowflake, and then Kafka will send events to Snowflake. This is one of the commonly used pattern. Let's take a screenshot of this as well and paste it here. Perfect. And that's it. Finally, the final architectural takeaway. Kafka does not orchestrate like Airflow. It is not that. It doesn't belong to that. Kafka does not compute like Spark. Kafka does not analyze like Snowflake. Kafka's role is narrow and critical. Kafka is a spine of the data platform, not a brain. Systems think. So Kafka is spine. When I say Kafka is spine, just like the spine connects every organ to the brain, the Kafka will also connect all these parts together with the stream. That's it. Kafka doesn't do any of the other tasks. It just connects these tools together with a stream. And that's it. I apologize for the last explanations that I've done for the last few concepts. because I'm just running out of time, and this masterclass is already so unhealthily lengthier than I expected. So I want to finish it faster. But the important concepts like Kafka core concepts and working with Kafka and reliability, all of those phases, I did explain it crystal clearly. So the concepts that I just haven't explained in deeper are the concepts that are not that important. Without those concepts, we can still work. These concepts make your but these concepts, knowing about these concepts, make your knowledge sharper. That's it. Hope you understand what I mean. But still, you will get this document if you want to know more about these concepts. The end of these two last phases that I explained with a little momentum. I mean, little faster. You can still dive deep into it slowly. I'm going to give you the whole document anyway. But here's the thing: the last 5 concepts doesn't have any demonstrations at all, right? So it doesn't make any sense to take longer to explain them. So that's why I just go through the definition and then said what it is, and then the reason why I cannot demonstrate it as well. And that's it. With that, Kafka Masterclass is officially completed. Hope you like it. If you like this video, don't forget to subscribe and share to your friends who actually want to learn Kafka too. With that being said, we will meet in our next video. Until then, adios.